Quanti siamo adesso? Good morning to everybody. Can you try to switch on the camera?
Scusa? Buongiorno. Ah, ecco il nostro regista. Buongiorno. Ciao Fulvio. Quindi tutti quelli che sono comparsi adesso si chiamano Diego Fantoma.
E
Sì,
come
questo è
mai?
vero.
Come mai?
Anche Fulvio ha cambiato nome, è vero?
Io no, infatti, ciao Diego. Io invece no, no. Siete appunto tutti in una stanza e quindi sì, però così non si vedono neanche i partecipanti. Delle prove. Sì, era quella l'idea, però non era quella l'idea. Così non va bene. No, no, aspetta. Sì, ma come siamo divisi fra uno e l'altro? No, io vedo solo un po' di partecipanti. Tutti gli altri stanno in Diego Fantoma.
Ciao Anna, hello.
Ciao.
Ciao Barbara.
Hello. Ciao, ciao.
No, ma io vedo solo pochi partecipanti, in particolare appunto molti stanno in Diego Fantoma, però non li vedo, li vedo ogni tanto. No,
Io ho 10 partecipanti in questo momento. Vedo 10 partecipanti.
And how many should it be?
ad esempio Diego Fantoni, Diego Bettoni e Stefano Fantoni non li vedo. Quando
Ma
partono, vedi?
Diego, devi uscire da questa breakdown room e così inizi a vedere tutti gli altri. L'ho appena fatto, perciò...
E direi di sì, perché altrimenti non si capisce chi sta dove.
Sì, adesso stanno aumentando, infatti.
Sì.
Sì.
Ciao Franco.
Ciao.
Che ora è?
Secondo il mio cellulare manca meno di un minuto. Quindi va bene essere in tempo. Ciao Stefano.
Ciao, ciao carissimo. Ti vedo dietro davanti ad una grande libreria.
Hai visto?
Mm,
È la mia tana,
è la tua tana, eh?
la mia stanza di lettura e della musica.
Bene.
Bene. Good. Let us switch on the workshop. Dear Compass colleagues, dear participants, it is with great pleasure that on behalf of the organizing committee, I open the 2020 International Workshop on Hadron Structure and Spectroscopy. As most of you know, this is a series of workshops we have started almost 20 years ago to introduce our collaboration meetings in outside of CERN, in one of the institutes of the collaboration. The series started in 1999 in Munich, and the first workshop was organized by Stefan Paul. The second one, the year after, in Dubna, and the third one in February of 2002 in Trieste. So this is the second time we do it in Trieste. And very much as for the first time, also the second time has a particular meaning. In 2002, in February, we were about to start the first physics data taking of Compass. 2002 was the first fruitful year of measuring with a polarized target, semi-inclusive dip inelastic scattering. Now we are about to start the last physics run of Compass, namely a run with the transversely polarized deuteron target to close up our preliminary investigation of the transverse spin and momentum structure of the nucleon. So we are very happy to have you here. And as a reminder, I just flash one of the many pictures you can find on the web of our Trieste Home Institute, INFN section. And if you look carefully at the picture, you'll recognize many of the present Compass collaborators. Although most of the ones who were young in this picture have gone away and to different laboratories and to different experiments. The picture was taken at ICTP, where we had this workshop. So as you know very well, we tried our best to have this workshop in presence in the old harbor, in the buildings of the old harbor of Trieste, but things went out different. We wanted to have it in May, and it was organized in collaboration with the many events which took place in Trieste this year, because Trieste this year was the European Capital of Science, and Stefano Fantoni in a while will tell you something about that namely about as of 2020. Of course, May was not a good time this year, so we had to postpone. And in April, we decided two things. Well, first of all, we decided to keep the workshop this year, namely in 2020, not to overlap with the run of next year. And then we decided when. And on the table, we had two proposals, either September or November. And the group leader board of Compass, in its infinite wisdom, chose November. That's it. September would have been much better, but it's not our fault. Anyway, we hope that in spite of this, the workshop will be a good one. In a way, it could even be one of the best we ever had. There will be no distractions. You won't walk out to look at the sea or to the Indian colors of the surrounding hills in Trieste. So we will stay close to the PC, and please switch on your camera and please ask questions so to make this workshop really effective. Okay, enough to open up. And now I would like to ask Diego Bettoni from the executive board of INFN to greet all the participants to the workshop.
Excellent. Thank you very much, Franco. It is a very great pleasure for me to be here and welcome you to this workshop, to this virtual workshop on behalf of the INFN president who could not be here this morning because of other commitments. And so Franco asked me, and I'm very happy that he asked me because besides being a member of the executive board, I am also very close to this community because in my scientific career, I have my research activity has been mostly concentrated on the Hadron spectroscopy and Hadron structure. So I think it's a very great pleasure for me to be here with you and to see virtually many friends among the participants, people that I have shared both scientific and also managing interests over the past few years. So also for us, it would have been much more pleasant to welcome you in person. But as Franco said, the situation is not yet such that to allow meetings of this magnitude to take place. In fact, since the second half of October, all meetings within INFN take place virtually. They are online meetings. We have stopped all meetings in presence. INFN is not closed. INFN is still continuing its activity. We have about 60% of the persons that go to work every day, and the rest works from home. Our laboratories are open, although for different reasons, there is no beam now either in Catania or in Legnaro for different reasons, but basically because of the work which is being done there to build and to go ahead with the projects of the future, the upgrade of the cyclotron in Catania and the space project in Legnaro. So as I said, it is a great pleasure to welcome you because this community is very close to my scientific interests. It's a science which INFN has done for many, many, many years, as Franco reminded us before. We've done experiments at CERN, at DESY, at JLab, but also at the plus and minus machines, like for instance now in China in BEST 3, the part of the scientific program overlaps with what is done by this community, mainly Hadron structure. And it's not only the past, but also the future, which we look forward to. As you, all of you know, we have this very important project, which is being born in the United States, the EIC, the Electron Ion Collider, and the INFM, in its usual bottom-up approach, has built a community, actually a very large community, which is interested in this, in experiments at these new machines. And we are moving to participate and to give a qualified participation to this project. So I am, again, very happy to be here to welcome you. I wish you a very successful workshop. I wish I could stay here and listen to some of the talks, but unfortunately, I have another meeting at 9:30, so I must leave now. But I will look at the transparencies if they are available online. And again, my best wishes for a successful and also pleasant workshop, despite the fact that it's a virtual workshop. But the physics is very real. Thank you.
Thank you, Diego. Thank you for your nice words and for your wishes. And now I ask Stefano Fantoni, who was the champion for ESOF 2020, to give us his welcome.
Thank you, Franco. Thank you very much, and thank you to all of you. I mean, it is a great pleasure for me to convey the welcome of Euroscience, which I represent in this particular moment, and the welcome of all the members of the team of ESOF, the team that has organized the 9th editions of the Euroscience Open Forum in Trieste. As Franco said, this event in September was essentially a sort of sum up of the 20 years of science for Trieste. Trieste, as he was recalling, has been, is still actually the city of science, European city of science. And so Euroscience, ESOF was substantially the clue of this. That was done in September, but with detail, and actually it is very important, I think, and very significant, the fact that we started in the opening session with Fabiola Giannotti, and we closed substantially with you. We close with another important fundamental meeting, and it is very, I mean, I think we should be, we in the sense of people being interested, should be very proud to host the, what is the 17th edition, if I'm not wrong, of this fundamental, say, review of the status of the Hadron physics, particularly devoted to the Hadron structures and spectroscopy. ESOF is a biennial appointment of science with society. So I think that is very important that a meeting like this is just hosted. I mean, it's just along this event. And this appointment, as a matter of fact, is a show up of science to society. And during this show up, actually, science also listened to society, to what are the main questions that society is raising to science, and so it's important in the sense that it is the only event, international event, that is doing this in Europe. it is a place in which science discusses about the new trends and even the new pathologies that may have been arisen in the last times. And it also discusses and dialogues with entrepreneurs in the direction of innovation processes. I mean, it is innovation and sustainability, let me put it together, which they are going together in a way. And for me, it has been very important that it is science to start up this or to reinforce this dialogue, because actually in many places and many people actually consider science not really present into the innovation process, which is a big mistake, according to me. So science is really the art of innovation. And as I said, I mean, it's very significant the fact that we started with CERN and we finished with CERN, which means that science is just in front of us. A second aspect that I want to recall is that, and that Franco has already mentioned, is the fact that this event and all the activity that has been done during this year is just a first step for a strategic project that this territory, in particular Trieste, is following. The project is substantially, we can call it the restructuring of the Porto Vecchio, that is the way in Trieste is called up, which is an old Austrian harbor. And that restructuring means to go into the direction of a new harbor of ideas rather than ideas and innovation, rather than an harbor of goods. I think it's very important for us, I mean for science, for the scientific community, that this step is done by science, which is very substantially, that put the complex, scientific complex of this territory in a very strong position, or at least it should be in a very strong position. So that is just to say why I think we of the team of ESOF, and I think we of Trieste, and we of Italy, I would say, and particularly grateful to all of you to being here. Actually, we are not here because the event, unfortunately, is in virtual, because the time is still is not allowing anything else. In September, it would have been a little bit better because we could do the event in hybrid form, which at least allows a certain number of presents, which we had. But I mean, it doesn't matter too much. I think it's like if you are here, we can embrace each other virtually. And I think if I can, I should like to invite you for a new edition, this time really in Trieste, so that we can really just embrace each other really, and not only virtually. So having said that, I think I wish you a fantastic conference. I am sure it will be, and I also wish a long life to the research in Hadron structure, which is actually my art. And of course, it's only in my art, because in my brain it cannot be any longer because I'm too old. But so, and having said that, I thank you very much for having invited me in this introduction, say, of the event, and I wish you all the best for your conference. Thank you very much.
Thank you very much to you, Stefano, and congratulations for all the achievements you have obtained in Trieste. Okay, now it's time to switch to the real workshop and start with the first physics session. So I pass the chair to Boris Grube.
Hi, everyone. Welcome to the first session. It's a great pleasure for me to chair this first session, which will be dedicated to low energy QCD and meson spectroscopy. And we start with low energy QCD, which will be a shared presentation by Stefan Paul and Norbert Kaiser. I see you are both connected. I think it would be great if you, I'm not sure which of you will start. Maybe first thing is that you unmute your microphones. Ah, okay, here we see the slides, very good. But we still cannot hear you.
Okay.
Ah, now we can hear you. Great. Okay.
Okay. Boris, thank you. Thank you very much for the introduction. So it's a great pleasure for me to give this opening talk in this workshop together with Stefan Paul. It's about chiral perturbation theory. So I will cover the theoretical part, means I will introduce this effective field theory and tell you about tests which have been obtained with the COMPASS experiment, and Stefan Paul will cover recent experimental results and perspectives. Nur ich schon hier drauf. Ich nehme den hier. Okay. So this is what will come today. This is concerns mostly the part of Stefan. Oh, sorry. I see this.
It's too much.
Too fast.
Too fast for me.
Okay, so this is my introductory slide, where I will remind you about chiral perturbation theory, what it is, and what highlights we have seen so far. So in short words, chiral perturbation theory is the effective field theory of quantum chromodynamics at low energies. It's based on the feature that we have spontaneous chiral symmetry breaking. So SU2 left cross SU2 right is broken down to SU2 vector, the usual isospin symmetry. And in this scenario, the pions emerge as so-called Goldstone bosons. And their low energy dynamics, so they are the effective degrees of freedom in this effective field theory, can be calculated systematically and also accurately in chiral perturbation theory. And this means one performs a loop expansion, so as it is known in quantum field theory, with an effective Lagrangian, not a fundamental Lagrangian. A basic quantity is the pion-pion scattering amplitude, so the interaction amongst the Goldstone bosons. And to lead in leading order, the pion-pion scattering amplitude is given by this expression here, S minus m pi square over f pi square. The scale parameter which enters is the pion decay constant, and you can see it grows with energy, means at small energies the interaction is weak, and this is a basis for being able to do perturbation theory. Here you see a very prominent result, namely a two-loop prediction for the isospin 0 pi pi s wave scattering length. It has the value in theory 0.22 plus some small error bar. And this prediction has actually been confirmed by the E865 experiment at Brookhaven through the pi plus pi minus mass distributions in this rare decay mode of the pions with a pi plus pi minus and a lepton pair in the final state. Let me tell that at leading order, the scattering length is 0.16, so this means there are sizable corrections at higher orders. There's a second scattering length, the one for isospin 2, And this could be determined from a cusp effect in the 2 pi 0 mass spectrum in this decay mode of the charged kaon, k plus 2 pi plus 2 pi zeros. Through rescattering, there occurs a cusp effect at the pi plus pi minus threshold, and this is directly proportional to the scattering length differentials, which is the transition amplitude from pi plus pi minus to pi 0 pi 0. And there is also, again, nice agreement, good agreement between theory and experiment. One consequence of this nice agreement between theory and experiment is this concerns now the basis of the chiral perturbation theory and our thinking about the spontaneous chiral symmetry breaking, that this quark condensate, the order parameter, is really large, and the pion mass, which is due to finite non-vanishing quark masses, its square is dominated by the linear term to something like 95%. So if that would not be so, then this quadratic corrections would be large, and there are large parameters involved, which would give totally different results for the scattering length. It's also interesting to look with chiral interactions beyond perturbation theory. So we have seen that there's a moderately attractive isospin 0 S-wave pi-pi interaction, and this can produce, upon iterations to all orders or just unitarization, a complex resonance pole. So in this first line, you see what comes if one resums bubble diagrams from rescattering. So they end up in such a geometric series. And the denominator can actually go through 0. So you see the ingredients, the isospin 2 driving interaction, and this loop. An even simpler view to see the occurrence of a resonance pole is given by the inverse amplitude method. So where this basic amplitude A00 is unitarized, leads to this expression. And one says this denominator can go through 0. There is a complex pole at square root of S 1 minus I 462 MeV. So this tells us that the pi-pi interaction is sufficiently strong to generate such a complex pole. Of course, all this has to be scrutinized and has to be confirmed. And it was verified by detailed calculations of pi-pi scattering with dispersion relations and solving Roy-Steiner equation. And this here are the people who have this done with increasing accuracy. And now we are at the position that we can say the sigma meson pole is rather accurately determined. So the mass is about 450 MeV and half the width, 280 MeV. So this pole is there. It's somehow unavoidable. But at the same time, one has to say, and this is important, that there is more to the physics of the pi-pi S-wave than just the occurrence of this pole far from the real axis. So you see here the phase shift, isospin 0 S-wave phase shift. And if you look at 450 MeV, where this pole is, there is just nothing. The phase is continuously rising, means this complex pole far away produces some smooth background, and you do not see any other features at real energies. So this resonance generation through unitarization iteration occurs in other channels. So where such complex poles can be dynamically generated. So it applies to the kappa in the pion kaon S-wave with isospin 1/2. The F0 and the A0 can be understood as complex poles generated by mesonic final state interaction in coupled channels, or even this lambda baryon can arise as a quasi-bound state in the coupled pi sigma k bar n channels. So now let's talk about things related to compass. So compass, since its starting, had a dedicated program to measure pion-photon reactions via the Primakov effect. So this is the expression to extract via the scattering of high energy pions in the Coulomb field of a high C nucleus cross sections for pi minus gamma reactions. Here S is the invariant pi minus gamma mass, and one has to extrapolate down to small momentum transfer, where the interaction between the nucleus and the hadronic system is dominated by one photon exchange. By measuring different final states, one can actually test different aspects of the chiral dynamics, means low energy QCD. So if the final state is pi minus gamma, one is dealing with pion Compton scattering, and then one can extract the electromagnetic polarizabilities of the pions. For the pi zero, pi minus final state, one can extract or test the chiral anomaly of QCD. And for the 3 pion final state, so either a additional neutral or charged pair, one has, in a sense, pi-pi scattering in an electromagnetic environment, and also tests what is known about pi-pi scattering. So here in this formula, in this expression, you see the two-loop result for the pion polarizabilities in two-loop order. Yeah, you will say it's not a prediction. Yeah, this is correct in a sense, because at leading order, one has a combination of parameters, L bar 6 minus L bar 5. But due to chiral symmetry, this parameter occurs also in the radiative pion decay. It determines the axial to vector coupling ratio. Well, that's the prediction, 5.7 plus minus 1 in this unit. And Compass has measured this, extracted it from their cross section, and finds a result which is in good agreement with the chiral prediction. And here on this figure, you see how what is the effect of the pion polarizability difference. It is this deviation of this cross-section ratio from 1 with increasing X gamma, which is the ratio of the outgoing photon energy to the beam energy. And this X gamma is related, X gamma in the lab is related to the angular dependence in the center of mass frame. The analysis of these data includes, beyond the polarizabilities, various corrections, which are all small, a chiral pion loop correction, so which comes from photons coupling to a pion loop around the pion, QED radiative corrections, and even isospin breaking effect. But most important is, this Compass result is for the first time in agreement with the chiral prediction, whereas the earlier results from Mainz and Serpukhov gave results which differed by factors 2 or 3, and which caused really a problem. The chiral anomaly is tested through this process, pi minus gamma to pi minus pi 0. Here you see the form of the amplitude. Yeah, and it's anomalous because there occurs this Levi-Civita tensor. In this figure, you see how the cross-section develops order by order, 3 plus loops, plus short distance, low energy constants, all nothing. The really dominant feature here is the rho meson. It must be included. Yeah, and this here is still a model dependent inclusion, but it's essential. One can actually go beyond this modeling of the rho contribution by using a dispersive representation of this pi gamma to 2 pi amplitude, which has as the only input pion p wave phase shift. So this is the work of Hofe-Richter et al. So to sketch briefly how it's done. So the amplitude is decomposed like that in this f function, and for the f function, one writes down a twice subtracted dispersion relation, where the imaginary part is determined by f and this pi p wave phase shift delta 1, 1. Then there is one subtraction constant, this c. This c has to be fitted to the data. So, because C determines in the end the height of this total cross section from threshold over the rho region and mapped to the chiral representation. And this way F3 pi can be extracted. So to say it in one word, here there is good theory waiting for good data. And actually recently the same theoretical analysis has been extended to k minus gamma to pi pi by Bastian Kubis in Bonn. And this is actually one of the perspectives for COMPASS. Lastly, the pi gamma to 3 pion process. As you can see from the graphs, this is pi pi interaction in the electromagnetic environment. Here is a leading order result where you see again that the cross section involves the pi pi interaction. That's this blue part of the formula. Of course, one wants to know how accurate it is, and this has been done in a recent work, and this is the outcome for the 3 pion final state with only charged pions. The chiral corrections are relatively small. For comparison, you see the result from COMPASS, the 2004 data, and one finds nice agreement between the theory prediction and the measurement. And this agreement does not happen only at the level of the total cross-section, which you see here, but there is an agreement on the level of the full 5-dimensional space distribution. This means all the angular correlation and energy dependencies in the final state are in such a way as theory predicts. For the 3 pion state, final state with 2 neutrons, chiral corrections are more substantially. And there are preliminary data from COMPASS which confirm this, but this should not be shown here. With that, I close my part and hand over to Stefan.
Yeah, thank you very much, Norbert, for this first part of this presentation, and thanks again to the organizers to have Norbert and me sort of prominently here as the first speaker. Now let me say a couple of words to the experiments, and I will mostly restrict myself to the coupling of mesons to photons, which was introduced already by Norbert. And Norbert already pointed out the issue on the chiral anomaly, so the chiral anomaly appears, as Norbert said, in 2 processes. First, in the ordinary pi0 decay, and in the transition of the photon to 3 charged pions. And so we basically have the pion decay constant, which appears, and in this process, which actually couples a photon to 3 pions, this obviously comes in 3 times, and it's called F3 pi. And this is a cross-section for the invariant mass of the final system, of the pi minus pi zero system. And this is the cross section, and the dotted curves are the calculations with and without the contribution of the rho, namely the p wave. Now, how does one measure this? Well, Norbert already mentioned Primakov reactions are the thing to do. If you want to involve pions and photons, you either have photons in the final state or you have them in initial state. We use the photons, quasi-real photons, as a target. We get them from the Coulomb field of a heavy nucleus, and we do what's called Primakov scattering, which a cross-section which scales proportional to Z. So you need large Z. Very high Z, of course, which you would normally use for lead, have a disadvantage because you get corrections, you get screening, and in particular, from the experimental point of view, you get multiple scattering and you get conversions. So at the end, you have to settle for something which is intermediately heavy, and this is nickel. So what the reactions of COMPASS were pi minus nickel with, for example, for the polarizability measurement with the pion and the photon, or for the measurement of the anomaly, you have pi minus and pi zero at the final end. So what you have to do is, in order to avoid strong interaction, you have to do basic experiment at glazing incidence, which means very forward, and you have to separate the photon interaction from Pomeron exchange or any other strong interaction exchanges, which means you have to go almost in beam direction, and you need excellent angular resolution in order to separate the photon-related processes to the strong interaction-related processes. And just to give you a number, you need angular resolutions in the order of 30 microradian, and this was achieved in COMPASS with the setup shown above. Now, let's say a few preliminary results. That's the advantage of me being involved in analysis. I can show it. Norbert cannot yet show it, but hopefully soon. There's this nice work by Hofrichter, Kubis, and colleagues, and they did the calculation, which was shown. The results, preliminary results, which we have, are shown here. So this is the mass of the pi minus pi zero. This is the cross section, and now in arbitrary units, and that is particularly what is preliminary, namely the scaling of the cross section. What you see here is a little here. The fact that you have cross section at all at very small masses, that's the Calver anomaly. Because without the Calver anomaly, you should not have the production of pi minus pi zero at very small masses. So this basically is something which is sensitive to the Calver anomaly. Then you have sort of the kaon decay, which has nothing to do with this, but it's a background which you cannot avoid. Then you have the P wave, which is a rho. But then you have both. You have the S wave and the P wave. You have interferences, which gives you sensitivity to the Calver anomaly, also in the rho peak. So what you do is you do a fit of this spectrum, and then you determine basically two free parameters. One is the Calver anomaly, and the other one is a coupling of the rho, which is pi minus pi zero, to the photon. So two free parameters. And this is the first attempt of such a fit. And you see excellent agreement with just two parameters. But you already see one issue here, namely at very small masses, you have underlying strong interaction effects, which seemingly yet have not been estimated correctly, and which is work to be done in the next months, together with the absolute normalization, which is not easy because when we started out COMPASS, we didn't think of absolute normalizations. And so we have to basically do a bootstrapping method, and then you always fall into traps and pits. And this is something which is presently being resolved. As a shortcut, we have a beam of pions and kaons. These experiments were done with pions. We know the ratio of kaons to pions. We can measure how many kaons we see by looking at the kaon decay. And from this, we can estimate the number of pions incident, and we get the luminosity. So this is something which is a very tedious process, already worked on since more than a year. So this final state, pi minus pi zero, offers more than the Calver anomaly and the rho. If you look at the full mass spectrum, you see the rho, but you also see intensity at higher masses. This is the mass of the rho, 770. But here you are about 1.67 GeV, which is the rho 3. And actually, if you do an angular analysis of the spectrum, you can separate spin 1 and spin 3, and you can actually determine the radiative coupling of the rho 3 at the same time, which is very nice. Now, I said the chiral anomaly is connected to the pi0 lifetime, and this has recently been measured at JLab. They also use Primakov, but they didn't have a pion beam. They have a photon beam. So the reaction is photon plus a virtual photon from the Coulomb field of a heavy nucleus, leading to pi0, giving 2 photons. And there's a very definite prediction, of course, calculation from theory, which tells you that the radiative width, which is the full width of the pi0, is basically 7.7 electron volt with a very small error here, uncertainty connected to it. Now, it was measured at JLab with the Prime X experiment. You have an incoming photon from a tagged photon beam. You have a heavy target, you produce a pi0. So pi0 immediately decays into 2 photons, and you resolve the 2 photons in an electromagnetic calorimeter. And just like with compass, you have to separate the Primakov region from the other regions, which means you have to do a very fine angular distribution of the final state. And that is what Prime X did. You see here the production angle of the pi0, basically reconstructed from the 2 photons. This is a differential cross-section, 2 times the same figure, once for target, which has low Z, once for target, which has higher Z, carbon and silicon. And you see at very small angles, that is the Primakov region, and you extract the intensity from this peak in order to extract the lifetime of the pi0, basically the coupling strength of the pi0, and you see the new value agrees very nicely again with theory calculations. I think another very nice results for the theory calculation and for experiment together. Now let's come a little bit to the kaons, briefly mentioned by Norbert already. With kaons, you can measure the kaon polarizability. You can basically repeat most of the experiments which we did with pions. You can scatter again by Primakov and produce k pi pi in charge and neutral version. And you can also do an experiment with k minus, and you scatter off a virtual pion, and you have a k pi in the final state. Now, the goals of these experiments is to determine the k pi scattering lengths similar to the pi pi. You get access to k pi resonances as introduced by Norbert for the sigma, and you get the radiative width of the various k pi resonances. You get access to the chiral anomaly for kaons, and here you have, of course, SU3 symmetry breaking, and there's a dispersive analysis for this prepared by Bastian Kubis. You get access to the vector form factor for the kaon. For the kaon decays, it's the radiative kaon decay, so semi-electronic in a way with a photon in the final state. This corresponds basically to the pi0 decay into 2 photons, and you get this value out here from this reaction as well. The corrections typically are larger than for the pions, just owing to the larger strange quark mass. Now, interesting, of course, is the k pi S wave. And the question is, how do you measure it? Because there's no direct pion target. And there are 2 ways you can do it. You perform scattering experiment, and so use basically the pion cloud as a virtual pion target. Then you hope that the pion exchange dominates at the pion pole. Now the trouble is in scattering, elastic scattering, you measure at negative t, the pion pole is at positive t. So you try to go down into t as small as possible, and then use theory to extrapolate to the pion pole, and thereby then you get the contribution of basically k pi elastic scattering. It's theoretically complex. It was done by the last experiment at SLAC and will be done by the K-long beam experiment at JLab, which has recently been approved. A second way how to do it is to extract the chi pi S wave from decays using what's called the Watson theory. So you can use weak decays, for example, the weak decay of the D meson goes to k pi pi, and then you analyze the k pi subsystem, or with something which is even cleaner, you use tau decays into k pi and to neutrino. And then you have k pi basically from threshold to any value you want, and that's very nice. Trouble, you can't reconstruct the neutrino, so you cannot reconstruct the full decay kinematics. Or you use strong decays, which is any excited k star goes to k pi pi. This is being done by Compass. Or you use done by best J psi decay into k star, and again a k pi, and you analyze the k pi. Now, just give you an example. Sorry, this didn't work here. The example is done by Cleo. They use Dales plot analysis, or by Bell. They did the analysis of the k pi. The trouble is they analyze the p wave and the s wave at the same time. it turned out, as we had shown recently, that if you do this, there exist ambiguities, unrecognized ambiguity until that time. So if you analyze P wave and S wave at the same time, you get correlated effects. And so this casts some doubt on the quality of the extraction of the K-pi S wave. Now, this is the present situation on the K-pi S wave. You see it's about, well, it's called K700 or kappa. It sits around 670 MeV with a width of 300, very similar to the values. Half the mass is the width to what we have seen with the sigma. Now, we plan to basically reuse the decay of tau goes to K-pi on neutrinos, and we perform a PWA. We developed a new technology, and we analyze the tau pair simultaneously. One decay goes to K-pi neutrino, the other one goes to 3-pi. Well, I missed the neutrino here. And this way you can basically reconstruct the kinematics of the decaying tau, and you can actually do a partial wave analysis.
Stefan, how many slides?
Or we do it in K-pi 5 final states from K stars. And I don't only demonstrate that this works very nicely with the P wave. We haven't done this on the S wave yet, but for the P wave, we just look at the K-pi P wave, and that is the result. Imaginary part, real part, you see a beautiful argon diagram which corresponds to the K star. This is a mass of the K-pi system, and you see the K star very, very purely. That's only the P wave, there's nothing else beyond. And so we can repeat the whole thing with the S wave, and we hope that we also, using real and imaginary part extracted from this, get the kappa. Last just thing to mention is, of course, chiral, the symmetry breaking leads to the mass splitting of the different multiplets of different parity, the rho and the A1s. And what you would expect, that if chiral symmetry is restored, like in the quark-gluon plasma, then this mass splitting may disappear. This is shown here. There's a temperature shown, and this is a mass splitting between A1 and rho. And once you arrive at 150 MeV in the quark-gluon plasma, then these masses should basically align. And one idea is to perform a partial wave analysis using Alice data, different type of collisions, and you see whether the mass of the A1 and the mass of the rho get closer if you go to high temperature. Technically very difficult, but maybe doable. So I basically like to conclude, and I think it has been shown that low energy meson dynamics is very nicely described by chiral perturbation theory, and the experiments, and numerous of those, address the key observables, either have already or will do so. The precision experiments allow to determine the low energy constant of an effective theory, which then at the end allows a universal description of QCD at low energies. Now, there is an extension to the strength sector, which is also one of the topics for the AMBER proposal. Partial wave techniques are important to extract the S wave and to signal out Primakov processes. And one important thing to be done in the future is to check for the parity doubling in the hot medium. So with this, I'd like to conclude. Thank you very much for the invitation. Thanks, Norbert, for the first part of this talk.
Yeah, thanks, Norbert and Stefan, for these nice talks. We have run a little bit out of time, so maybe there are one or two short questions. If you want to ask a question, please use the raise hand feature. So I see Oleg has raised his hand. Please, Oleg, go ahead.
Yes, Stefan and Norbert, thanks a lot for a very nice talk. You are aware that we are right away scrutinizing the issue of emergence of hadron mass in view of forthcoming new activity here at CERN, quoted already by Stefan, AMBER experiment. I wonder whether we can expect to have an insight from chiral perturbation theory on this issue, on basically why this huge difference between pi and proton mass, even though these are two quantum dynamics rather similar objects.
Okay, the chiral perturbation theory cannot fully answer this question. It only says, yeah, the pion is special because it's a pseudo-Goldstone boson. Its mass is small because it hinges on the finite non-vanishing quark mass. from the chiral theory point of view, all the other masses arise from non-perturbative QCD dynamics, spontaneous chiral symmetry breaking. Yeah.
Okay.
That's my answer.
Thank you.
It cannot, chiral perturbations in the effective fields, it cannot fully answer this.
Okay, thanks. There's a second question by Bernard Molino. Bernard, we cannot hear you, unfortunately.
Hello.
Ah, yes, now, please go ahead.
I have one question to Stefan. On the, I can't tag along the slides, but I think the title was Model-Free Analysis of Hadronic Decays. Could you go to that slide, please? Yeah, just, yeah, this one.
I'm sorry, I have some, there's an overlay which didn't work for the PDF, but yeah.
Okay, thank you very much. I just wanted to know, here I can see the this data shows mass, just moderate mass from 6050 to 850 MeV. And as we go to higher mass, we see these large fluctuations occurring. Maybe this is not good for this data. But then below 750 MeV, I think we see very good data. My question is, what happens when you go below 650 MeV?
Well, I think this, what we see here is really the extraction of these pole parameters, either done by experiment, partly done with Bry-Wigners, or done very elegantly with a lot of work from theory using dispersion relations, Roy-Steiner equations. So the two red points, I think, but the theorists are the only ones which are taken seriously, because the other ones are done by simplistic experimental way. Now, this is not the mass distribution. This is really the extraction of the pole parameter for the k-pi. Now, the mass distribution, of course, now let me get a background slide here, a backup slide. So this is what you have if you do elastic scattering. If you do elastic scattering of k-pi, you basically scatter off the virtual pion. So you have the pion in the final state. This is the mass, or square root of s. Obviously, you come to threshold, which is k-pi. This is the threshold. These are the data from SLAC, the famous LUST data. This is the projected data from JLab. This is what you get in mass too. So, of course, obviously, you cannot go lower because it's the threshold mass. And so what, however, of course, JLab has to do is they have to measure the spectrum at various t and extrapolate the, to t equals m pi squared. Now, if we do it from decays, like d decays, and from kaon decays, we actually can go down basic to threshold here. There is, since there are 3 body decays, let it be also the tau, you really get down to threshold. But what you have to do is you have to measure the phases. That is what is important. And so what Clio and Focus and also Best have done is they extracted the k-pi phases and assumed widths, assuming basically Bry-Wigner from a Dulles plot analysis. And so what COMPASS intends to do is you have the complete spectrum and you separate out the quantum numbers. Basically, you see the complex amplitude, real and the imaginary part, and you fit it basically separated without having to do a complex Dulles plot fit. And you can do this if you're clever without any of the ambiguities which I just briefly mentioned, which, however, govern these type of analysis previously.
All right, thank you very much.
Okay, so I think we are running a little bit out of time. So nevertheless, thank you a lot, Stefan and Norbert, for this nice talk. The next one will be by Bertram Kopf, and this will be an overview about light meson spectroscopy. Bertram, are you there? I see you are connected.
Yeah, can you see me and can you hear me?
Yes, we can hear you loud and clear.
Then I try to share my talk.
Yes, correct. Stefan probably needs to unshare.
Then I will try it.
Well, now you should be able to share.
Can you?
Yeah, we see your screen.
Can you see it?
Yes.
So how can I?
Probably would be good to go to full screen or something.
Full screen, yes. So is it?
Oh, we just see a black screen. Probably you first have to go to full screen and then share the screen.
Okay, then
and share first and then go to full screen and then share again.
It's at the moment it's confused. Oh, I don't see my
you lost
anymore. So there's a technical problem at the moment. Let's no. Oh, okay. No. Oh, sorry. It's there. So now can you see it?
Oh, great. Good. Perfect.
Okay, sorry for the delay.
Let's do that.
But it's okay. But I can't, yeah. So, okay. First of all, I would like to thank the organizers for inviting me and for giving me the possibility to talk about light meson spectroscopy. And I will start with an introduction before I will then summarize the results which have been obtained in the past. And here I would like to focus on the scalar, pseudoscalar, and tensor resonances. And then I will come to some results which have been recently observed. And here my focus is on the spin exotic 1 minus plus hybrid candidate pi 1 1600. And then I will also summarize our studies, which we did during the last 2 years, roughly, a couple of channel analysis of with antiproton-proton data together with pi-pi scattering data. And then I will briefly summarize perspectives in terms of new data samples and experiments. As you know, the light mesons are bound states consisting of up, down, and strange quarks. And the states cover the non-perturbative QCD regime, as you can see here in this figure. And due to this fact, the description is very challenging, and one has to make use of lattice calculations, for example, or phenomenological models. But also from the experimental side, it is also very challenging because the observation and the measurements of the resonance properties are difficult due to the fact that there are many overlapping resonances existing with the same quantum numbers, and there are also a lot of different decay channels. The quark model was or is very successful for the classification of the mesons. So a quark-antiquark pair can be classified by the isospin, G parity, spin parity, and C parity, which is determined by the isospin itself, by the orientation of the spins and the orbital of the quark spins and the orbital angular momentum. And based on this, one can find possible JPC configurations, as you can see here. And there are also quantum number combinations forbidden for such conventional QQ bar mesons. In addition, the quark model provides also a scheme to group the QQ bar mesons in SU3 nonads. Here you can see two different nonads where one can really predict, one could predict states and could classify it in this scheme. And here you can see the nonads of the ground states for the pseudoscalar and vector mesons. In addition to this normal QQ bar mesons, also the QCD predicts exotic states which can be grouped in three categories, which are, for example, hybrids, which are QQ bar states with exotic gluonic degrees of freedom. Glue balls, which are hadrons without any valence quark content, so the gluon itself are the content of this states. And multi-quark states, which are, for example, tetraquark states, which are tightly bound QQ bar states, or molecules, which are loosely bound pair of mesons. And for such exotic states, also quantum numbers are possible, which are forbidden for conventional QQ bar states. So if you observe such states, then it is an unambiguous signature for such exotic states. Here you can see the light meson spectrum. And as you can see, this is a very rich spectrum. And of course, there are a lot of states which need some confirmation. This is not up to date. This is here a sketch of the PDG from 2015. But you can also see candidates already with exotic quantum numbers, 1- here in the right region. But to conclude this here, there are a lot of challenges, because here one can also directly see many overlapping resonances with the same quantum numbers. And also, due to this fact, the distinction between conventional QQ bar mesons and exotics are very difficult. And therefore, it is very important to get a proper access to the resonance parameters and also to the inner structure. And how to do this and how to get access to such an inner structure. So one important point is really the characteristics of the production process. For example, gamma-induced processes include QED effects, and this can be calculated in a very precise way, and this gives direct insight to the inner structure. And in addition, exotics, for example, with gluonic degrees of freedom, should mainly produced in gluon-rich environments like radiative J-psi decays, like central production, or also antiproton-proton annihilation, as you can see here in the graphs which are shown here. And on the other hand, exotics should couple weakly to gamma-induced processes like gamma-gamma fusion, for example. And in addition, also the characteristics of the decay pattern are very important. Glue balls, for example, should decay flavor blind, more or less, and molecules should decay into meson pairs close to threshold. Here you can see some lattice QCD calculations for glue balls and hybrids. So the lightest glue ball with exotic quantum numbers is above 4 GeV over C square. That means this is beyond the mass range of the light mesons. But there are also glue balls expecting in the light meson mass range with non-exotic quantum numbers like 0++, 0-, and 2++. And for hybrids, the situation is a bit different. So the lightest hybrid is expected to be below 2 GeV with an exotic quantum number 1-+. Okay, then I will try to summarize the status of the 0++ states. So there are a lot of resonances observed in the light mass meson region. And there are really too many to fit to the ground state nonads. As you can see here, these are the most prominent states which have been found. And one possible explanation is that the F01370, the F01500, and 1710 are mixtures between conventional QQ bar states and glue balls. And especially this F0 1500 and 1710 are candidates with large gluonic content because they are strongly produced in gluon-rich processes and are also strongly suppressed in gamma-gamma fusion. As you can see, here are 3 examples. For example, measurements from crystal barrier experiment, P-by-P annihilation, then radiative decay, where a lot of strong contributions of the F0 1500 and 1710 have been found. And also gamma-gamma fusion, where this is the 2 states are more or less missing. Okay, there are various scenarios existing for the description of this mixture between the configuration with up and down quarks, with the configuration with strange quarks, and with the configuration of glue balls. Here you can see 2 different results, which are really results in contradiction, more or less. So the result is not in agreement to each other. And the result is here especially based on the observation of the production and decay strengths. And this is really the challenging part, because this could not be determined so properly, especially for these resonances, because the challenge is here really a proper description of a dynamics above the KK bar threshold, where especially these 3 resonances are appearing. So to conclude this is one needs in principle more and accurate measurements and also more sophisticated analysis, in particular in the region above the KK bar threshold for the 0++ states. Then a few words to the 0- states. Also here many pseudoscalar resonances have been observed. And the eta 1405 is favored to be the 0- glue ball, because it is strongly produced in radiative jet psi decays, and it has also been seen in P-by-P annihilation, as you can see here in these histograms. And in addition, it also weakly couples to gamma-gamma. And based on this scenario, the eta 1295 and the eta 1475 could be then explained as the radial excitations of the ground state members eta and eta prime. But the life is not so easy, because this eta 1405 has not been seen in central production, for example, which is then very strange. And also the lattice QCD predicts the lowest glue ball, 0- glue ball above 2 GeV. And in addition, from the experimental side, it is also not clear whether this eta 1295 exists at all, and whether the eta 1405 and the eta 1475 are 2 different states. There are also a lot of good arguments that this is originated from 1 state only. Then a few words to the 0++ states. So based on the quark model, there should be existing 2 isoscalar nonads. And this results in, more or less roughly 10 or more conventional QQ bar states, which should exist in the light meson sector. But the knowledge, especially above the P-by-P threshold, is so far poor, because, for example, all P-by-P measurements at Lear cover only the mass region up to the P-by-P threshold. And in addition, the lightest tensor glue ball is also predicted in this mass range between 2 and 2.4 GeV. But for this, there are at least some hints. For example, here I show the reaction pion proton to phi neutron, because a glue ball should decay strongly in phi. And here one could see a unexpected large cross-section for 3 tensor mesons. And this is at least a hint that there could be tensor glue ball. Okay, to summarize this, concerning the light meson spectroscopy, so over the last decades, or roughly 30 years, a significant amount of data has been analyzed, but there are still unresolved questions. So, okay, there are a lot of things which are known, but there are really still unresolved questions due to the fact that there are also a lot of broad overlapping resonances, that it is possible that conventional QQ bar mesons can mix with exotic states. And due to this fact, a complete and unambiguous knowledge of all QQ bar multiplets are needed. And yeah, one problem was that many resonance properties have been obtained from single channel analysis with Breit-Wigner parameterizations. And it would be better, for example, to perform more multi-channel analysis with sophisticated approaches where the unitarity and analyticity are fulfilled by, for example, combining different data sets with different decay and production modes. Yeah, as I already mentioned, the description of the dynamical function is very important, and these Breit-Wigner functions are widely used, and this is a good approximation for isolated resonances which are appearing in, for example, only in one single channel. But the Breit-Wigner function is also, the description, it depends also on, or the resonance parameters are depending on the production mechanism itself. And therefore, one needs more sophisticated descriptions because the resonances are in general decaying to multiple channels, also several resonances appearing in the same channel. And also when some resonances are located at a threshold somewhere, then this results also in a distortion of the Breit-Wigner-like line shape. And to conclude this, it would be good to perform fits with approaches with an adequate consideration of the unitarity and analyticity. For example, the K matrix is one method, N over D method, or the two potential decomposition. Now I will switch to some new analysis which go exactly in this direction. So first of all, I would like to present an analysis from the JPAR group with compass data. And they performed a couple channel analysis of the 1- wave and 2+ wave in the reaction pion proton to pion eta and eta prime with a spectator proton. And here there are in principle two hybrid candidates seen, one at 1.4 GeV in the channel pi eta, which is also listed in the PDG, as you can see here in this first left histogram. And the other one at 1.6 GeV, which has been seen in pi eta prime, which you can see in the right histogram. The analysis has been done by considering here these mass shapes, as you can see here, and also the phase shift between the 1- and the 2++ phase. Okay, in addition, also especially for the 1.6 GeV resonance, this has been seen also in other decay channels. This has not been considered, so the unitarity is not completely fulfilled, but at least this is a two-channel description. And the result is really very, very nice. So here you can see the result of this couple channel fit. And this could be described with only one 1- pole. And you can see that the peak at 1.4 GeV in pi eta and 1.6 GeV in pi eta prime can be described very well. And also all other spectra are in good agreement with the data. Yeah, that's really a very nice result. And this is not possible by performing a fit with Breit-Wigner functions. Then you get really two different resonances in this case. Now I will switch to the partial wave analysis with antiproton-proton data from Crystal Barrel at Lear, which we did during the last 2 years. To remind you, Crystal Barrel was a fixed target experiment at CERN, and it was in operation between 1989 and 1996. During that time, it was more or less a leading P-by-P experiment in the field of the light meson spectroscopy. And the focus was the investigation of antiproton-proton annihilation at rest. And partly also in flight with the highest beam momentum of roughly 2 GeV over C. We did a couple channel analysis of the channels antiproton-proton to pi 0, pi 0 eta, pi 0 eta eta, and k plus k minus pi 0 in flight at a beam momentum of 900 MeV over C, together with pi scattering data. Why did we combine the 3 different P/P channels? The reason is that many A0, A2, F0, and F2 resonances are expected to be seen in these 3 channels. And in addition, then one can really constrain the production amplitudes there, because this has been in common for all the 3 channels. And this has been done with a description of the K matrix. In addition, we have also looked for the spin exotic wave, pi 1, 1400 in the decay to pi eta, which has so far only been seen in P/P data at rest. And therefore, it would be also interesting to search for it in flight data. And why did we take into account the scattering data? So the scattering process itself is only characterized by the elasticity and the phase motion. And this gives really then a very good and easy access to the resonance properties. And for this, we considered the isospin 0s and d wave and the isospin 1 p wave. And this gives really then good constraints for the F0, F2, and rho resonances. Here you can see the fit results for the individual channels. So this is not complete, these are only some examples. But as you can see here, all channels can be described in a very good way, and also the pi scattering data in addition. It was possible to extract more than 50 different resonance properties. I don't want to go here into the detail. This is just a list of all the properties which have been obtained. And to conclude, this is all the properties are more or less within the ballpark of all other measurements, so to say. Another interesting outcome was that we could observe the 1 minus plus wave in the channel antiproton-proton to pi 0 eta, and with a decay into pi 0 eta. And what one can see here is when one compare the phase difference of the pi 1 wave with the A2 wave from this fit in the T matrix, in the scattering matrix, this is really in good agreement with the compass measurement. This is really a very interesting result. So this is no fit to the compass data. This is just a comparison. And as one can see here, the shape of this phase difference is in very, very good agreement. So here the black lines show the results obtained with the P/P fit, and the red arrow bars are the compass data. So this is really in very good agreement. And in addition, we could also determine the pole positions here, which is roughly, the mass is roughly at 1400 MeV. Okay, and due to this nice result, we came to the conclusion to extend this fit and to take also the compass data into account to this coupled channel approach. And here you can see the first results. So this is still under investigation, but as you can see here, one can also achieve really a very, very good description for all data, also with this one pole scenario for the 1 minus plus wave. But again, this is still under investigation. Then I will come to the perspectives and to new expected data and also to new experiments. First of all, I think one important experiment is a GLUX experiment, of course, which is studying already the light meson spectrum up to 3 GeV in the photon production. And one main focus is a search for hybrids. And I think there are a lot of data will be available to clarify, especially the situation concerning the hybrid states in this low mass region, and especially for the 1- hybrids. In addition, I think Bell 2 provides for the light mass spectrum high statistics gamma-gamma data, which can also give new information about gamma-gamma fusion, and also Bell 3 has taken or has recorded a couple, very much J-psi data, so they achieved 10 billion decays so far, and this gives insights, especially for radiative decays. As I already mentioned, this is a gluon-rich process, and this gives new insights in this direction. Yeah, LHCb with B and B sub S decays are also very important and will give really good data. And then there are also some new experiments, for example, the PANDA experiment at FAIR, which will investigate antiproton-proton annihilation in the with the B momentum between 1.5 and 15 GeV over C. The main focus is here on in the charmonium sector and open charm sector, but also here in this light meson mass region, especially here, the PANDA can cover the lack of the data close to and above the P/B threshold, because this is really very important. Another very important and interesting experiment will be the antiproton physics with EMBA or COMPASS++. This will also provide very nice and good data in this direction. And of course, the K-Long facility at JLab, and Igor Strakowski will give a presentation during this workshop here. Okay, to summarize, so many new insights have been gained during the last decades, but there are still many unresolved questions in the light meson region due to the fact that there are many broad and overlapping resonances with the same quantum numbers, that there are also mixtures possible between conventional QQ bar mesons and the exotic states. And therefore, it is very important to get proper access to the inner structure by investigating the different production processes and decay modes. Sophisticated analysis methods are needed in order to extract the properties. And here I show two examples: the JPAG analysis, which was dedicated for the spin exotic 1- wave, and they could explain the peak at 1.4 GeV in the pi eta spectrum and 1.6 GeV in the pi eta prime spectrum with only one pole. And I've presented a couple channel analysis with antiproton-proton data together with pi-pi scattering data. And of course, new experiments and high statistics data are very important to clarify the still unresolved questions in the light meson region. Yeah. That's it, and thank you very much.
Yeah, thank you very much, Bertram, for this very nice overview. Are there questions from the audience? Please use the raise hand button. Bernhard Ketzer wants to ask a question. Please go ahead, Bernhard.
Yeah, hi, Bertram. Thanks for the very nice talk. I have a question concerning the P/B couple channel analysis on the crystal barrel plus the scattering data. So there, you still have a pole at 1.4 GeV. Did I understand this correctly? And is this not in contradiction with the single pole analysis of the COMPASS data?
Okay, in principle, yes, but we are only, for the antiproton-proton data, we have only analyzed here this channel pi eta, so we are only sensitive to this pi eta system. And in the pi eta system, in principle, all measurements show a mass of roughly 1400 MeV. And we explain it, of course, we explain or we describe this pi 1 with a K matrix, and also in addition with a pi eta prime channel, but without any data here. And this is a problem, I think, and therefore we are not completely sensitive to the correct mass. So the data in pi eta prime are really mandatory to fix this mass in a proper way. So this is a result of this P/P analysis together with scheduling data, and I can say that here, by taking into account also the compass data, where we have then also access to this pi eta prime system, then the mass is also shifting, or the pole position to higher masses, between 1500 and 1600 MeV. So I think a couple channel analysis is needed here in order to determine in a proper way this pole, in the case that this pole is really only one pole. So this is also questionable, but one can explain this by one pole. This is, and in this case, both channels are needed.
Okay, thank you.
Yeah, the next question was by Oleg Denisov. Oleg, please go ahead.
Yeah, the question is imagine you have a choice, or you increase your statistics in the pi-induced diffractive scattering by a factor of 10, or you have equal statistics in the Kern-induced diffractive, the same statistic as we have right away for the pi-induced diffractive. What would be your choice?
Good question. So if you look for rare, at least for resonances with lower cross sections, then of course you need higher statistics. This is clear. But I think the most important point is really to combine different data together, as I already mentioned. So to take into account different production processes and different decay modes in one analysis. I think this is the most important point, but of course the statistics is also very important. So it's difficult to answer the question. I think it is also depending on the topics which you are investigating. But of course here for what I already mentioned in for the P/P data, for example, there's really a lack above 2 GeV, and it is needed to have more data in this direction. Yeah.
Okay. The last question by Wolfgang Dünnweber. Wolfgang, please go ahead.
Yeah, hello. Bertram, nice to see the old crystal barrel data popping up again. You seem to see the exotic only in pi0 eta, but of course there's also pi0 eta eta. Do you have an explanation why it seems to be not appearing in eta pi0? Is there an entrance channel selectivity? For instance, the two channels have different isospin. pi0 eta has isospin 0, the other has isospin 1, and isospin is linked to different partial waves. Can you comment on this?
Yeah, this is a very good question, and this is of course difficult to answer. What is the reason for this? But exactly this has been already seen in P/P data at rest at crystal barrel, that the pi1 wave is visible in this channel pi eta with a recall pion, but not with a recall eta. And as you already mentioned, the production process is different in both scenarios. In one case, you have an isospin 1 particle as a recoil particle, and in the other case, it is a eta isospin 0 particle. And maybe this is related to this, but we have to ask theorists for this. But I think this is strongly related to the production process, of course.
Okay, then I think we have to move on. Thanks a lot, Bertram, for this nice presentation. And we come to the last presentation in this session, which is by Christoph Hannert about XYZ state. Christoph, can you share your slides?
Thank you very much.
We can hear you. Very good. Great.
Okay.
Yeah, we see your slides. Great. Go ahead.
Thank you very much. It was for Boris for opening my talk, and thanks for the organizers for the opportunity to talk on the XYZ states. This talk is sort of a continuation from Bertram's presentation, because now I talk about states in the heavy sector in contrast to the light sector, as it was covered in the previous talks, and that this is a very hot topic. You can actually see already from the large number of reviews that were produced in the recent years. Sorry, here on the introductory slide. The title is I will present some thoughts about the XYZ states and beyond, and what this and beyond means should become clear in the course of the talk. Okay, what is the situation? Until 2002, there was a strong belief that the heavy quark sectors, or the quarkonium sector, can be well understood within largely the non-relativistic quark model, or modifications thereof, or improvements thereof in the sense of an effective field theory. There was a Cornell description of from the Cornell potential that described all those states here put in blue very nicely, mostly not only the masses, also the properties. Before 2002, two states, the eta C prime and the HC1P, were not discovered yet, but it was expected that those will be found, and that also above the first open flavor threshold, additional states will be found predicted by the quark model. But in 2003, then the situation changed dramatically, because in 2003, the X3872 was discovered. And it did not fit at all into the predictions from the quark model. It was 100 MeV lighter than the, say, the Cornell model prediction, and also decay properties were very unusual. And in the years shortly after, many additional states were found that did not fit at all into the quark model predictions. They were all above the DD bar threshold. The two states at the time before missing below the DD bar threshold, the eta C prime mentioned before and the HC1P, were both found exactly at the predicted mass, but above the DD bar threshold. There are now many new exotics found. They don't fit into the quark model predictions. They are super numerous in the spirit of what Bertram explained. Most of the new states are in the charmonium sector, but there are also two states in the bottomonium sector, and those are even more special. Those two states were found in the decay Y5S, going to a heavy quarkonium and a pion pair, and they were seen in the invariant mass distribution of the heavy quarkonium and the pion. Therefore, they must contain both simultaneously a heavy quark anti-quark pair, because that appears in the final set and cannot be produced in the decay itself, and it must contain light quarks because they are isovector and they are charged. Therefore, they appear in charged components. Therefore, there must be at least 4 quarks. After this discovery at Bell in the bottomonium sector, analogous states were also found in the charmonium sector. Here I show you data from BEST3 on the ZC3900. It's located very close to the DD star threshold. You see a very nice signal here. And also this one must contain at least 5 quarks. Analogously, also in the baryon sector, in the J-psi proton channel, signals were discovered with beyond 7 sigma signal, and those must be pentaquarks, in analogy to these ones certainly being 4 quark states. Now I can mention for the first time the beyond. There are now even states seen at LHCb in double J-psi. You see the structures here. The experimental analysis delivered that these signals are above 5 sigma, and they must contain at least pairs of charm and a pair of anti-charms. So this is clearly beyond the XYZs, and there's not even a name proposed for those states yet. So we don't know how to call them. Let's call them double J-psi structures for the time being. I will come back to those data later in my presentation. Let me now tell you a little bit about what people suggest those XYZ states are. And one of the most prominent models is the so-called heavy tetraquarks. Here, the structures are thought of being bound states of one diquark with an anti-diquark, where the diquarks are heavy light systems. So this is a picture put forward, for instance, by Mariani in 2005, where the formalisms originally proposed by Jaffe for the light scalars was extended to the charm sector. To account for the phenomenological observations, Mariani et al. Had to propose that the spin-spin interaction only happens within diquark and anti-diquark and not within, not in between the diquarks, which is sort of counterintuitive because spin interactions amongst heavy quarks are heavily suppressed. In order to explain that phenomenology, later they proposed that there might be some well structure here where the diquark is sitting in the one side, the anti-diquark in the other. And this relatively large distance here prevents spin-spin interactions between diquark and anti-diquark. Then later it was proposed that a tensor force is needed, and putting all these things together, one can really write down a mass formula analogously to formulas that were used in atomic physics. You have an L² term, LS term, tensor force, and this is the spin-spin interaction acting only within these diquark, anti-diquark structures. A result of this thing is that there are already many ground states and that each level has both an isovector and an isoscalar state. Now, to illustrate a typical result in the negative parity state, so you see there are 4 vectors needed to fix the parameters in this negative parity sector, when once also the positive parity sector is already fitted. This is now for the additional terms involving angular momentum. And you get many predictions, which are experimentally testable. That's nice. The question remains, however, which states to fit in the vector sector, because there are analyses for here it's BESS3 data shown in J-psi-pi-pi final state, where this structure here is fitted with 2 resonances, then these 2 can go into the analysis here for the spectrum. But there are also explanations for these data that have only 1 resonance. That would mean that this analysis is lacking 1, even in the vector sector. Additional questions are, first of all, are the many threshold proximities that are observed for these new states accidental? Secondly, as I mentioned before, there are many more states predicted than observed. 2 possible explanations for that could be either that this diquark picture, which only includes diquarks in the color 3 bar, is too restrictive. The color 6 is possibly needed as well. That should reduce the number of states claimed by Richard et al. Or Richard Lebbert and his group proposed that maybe the potential needs to be extended by some isospin dependent force. This is still going. The second model that's often quoted is the so-called hadrochammonium or hadroquarkonium in more general terms. There you have a compact heavy QQ bar core in the center surrounded by a light quark cloud. Originally, this was proposed to explain the data for the Y4260 that is a vector state that does not decay to DD bar, but it's seen in J-psi-pi-pi. Therefore, the idea was that the core state simply survives the decay. Later, then there was data seen with strength in the mass range of the Y4260 in the HC-pi-pi final state. A priori, this sounds like a problem for the hadrochammonium picture, since the heavy quark spin symmetry demands the spin of the core to survive the decay, and the HC is a spin 0 state, while the J-psi is spin 1. Therefore, the solution put forward by Lee and Voloshin was that Y4260 and Y4360 could be mixtures of 2 hadrochammonia, one with a spin 0, one with a spin 1 core. And if one thinks that's true, one finds that this spin 1 core, the 1 minus CC bar, must be accompanied by a 0 plus plus QQ bar. The 1 plus minus CC bar core, this one has the heavy quark spins in spin 0. the 1 comes from the p wave, must be accompanied by a 0 minus plus QQ bar surrounding. And then Leon Voloshin proposed that for this Y4260, Y4360 admixture, the core in the vector state must be predominantly zip psi prime. Then one can predict here spin partners by simply replacing the QQ bars, the heavy QQ bars, by their spin partner states. Therefore, the psi prime gets replaced by the eta C prime, which is a spin partner of the psi prime, the HC by the chi CJs. And one can then predict 4 additional new states with a special feature that there should be a light eta C at 4140 that does not decay to D star D bar, right? Analogously as the Y4260 does not decay to DD bar. Finally, I come to the hadronic molecules. I think here we don't need to discuss whether bound states of color neutral objects do exist. They do exist as light nuclei. Examples are, for instance, proton and neutron, or hypertriton, which can be viewed as a bound state of a lambda and a deuteron. And all those states are located typically close to the relevant thresholds. So that many exotics are found close to thresholds. It comes in the molecular picture natural. Binding energies are usually small. The deuteron has a binding energy of 2.2 MeV, the hypertriton of 130 keV. Another quantity that's very relevant in this context, that should become clear later, is the so-called binding momentum. That is the typical momentum inside of the constituents inside a molecule. It's calculated as square root of 2 times the reduced mass times binding energy. And this binding momentum for the deuteron is 40 MeV. And for the hypertriton, it's 26 MeV. Weinberg showed already in the 1960s that observables can be directly related to the probability to find the molecular component in the bound state wave function, which is very nice if one can basically measure how molecular a state is. Therefore, what he showed is that this compositeness, the mentioned probability, is directly proportional to the coupling of the given state to the continuum up to known prefactors. So what appears here is again the reduced mass of the constituents. It appears this binding momentum, the mass of the bound state, and the compositeness XW. And XW can then also be translated from this equation here directly to scattering length and effective range, which is again given only in terms of the binding momentum and the compositeness. One sees, for instance, that the scattering length goes to just 1 over gamma when the state is a pure molecule. Okay. The question therefore is, I think there's a sign error here, should be a plus. The question therefore is, are there mesonic molecules? Okay, not because it's there are baryonic molecules, we know. The general considerations about this, first of all, these constituents must be very narrow, simply because the constituents should not have decayed before they can actually hadronize and form bound states. Therefore, the constituents that we have at our disposal to form exotic states in the germanium sector are the ground state D and D star, the 0 minus and the 1 minus, and the narrow D1 and D2, both having a width of 30 and 50 MeV respectively. There's also a D0, the scalar, and the axial vector D1. Again, these are spin partners, but they have 300 MeV width, therefore they are way too broad to form bound states. Okay, now without any calculation, one can already look what one can make, what kind of general statements one can do. Well, first of all, as all bound states should be close to thresholds and bound states appear in S wave. First of all, just from the masses of the potential constituents, we can already identify the mass ranges up beyond which we expect these exotics to occur. And this is not just a straight line along the DD bar axis, but what one sees is such a histogram type of thing here. For instance, it nicely explains why Y4260 as the lightest negative parity exotic found so far is about 400 MeV heavier than the X3872, because if the X3872 is a DD star bound state, the Y4260 a D1D bound state, the mass difference between these two guys should be just the mass difference between the two constituents, and that boils down to the mass difference between the D1 and the D star, which is 400 MeV. Moreover, to come to a scalar with negative parity, we have to combine this D1 here with the D star. Therefore, in this molecular scenario, the prediction is that the lightest pseudoscalar is about 100 MeV heavier than the Y4260, in contradistinction to, for instance, what we saw in the Hadron picture, where the lightest pseudoscalar was 100 MeV lighter than the Y4260. Therefore, there are clear experimental signatures that distinguish the different pictures. In order to have a model independent criterion analogous to the Weinberg criterion, which, however, is more generally applicable, we must somehow extend the Weinberg approach. And this is what we did recently to also, for instance, describe virtual states. I should first introduce a little bit of nomenclature. What you see here on the left is the, in the one-channel case, the momentum plane, the complex momentum plane, which here maps on the S plane. Therefore, in momentum, there aren't any cuts. Therefore, this is just one plane. In the energy, there are two planes, the physical Riemann sheet, or sheet 1, and the unphysical Riemann sheet, sheet 2. The upper half in K maps onto the physical sheet, the lower half onto the unphysical sheet. What I want to call a bound state, or what's called a bound state, is a pole in K on the imaginary real axis. No other poles are allowed in the physical sheet, and this maps here in the S plane on, again, on a pole on the, in this case, it's on the real axis below the lowest threshold. Then a virtual state is a pole on the imaginary K axis, but in the lower half plane on the unphysical sheet. That maps to the second Riemann sheet below threshold on the real axis. And all other poles are called resonances, and they are called then located in the unphysical sheet in the complex plane, as they always have to come in pairs. If you have a pole here, there must be a second one here in the K plane, and in the S plane that maps to, if there is a pole below the real axis, there must be a pole above. Weinberg did his analysis based on the effective range expansion, which I repeat here. Therefore, our extension uses the effective range expansion as well. And as you see, the effective range expansion has a second order polynomial in the denominator. Therefore, it generates two poles. And the location of the poles then can be directly expressed also in the plane A and R, scattering length and effective range. And this is shown here in the right. Therefore, this part here is where the bound states live in the AR plane. Virtual states are this corner up here. And resonances are then below this line R equal to minus A/2. And there's here this dotted line denoting the threshold, because what you can see from this picture here, there could also be poles, resonance poles, which are here located below the threshold. Right? So they would still show up more like virtual states in the data, although they are already resonances. But if these poles move above thresholds, they move above the dotted line here in this AR plane. Okay. There's one more piece of information in the plot, namely this Wigner bound. Therefore, positive effective ranges should not be larger than this Wigner bound, which is basically given by the range of forces, because then causality would be violated. And the fact that no poles are allowed in the complex plane here, or here in the physical sheet, besides on the real axis, this is reflected in the white area here, simply because this white area then shows there shouldn't be any poles there, because that would violate causality. Now, let's come back to the Weinberg original analysis. There, Weinberg showed that for a pure molecule, the scattering length is very large and the effective range is of the order of the range of forces. It's actually typically positive. Therefore, a typical molecule pole would be located here. If we restrict ourselves to just attractive interactions, then for a bound state in the sign conventions that I have, the scattering length is negative, but an attractive force that's too weak to form a bound state has a positive scattering length. So the scattering length must change sign. Therefore, if we ask what happens to the molecule as it becomes unbound, what happens is the effective range will stay at the same range, but the effective range goes through minus infinity. It reappears at plus infinity and ends up here. Therefore, the natural thing as the interaction gets weaker and the system is no longer bound is that a molecule directly turns into a virtual state. On the other hand, Weinberg showed that a compact state has a very small scattering length, but a very large and negative effective range. Therefore, in this AR plot here, the compact state is located here. Now, if I change the scattering length, but leave the effective range almost unchanged, I move from here to here. Therefore, the compact state directly moves to the resonance. It does not go through the virtual state. Therefore, this actually confirms the prejudice that was around since many years anyway, that virtual states are always of molecular nature. But now we have demonstrated that even connecting to this very nice model-independent Weinberg criterion. All these features that I just sketched here can be subsummed in some alternatives. Therefore, before this was X bar W, now I have X bar A for alternative compositeness, which can then be expressed in terms just of A and R in this way. There are other approaches generalizing Weinberg's criterion, but they typically use on-shell factorization and work within a certain representation. This is unnecessary here because the only things that enter the analysis are scattering length and effective range. I can now come back to the double J psi spectrum I showed in the beginning. Here we have to ask, are these tetra quarks or molecules? And I can just apply the method that I just presented to you. But unfortunately, in the mass range covered by this double J psi spectrum, there are many, many thresholds. Therefore, in order to proceed, I must first make some simplifying assumption, which I cannot really justify besides let's see where it ends. And the simplifying assumption is let's restrict ourselves to just double vector channels. Therefore, in addition to J psi, which has the threshold down here, I want to include J psi and psi 2s, and J psi and psi 3770. The two thresholds are actually, interestingly, located very close to the appearing structures. Now we apply two different models. This is on the archive under this number. The first model is just including two channels, J psi, and psi prime, J psi. This is the corresponding threshold, no other. And in the potential then, in order to fit the data, we find we need some energy dependence. This is here. And we have a three-channel problem where in addition, we add into the two already mentioned channels, the psi 3770 J psi channel. The two thresholds are here. The green area is the fitting range, and you see how well the fits work. So for both descriptions can describe the data very nicely. But what does this mean? Well, let's first look at the pole structure, because the underlying pole structure is the entrance door to an understanding. In the two-channel case, which is here in the upper part, we find, in addition, we find two higher up poles. One here. These are the corresponding mirror poles. But we also find a structure very close to the J psi threshold here. In the three-channel case, we have one resonance high up, which is badly determined in mass and width, because as one can see here, this is a residue. A large residue can compensate for a big distance to the threshold. But also here, there's always a pole close to the J psi threshold. Therefore, the two approaches give very different results in the higher energy regime, but both produce poles close to the J psi threshold. What does it now mean if we interpret those pole locations close to the J psi threshold in terms of this extended Weinberg criterion? What we find is that what we find in the two-channel fit is actually consistent with both the structure being either a molecule or a compact state, while in the three-channel fit, we had two different fit minima, which were of similar quality. Both delivered that the J psi state is a pure molecule. Well, therefore the current data doesn't allow one to distinguish, but what one can do to distinguish is, for instance, just measure the psi prime J psi final state. because there the energy dependence of the two cross sections look utterly different. Therefore, up here, these are the two fits from the 3-channel model. Down here is what comes with the, sorry, from the 3 channels, yes, and this is what comes in the 2-channel approach. Therefore, it's a somewhat above 3.9 GeV. The two pictures can be very nicely distinguished. This brings me to my summary slide. What is needed? Well, obviously, we need additional excellent data for the different spin states. I showed you, for instance, that this pseudoscalar state allows us to distinguish between the molecular picture and the hadron-germanium picture. What is the underlying insight is that the amount of spin symmetry violation is very sensitive to the nature of the states, and therefore the more states we know in the heavy quark sector, the more we will learn about the nature. Moreover, we need more refined theory predictions. For instance, what is completely unclear up to now is the role of the regular QQ bar states for the situations where they are allowed to mix in. There are studies that investigate their mixing. There are studies that claim there shouldn't be any. This is completely unresolved yet. Within the molecular picture, we also do not yet fully know what the proper approach is. There are groups that claim that the pion exchange, for instance, should be treated perturbatively. There are groups that treat it non-perturbatively, and the predictions are also different. Maybe we need better data to tell apart which one is on the right track. Thank you very much for your attention.
Yeah, thanks a lot, Christoph. Very nice talk. Are there questions from the audience? I think, Wolfgang, you had probably your hands up still from the last talk. Maybe I have one. In this compositeness criterion, could it also tell apart triangle diagrams? I mean, they were also discussed, at least as a possible explanation for some of these states. Would that be something, or let's say, is that a different concept, or would that be also molecular in some sense?
Well, the triangular, no, that's a different concept. If a structure is really produced from a triangle diagram, it comes from a logarithmic singularity coming from these triangles, and there is no pole. Therefore, if a structure is explained via a triangle diagram, and there are proposals for a few of them, for instance, there's this state Z4430, which is claimed by different groups to be a triangle, then there is simply no state because there is no pole. What we call a state is a pole.
Okay.
And what is done here in this extended Weinberg criterion, working with scattering length and effective range, there's an underlying assumption, namely that there is really a pole and that there is no other singularity nearby besides the threshold and the pole. If there is a triangle singularity nearby, one has an additional small scale, and this picture here breaks down. Therefore, in order to investigate and to better understand whether there is a triangle operative or not, one also needs additional data. But in this case, one needs additional data in the so-called elastic channel, because there is a theorem which is called Schmidt's theorem, which says that in the so-called elastic channel, which is the channel that drives the cut before the particles in the triangle merge to reach the final state, in this channel, a triangle singularity should disappear. Therefore, that is then the experimental test, whether or not such a structure exists.
Okay, thanks a lot. So there was a question by Bernhard Ketzer. Bernhard, please go ahead.
Hi, Christoph. Thanks for the nice summary. I have a question concerning, there were theory, considerations that one could learn about the structure of these states also by looking at their production in different collision systems. For example, proton-proton versus proton-nucleus or nucleus-nucleus. Do you think that this is a viable way of, or would be a viable way of approaching the structure, or not?
To be honest, I don't know. Therefore, that's the most sound statement I can tell. Intuitively, I'm a little skeptical. The underlying ideas here in these kinds of analyses that I was presenting are effective field theories. Effective field theories, in the spirit that Norbert introduced them in the very beginning, really take into account all small scales fully dynamically, and all heavy scales are integrated out. Therefore, if we have a mechanism where I have to simultaneously include also the heavy scales, like in violent heavy ion collisions, for instance, or in also in proton-proton collisions, central collisions, in principle, I get a problem in how to deal with the different scales, at least within this formalism. And this fact is reflected, for instance, in this ongoing debate on how to properly treat, say, the X3872 production in large PT reactions. Because there's one group that says the observed rate clearly proves that the X3872 must be a compact state. And there's another group which claims that this is incorrect because this is driven by short-range dynamics. And one can easily explain, even within this molecular picture, for instance, the production rate of the X3872, because one anyway has a leading order counterterm. Therefore, at the moment, our level of understanding isn't there to really give a definite answer to your question, and I'm skeptical that we will get there soonish.
Okay, thank you.
You're welcome.
Okay. I don't see any other hands. So let's thank all the speakers of this session. And yeah, we have a coffee break now. Probably we are a little bit over time. Probably we will shift the coffee break a little bit. I'm not sure the organizers, what time do we agree upon?
Yes, I think we have to keep the schedule. So I propose 11:15.
Okay, very good. Okay, so enjoy your coffee. And see you at 11:15. Thanks a lot.
Alessandro, if you are ready to start, I would invite you to speak about the 3D nucleon structure, please.
Here it is. Can you see the slides?
Yes.
Okay, so it is, as usual, a pleasure to be participating into the IWHSS workshop. Unfortunately, this time not in person. I regret it a lot. So I was given the task of giving a sort of introductory talk on 3D nucleon structure. And as an excuse, I had a little time to prepare it. So I apologize if I miss mentioning some important things. Of course, we are talking about a 3D structure, but in reality, if we want to be more general, we should be talking about 5-dimensional structure, because if we start from linear distributions, they are functions of BT, NKT, and X. So they are 5-dimensional. At the moment, we don't have access to these objects directly. So we reduce the dimensionality and we talk about TMDs being the momentum space 3D distributions. So it's a function of longitudinal momentum and transverse momentum. And impact parameter distributions, which are the Fourier transform of GPDs. They are 3-dimensional in the combined momentum, longitudinal momentum, and impact parameter space. And we also know that if we further integrate 2 of the 3 dimensions, we are left with PDFs or form factors in their Fourier transforms. So in this talk, I will speak mainly about TMDs because of the relevance to the COMPASS program at the moment. And I will say, unfortunately, only a few things on the GPD side. I hope you apologize me. So longitudinal momentum and transverse momentum, they are encoded. The distribution of quarks in these variables is encoded in transverse momentum distributions, 3D objects. I hope I don't need to make an introduction anymore to this distinguished audience of the COMPASS collaboration, and I will go straight to one of the most recent results. So this is the distribution of up and down quarks in the proton as a function of transverse and longitudinal momentum. Here you see different slices at different axes, up quarks, down quarks, and you see also the effect of polarization. The polarized proton now is polarized vertically, and you see the small shift of the up-down to the right and of the down quark to the left. This is due to the Siever's effect. Now, this is, we have been doing these images using models or using some simplified fits. In my opinion, this is the first time we can really say that we have obtained these objects completely from data, because you need 2 main ingredients to do this. You need the unpolarized distribution in transverse momentum space and the Siever's function. And there was no work up to now that had these 2 ingredients consistently extracted. So I think this is a tremendous achievement. Unfortunately, the referees of PRL did not share my opinion, and I think they missed the opportunity of increasing their impact factor. But okay, so we are trying to get it published. And let me say that 75% of the data to perform this kind of extraction come from COMPASS, both from the unpolarized multiplicity and for the Siever's effect. So it's one of the, in my opinion, big achievements of the last year. Let me mention, of course, also impact parameter distributions, which are the Fourier transforms of GPDs. They are also 3-dimensionals. Now, there is the longitudinal momentum and the transverse position or impact parameter. And also here we are doing steps forward. This is not so new anymore, but still it is beautiful. So this is again a kind of image of the 3D structure in terms of longitudinal momentum and impact parameter in this case. And you see here the effect of the unpolarized distribution, and here it's the longitudinal, the effect of longitudinal polarization. For the moment, there is not yet the effect of transverse polarization. Here, COMPASS is not playing a big role yet, because, as you know very well, you have been collecting data, analysis will come, and I'm sure that in the next years, COMPASS will also play a very, very important role in the reconstruction of these densities. This is an example of one of your of the publications of the collaboration of 2018, and here the red point is the one obtained by COMPASS, and it is directly related to the width of the distributions I showed you before at smallish values of Higgs. So unfortunately, I will not say much more about this topic. I'm not an expert in this field, and as I said, I have the good excuse that COMPASS for the moment is not playing a big role in this business. Why? So those were maps of the nucleons in a transmomental space, simple parameter space, but they are nice. I think they are very nice, but still, why do we do it? Why do we map the nucleon? What do we want to know and understand? Well, first of all, we want to know if these maps are consistent with QCD. So we should be able to see if there are predictions based on QCD and see if our maps agree with these predictions. And secondly, we can use these maps to make further predictions, in other environments for experiments that maybe do not have as a goal the reconstruction of the structure of the proton, but they need the structure of the proton to make predictions and to maybe look for physics beyond the standard model. So as an example of comparing QCD predictions with extractions, let's take really a very basic and famous one. This is the total longitudinal momentum carried by the quarks. And we have both experimental extractions, phenomenological extractions, global fits of collinear PDFs, and lattice predictions, so really based on the QCD Lagrange. And you see that the agreement is very good for some quantities. For instance, the isovector combination is very well compatible between fits and lattice QCD. But even in this case, there are some discrepancies. For instance, the up quark momentum is not really the same for the extractions or for lattice, even if it is compatible within errors. And look at the gluons. The gluons is really, for the moment, being off. So it's fair to say that, yes, there is a fair agreement, but not perfect. There's a lot of work to do, even in the case of this is one-dimensional structure. So imagine what we can do with the 3D structure. Even more, those were, this was the previous one was a Mellin moment of the collinear PDFs. And the lattice QCD is now trying to get really the distribution itself, not just its moments. And these are some recent attempts. You see the blue bands and the gray bands are based on lattice calculations, and they compare to the parameterization, the global fits. Again, here the agreement is not that impressive yet, but okay, these are pioneering studies and things are progressing. So we are, even in the field of internal structure of the proton, we are achieving a situation which is similar to what happens maybe in spectroscopy, as many of the people in the COMPASS collaboration know. You have the measurements, you have the lattice predictions, and you check if they agree. And here we are getting to this level of sophistication, which is very, very nice. Then we need the maps to make predictions. Here, I should just say that there are a lot of predictions for quantities in mainly in Drelian kind of processes at high energies like at LHC, because as you can imagine, these are very important for LHC physics. And there are a lot of tools that are used for these predictions, but almost none of them seriously takes into consideration the problem of fixing the three-dimensional structure of the proton and checking its impact on the predictions. only these two last tools, which are very recent and they are produced by our community, the community of hadronic physics, the community of 3D structure, do contain some information about TMDs. And this, we believe, it's important, especially for the high precision required for the studies at LHC. So this is getting noticed finally, and I hope that this will become also a common wisdom for all the other tools. Okay, now let me come, so this was a general kind of setup and the relevance of the studies we do. Let me come to some selected recent results and perspectives. Again, I apologize because it's my personal viewpoint, but you will have also other talks during the workshop that can also speak about other points. So I will start with unpolarized TMDs. The unpolarized TMDs are the benchmark for the studies of also polarized TMDs, obviously. If we don't understand unpolarized TMDs well, it's impossible that we can pretend to know the polarized ones. And in fact, the unpolarized TMDs are the sector where most of the progress has happened in the last years. I just remind you, since I'm a theorist, so there should be some formulas in the talk. This is the structure functions in semi-enclosed DIS. Structure functions which are observable are obtained by convolutions of TMD PDFs and TMD fragmentation function. So one of the problems in the business of TMDs is that you always have these convolutions. You have to parameterize the non-perturbative objects, but they are convolved to pairwise, and so it's a bit more difficult to extract them. And most of the analysis in the theory side, from the phenomenological side, is done in the Fourier conjugate to KT. And now, unfortunately, in the literature, we use very often the symbol BT, but this is not the impact parameter space of the GPDs and of the impact parameter distribution. This is simply the Fourier conjugate to transverse momentum. It is convenient to do this analysis in this space, because in this space we can write the TMD, sorry, so this is, the convolution is multiplied by a half factor, which can be computed to a certain level in alpha S, a certain expansion in alpha S, perturbative expansion. So I was saying, why do we do the BT space Fourier transform? Because there we can write down a formula for the Fourier transform of the TMD, which contain all the ingredients, including the evolution of the TMD. Here you see that the TMD is built starting from collinear PDFs from the so-called matching coefficients. They can be calculated perturbatively. Then there is the so-called perturbative pseudo form factor. Again, this is calculable perturbatively. Then there are the non-perturbative parts, the non-perturbative part of evolution and the non-perturbative parts of TMDs. These are the ones we extract from data. The other ingredients, we can compute them at a certain perturbative accuracy. Fits of unpolarized TMDs. These are the last year's fits fully based on the TMD formalism. And you see that they are increasing in number. The number of points is different for the different fits. The levels of accuracy are different, but a lot of work is being done in this respect. And for concerning the level of accuracy, look at the behavior of the predictions if you change the perturbative accuracy. You see that in the beginning you have big differences between what is called leading log and next to leading log. Then the moment you start going to next to leading log, prime, and next to leading log, these are higher orders in perturbative accuracy, you see that the perturbative series is nicely converging. And we are now working with this kind of accuracy. So we are confident that we are not doing big errors with the perturbative analysis. The X and Q square coverage is pretty good, pretty wide, because we are using both fixed target experiments, CIDIS fixed target experiment, including COMPASS. COMPASS is here. And also Drelian experiment at different energies, including the Z boson mass. And this is the recent Shimemi Vladimirov 19 extraction, so similar coverage. This is now in a log in Q plot anyway. So it's a very nice, it's starting being a very nice coverage. We are missing all this region, but this is going to be covered by EAC. Even if you thought it was a very large X and Q square range, compare it to the global PDF fits. Global PDF fits, collinear PDF fits, have a much higher reach in X and Q square. So we have to go there. We have to still do a lot of work. There are available tools which appeared recently to compute TMDs and to also use the extracted TMDs. I encourage you to use these tools and also to give feedback to the authors of the tools so that we see what is useful for the experimentalists, what is useful for the community. One of them is this Nanga Parbat tool that we developed here in Pavia. So it's a TMD fitting framework, and it contains the results of our TMD extractions. Another one is Artemide, developed by Alexei Vladimirov, Ignazio Scimemi. So this is also similar. You can get information about the TMDs, obtain the TMDs of the extraction from their software. So try to use it and see if it makes sense also with your data. Also, we are working on TMDlib and TMD plotter. This is a website where you can plot can get the TMD values in their plots. We are still finalizing it and improving it, and we are going to put inside this tool also the recent extraction. This is just to give you the feeling that things are moving and we are getting closer and closer to what happens for the collinear PDF, so for the 1D world. Now, what about using COMPASS data for these fits? So we have used COMPASS data in the past, and we have checked the most recent COMPASS data at this level of accuracy, which is called next to leading log. The R factor in that case is 1, and the agreement between our past fits and your data is very good. However, if we go to higher orders, so if we put the R factor to 1 higher order in alpha S, then the situation dramatically worsens. So for some reason, we have problems that we have not been able to resolve yet with the normalization of the multiplicities, the semi-inclusive DIS multiplicities. We are working at it, so maybe this is going to be solved. And this problem was observed also by the Torino group. Again, problems of normalization factors required to be on top of the data. But the 2019 fit by Scimemi and Vladimirov does not show this problem. So here they achieve a good description of the multiplicities, including COMPASS multiplicities, without normalization problems. This is good news, but okay, of course we have to check if we confirm this prediction or these results, or if we still have problems, and we are working on it. What about some other features of the TMDs that are not currently properly addressed? One of them, I think it's the most important one at the moment, is the flavor dependence of TMDs. At the moment, all the fits assume that the width of the TMDs are the same for different flavors. Only we did a work in 2013, back in 2013, where we tried to inject some flavor dependence, and we saw that there is a lot of room for flavor dependence, but it's not really under control. So we don't know if for instance, the up quark is wider than the down quark or than the C. So this is still unknown, and it is important to go forward with this. And I think COMPASS data will be extremely important, because you have been showing preliminary data for the proton multiplicities, so for multiplicities with proton targets. And these are extremely important because at the moment, I told you, 75% of the data we use are coming from COMPASS, but they are coming from the deuteron. So they are not really the best for assessing flavor dependence. Proton data together with deuteron data will be extremely important to do this, and I very much look forward to seeing the data and using them. this is not an academic problem, and it's not a problem that affects only the hadronic physics community. Of course, for us, it's very important to know if up and down are wider or narrower, but it is important also for other fields, in particular for even electroweak precision physics, because the extraction of the mass of the W is based on some knowledge on transverse momentum distribution. And it is usually, all analyses assume that TMDs are not flavor dependent. What happens if they are flavor dependent? We did a study in this direction, and we noticed that if we change the flavor dependence a bit within reasonable ranges, this has an effect on the determination of the W mass. So it shifts and gives an extra error on the determination of the W mass. They are very small errors, but given the precision required by these studies, they are relevant. So people cannot neglect this. We have to know the 3D structure also to fix these precision studies. Gluon TMDs, I speak about flavors, and I meant mainly quark flavors, but what about gluons? Gluons are also an entire sector of TMD studies that at the moment is poorly known. They can be accessed, for instance, in X production, but the problem with this is that it's very high energy, so it's very poorly sensitive to the non-perturbative parameters. And they can also be studied in quarkonium pair production and other processes. And there are preliminary phenomenological studies in both these cases. And so things are moving also in this region, in this part of the TMD field, although of course with more difficulties because gluons as usual are more difficult to access. And Daniel Boer will give a talk specifically on this topic, which is of current interest. Polarized TMDs. There will be a talk by Marco Radici later, so I will not give many details, but let me stress some of the things that I believe are quite important and recent, happened in the last years or so. This is the usual TMD table. So there are many TMDs, 8 of them a leading twist, helicity, transversity, sievers, Bohr-Mulders, pretzelosity, worm gears, one of them sometimes called the Kotzinian-Mulders function. So about all of these, we have some information, but not that much yet. And let me mention some of the highlights. Transversity is a very important part of the TMD business, and there are extractions of transversity in increasing numbers and precision and with different qualitative features. One of the problems is that we had some tension between the lattice prediction and phenomenology. The black dots are lattice, and the other color bars and distributions are phenomenological extractions. So you see that there is a difference between phenomenology and lattice QCD. This is one of the problems that we have to resolve, and it goes in the direction I was telling you at the beginning, checking QCD predictions with phenomenology. Recently, this is a paper of this year, there was a very, very different approach to the extraction of transversity, putting together also quantities which are not normally used for transversity extractions, which are subleading twist also. And in this particular case, they seem to have no tension. So you see that these are the lattice prediction, the magenta, and also the magenta ones, and this is their recent result. Now, this is very interesting, and it's a pioneering study. However, one has to be careful because if you use just a standard approach, so using only, let me say, data where we are sure that we are accessing the transversity function, then the tension is still there. This is the greenish band. Only if you add up also the subleading twist asymmetries, then the situation changes. But it changes, in my opinion, to some price, because this is the result of the transversity from that work. And now you see that the transversities are much bigger than the previous extractions at high X, both the up quark and down quark. And one of the reasons why this happens is that the authors of that fit do not impose the Sofer bound. So in the last months, there have been at least 3 extractions Benel, D'Alesio, and this one, which relax also the software bound. This is interesting to study, but in my opinion, it can be dangerous in the sense that the extrapolation region at IX, where effectively we have no data, is obviously, as you see it visibly in this case, increasing the value of the tensor charge due to the upworks. So I think we should be careful and reassess the situation. What about the Sievers function? The beginning of my talk was showing you a distribution in transfer momentum space, which is influenced by the Sievers function. This is a result of our fit, and this is also a recent, very recent result by Echevarria, Kang, Terry, and John Terry is going to give a talk about this, so I hope he will give a lot of information and clarifications. You see that if you use only the semi-inclusive DIS data and also COMPAS pion proton Drell-Yan data in their case, the extractions are consistent. Now here, pay attention that the color coding is different. This is the up quark, so it should be compared with the green curve, and these are the down quarks to be compared with the red curve. They are very similar. So if they are similar, what can we say? And they are also compatible with lattice predictions, by the way. There are pioneering studies showing the so-called Sievers shift, and this is in quantitative, semi-quantitative agreement with the extraction. So this is all very good. So you know very well that there is this prediction of the sign change of the Sievers function, and COMPAS made a lot of efforts to study Drell-Yan processes and verify this sign change. This is a plot from your publication of 2017. The precision of your data were at the moment not that good yet, and you are increasing these statistics. But you see that you can compare the predictions, your data with your measurement, with the predictions with the sign change and without sign change, and you are favoring the sign change. Now here we are in the position of saying something a bit more quantitative, because in the fit by Echevarria, Kang, and Terry, they also included COMPAS Drell-Yan data in their fit. And they see no tension with the fit. You see that the chi-square per data is 0.6, so perfectly in agreement with the hypothesis of sign change. So this is okay. What is not okay, however, are the data coming from RIC, from STAR, at higher energies, W and Z mass. Here you see the predictions, the blue curves, and the data. And the chi-squares are bad. So this is not so okay, but this is not due to the sign change problem. These are assuming the sign change, but you see that the problem is not so much the sign change, it's the magnitude of the effect. So what's the problem there? We don't know very well, but the group also tried to make a fit, including those data, including the RIC data in the fit, and this is what happens. It's something troublesome in my opinion, because you see that the Sievers functions are now not very well determined. They go very big, they become very big at IX. And again, here there is no imposition of positivity bounds. So I think these are all problems that should be carefully assessed. But John Terry will tell you more, and also Marco Radici will tell you more about these topics. Then something else which is important for COMPAS, weighted asymmetries. The usual asymmetries contain some convolution of TMD and fragmentation functions, as I showed you at the beginning. So convolutions are involved when you do normal asymmetries. When you do weighted asymmetries, so we weight the asymmetry with some power of PT, then in principle you achieve a deconvolution. So you achieve a product of the Sievers function and the collinear fragmentation functions. You have published data here with the weighted asymmetries. They are very interesting, and you even did an extraction point by point of the Sievers function based on this, since you could take advantage of this deconvolution. This extraction is compatible with the previous extraction of the Sievers function, but is it admissible? Is it correct to use the weighted asymmetries? And Ted Rogers is giving a talk on this topic, so I leave it to him to clarify this point. Jet asymmetries are a new topic that entered the game of TMDs. And at COMPASS, there is no possibility to use this probably, but still at EAC, there will be an exciting opportunity. So this is again another field that has been open to the study of TMDs. Bohr-Muller's function, I mentioned transversity, Sievers. Let me also mention just a third example, and then I will not touch any other TMD, the Bohr-Muller's function. Why am I showing this? Because you have recent data on these observables, so on the observable that is related to the Bohr-Muller's function. Maybe you are nervous because you don't see phenomenological studies using this data yet, but don't worry. Keep calm and they will come. Unfortunately, we have some priority. Let's say first we study from unpolarized, then Sievers or transversity, and then this will come for sure, sooner or later. The future is bright. So there are new data from Hermes appeared this year. This is surprising because Hermes closed 10 years ago, but the collaboration is still producing results. And this is the first example of a multidimensional meaning of all the asymmetries of Hermes. So this is very important. Bravo to the Hermes collaboration. COMPASS, I already mentioned that you have a lot of preliminary data. You are in full swing mode, and these data are giving a lot of information for TMDs. I'm very happy. So congratulations, keep going. And JLab almost has just started. This is 2% of their statistics compared to all their Hermes and COMPASS data. So with 2%, they do already comparably good or better than past experiments. So this is awesome. And there are projects also for future detectors or future machines. Solid JLab, then fixed target LHC also with spin. Very interesting project. Then NICA, for instance, to study maybe gluons, to access gluons in PP collisions. And of course, last but not least, the EAC. There will be a talk by Marco on the topic. Let me just show you one of the results we obtained recently, and it will probably be included in the yellow report. These are the sensitivity coefficients. So they tell you how much the data from EAC will impact on the parameters of the TMDs. And the bigger the bar is, the bigger the sensitivity is. You see how beautifully the impact of EAC will affect TMDs extractions. And each
Alessandro, sorry, I have no possibility to show you the time, but I warn you. Yeah, thank you.
I'm done, Fulvio. So conclusions. Unpolarized TMDs. There are full-fledged TMD extractions up to even N3LL accuracy, and there are constant improvements. One of the outcomes of this analysis is that by now, simple things like Gaussians or no X dependence, they have to be abandoned if we want to describe the data. However, flavor dependence is still unknown and should come next. For polarized TMDs, nice results, new results, some of them contradictory. For instance, transversity differences, Sievers differences. I think this is an interesting time because contradictions are anyway nice. And new ideas keep coming. Jets, jet observables, weighted asymmetries, different measurements. So there's still a lot of work to do, and many results are also expected from the experimental side in the next years. So I think this is really an exciting period. Thank you for your attention.
Thank you very much, Alessandro, for this extremely interesting talk. I see only one hand raised by Silvia Della Torre. Please, Silvia.
Hello. Ciao, Alessandro. My question is the following. So you have underlined the relevance, it is also in the conclusion, of the flavor dependence. And for this subject, you have used mainly the different targets, protons versus deuterium.
Yes.
Now, my question is about the final state. if we have flavor analysis of the final state in semi-inclusive, for example, do we also move in this direction? Can you comment about?
Yes. Yes, for sure, the identification of the final state may help for flavor analysis, as always, also in the case of collinear PDFs. Also in the case of collinear PDFs, final state address detection allows some, gives some impact on the flavor of the determination of the flavor dependencies. However, there is always the problem of the mixture between PDFs and fragmentation functions. So most of the semi-inclusive DIS data at the moment, let's say in the inclusive case, DIS data are used to extract mainly the fragmentation functions, not so much the PDFs through the use of fragmentation function, but mainly the fragmentation function. This might change, and this will change in the sense that you simultaneously have to determine both PDFs and fragmentation functions. But the fact remains that you have in the middle also the fragmentation functions. The same goes for the TMDs. So we are now speaking about the width of the TMD, but in the observable, we have the width of the TMD together with the width of the fragmentation function. So it's less, it helps, it certainly helps, but it's not so clear-cut as changing the target. But it will definitely help.
Thank you.
Andrea, you have a question?
Yeah. First of all, I would like to thank Alessandro, but I would like to ask him if he can comment in the slide before how these results were calculated. What was the luminosity and the amount of integration of the data?
Thank you, Andrea. So, yes. So I can tell you what we did, and for the details, for instance, luminosity, I have to refer you to the yellow report and to Ralph Seidel, because what we did is we started from simulations done with Monte Carlo generators by mainly Ralph. So in that case, he was taking, he gave us some energy configuration. For instance, this is the square root of S equal to 60 GeV. So this is 10 GeV on 100 GeV energy configuration. Then this is reconstructed in the acceptance. So it takes into account also acceptance options. So we just took that. And then what we did is, we studied if we change the parameter of the TMD, how much this is correlated with the observable in this specific bin. So these are bins of X and Q. Within this bin, there are many bins in Z and PT. Okay, so there are data with a certain statistics, so with certain numbers of events in each point in X, Q square, Z, and PT. And here we give you the average over Z and PT. So it's just it gives you an idea. It gives you an idea of the impact of this specific X and Q square bin on average. And you see that changing. Let me give you an example. Let's take the orange band here. The orange band is the low X behavior of the TMD. It's a parameter determining the low X behavior of the TMD. So not surprisingly, if you have data low X, they are very much correlated with this parameter. So if you measure things here, you are going to give important information and to constrain this parameter a lot. High X data, not surprisingly, they don't affect much the knowledge of the low X TMD. Vice versa, if you have, let's say, the width of the TMD itself, at mid X, so at X, well, even IX at 0.1, this is affected more by IX data. G2 is the so-called non-perturbative evolution parameter. So you see that this parameter is affected by a lot of measurements, especially the one at higher Q. And again, this is maybe not surprising, but here you see it quantitatively. Does it answer your question?
Yeah, thank you.
So I think I can just accept one more question from Franco, please.
Alessandro, I'm surprised by what you said about extraction of transversity and the puzzle, the problem, the discrepancies. Insofar, all the extractions of transversity have given more or less the same result. Yes. Now what you've shown is widely different. Can you say in a few words what's the problem?
Okay, so maybe Marco will also say something more about this. Well, for sure, Marco will say something more about this. But the idea of the fit, let's call it JAM 20 fit, is to use the
sorry. I'm not referring about the difference between lattice and phenomenology. You have shown a transparency in which there is a band extracting transversity, which is here. Here it is.
Yes.
This one.
Yes. So here I can only say that the method they are using is very different from the standard method, because they are using a pool of measurements, including subleading twist asymmetries. So subleading twist can be connected with leading twist asymmetry within certain assumptions, typical Vanzura-Wilczek approximations, Lorentz invariance approximation. Via these things, they connect everything together. And then they try to do a fit of all these observables simultaneously. So this has the merit of putting more data in the game and giving more constraints. It has some drawbacks. One of them is the need of certain assumptions, and also the analysis done at a lower level of accuracy. So this is leading order with no TMD evolution, with Gaussians, so many simplifications. So I think this has to be taken as a first, an example, a very interesting example of the first application of this method. But I think one has to check again more carefully if the assumptions are okay and what is the compatibility with other extractions. In particular, here I am a bit worried, as I told you, that the behavior at IX is very different, and we have no data in our extraction. We have no data at IX. In their extractions, maybe they have some influence from some data set, which also constrain a bit the IX region. But I would be worried about extrapolations to IX.
Thank you.
Fulvio,
Okay.
I know we are late, but just one word that I will comment this talk.
Okay.
Yeah,
yes.
I mean, in my opinion, the reason is somewhat different. So anyway, I'll just refer to my talk. I will have a couple of slides on this problem.
Okay. So thank you, Marco. You will elaborate on that. So please, Anna.
I think that our measurement on deuteron next year will be very interesting to check these calculations.
Yes, and I'm sure that Marco will speak about that.
Yes.
Okay. So thank you for this very lively discussion, and I propose that we thank Alessandro once more and pass to the next talk by Gunnar Schnell, TMDs from semi-inclusive DIS.
Good morning. I hope you can see my slides.
We do.
Also hear me?
Yes.
Good. First of all, thanks for the invitation to give me the chance to talk about TMDs, from semi-inclusive DIS. And first, I also will start with a disclaimer that by now, actually, we have reached a point in time where there are too many results to cover in one talk from TMDs. And clearly, this will be a personal selection. I will concentrate mainly on polarization. There will be a talk later on unpolarized targets on Wednesday, actually, for the COMPASS data. And there will also be a clear bias towards the latest Hermes papers because there's no dedicated Hermes talk, so I thought I will do that in this talk. There will be dedicated talks for COMPASS and JLab, and as well as future programs, and I refer here mainly to the talks by Patricia, Harut, Hayan, and Marco, who will give the next talk. And I also omitted an extensive introduction because I rely here on the talk, the excellent talk, which was just given by Alessandro. Now, just to remind ourselves, the beauty of semi-inclusive DIS is that when you observe not only the scattered lepton, but also the produced hadron, you have various observables, various basically probes. The scattered lepton actually gives you information already about the particle kinematics in the nucleon. And then you can, of course, have a polarization of the nucleon, which gives you also information about the parton polarization. If you then also observe the final state hadron, you will have access to fragmentation kinematics, and the angular distribution of the hadrons will then also give you a selection of the fragmentation function. And the flavor actually of the final state hadron, which is not indicated here, will also give you a tagging device to the flavor of the initial partons. Now, I will not go in detail, but just to have it for completeness, there are 8 TMDs that basically characterize the spin momentum structure of the nucleon at the leading twist level. And they are somehow summarized here in this table, where the quark polarization is indicated, unpolarized, longitudinal, transversely polarized, as well as the nucleon polarization. And all the functions in green are actually chiral odd functions, so they cannot be measured easily in inclusive DIS. So you need actually a chiral odd, so parameter, for instance, a chiral odd fragmentation function. So they all have some names, which I will refer to during my talk. So important here now is that you have these parameter, and if you want to look at hadronization, these are the fragmentation function, a very similar table as before, but now it's not the nucleon polarization, but the final hadron polarization, which is given here on the left. I do not see actually the mouse, so I cannot really point. And if you only observe unpolarized hadron in the final state, 2 leading twist fragmentation functions survive. This is the D1, the unpolarized one, and the Collins fragmentation function. And then those 2 couple either to the chiral odd TMDs or to the chiral even fragmentation function. If you want to go further, you need to look at polarization in the final state, like transverse lambda polarization, which has actually been done, for instance, at COMPASS. So if you couple them to the various PDFs, you will then get characteristic azimuthal dependencies, which you then analyze in semi-inclusive DIS. So let me go to the results. I will quickly flash the multiplicity landscape for the unpolarized TMD, F1. And here's a table from a latest COMPASS paper, which basically summarized the data sets which are available at the moment. There are some limited measurements also by H1 and Zeus. And the reason why I would like to flash and remind ourselves about this paper is because of the beautiful precision which has been here achieved. This is the data which is taken on a deuteron target. And it's differential actually in 4 variables, in x, z, q squared, and ph verb squared, which is very important nowadays. All these CDIS cross-section and asymmetries should be actually analyzed as in all dimensions as if it's possible, or in as many dimensions as possible. Now this is only one example of because this is the lower Z bin, so you have many more Z bins. So this gives you a flavor on how precise these data are. Of course, precision also comes with responsibility, and it's important there to really employ scrutiny in evaluating all systematic effects, detector effects. And even better is to have similar experiments or similar data sets from other experiments, which in the moment is not available, but hopefully will come from JLab and EIC. Now, there's also a beautiful high statistics data set still to be analyzed, or maybe we hear something more in this conference. It's the data set which we're taking on a pure proton target, mainly actually focusing on DBCS studies, but of course can also be used for multiplicity studies and other unpolarized nucleon TMD studies. Now, this is just a quick comparison, and you can see this is on the left. You can see the comparison between COMPASS and JLab. JLab, of course, much lower energy, and on the right, you see the comparison with Hermes. And from the slope, you can already conclude that you have a widening of the pH perp width when you increase the energy. But now let me come to polarization. And the first PDF I will discuss, or TMD PDF, is here the helicity distribution. Normally, helicity had been analyzed mainly in the collinear framework, basically to evaluate the contribution from quarks to the spin of the nucleon. But one can also look at the transverse momentum dependence. Klaas was, I think, the pioneer in this respect and looked at the transverse momentum, because that gives you information about the width of the quark distributions for the different spin alignments in the nucleon. And you can, if you have, for instance, this is well possible, a difference in the transverse momentum width of F1 and G1, you will get a transverse momentum dependence of phi symmetry. So Klaas sees some hints of a pH perp dependence or PT dependence. Here are data from COMPASS and Hermes, both on a neutron target, where no significant pH perp dependence actually was observed. And there may be a hint for a dependence for the proton data from COMPASS, but I think these data have not been finalized yet, as far as I know. Now there are also very new data from Klaas, or relatively new data from Klaas. These are now high precision pi0 data. And this is now in a two-dimensional binning in X and pH perp. And I would say it's still not conclusive whether there is a pH perp dependence. I think it's also consistent with none. But there are other data which will come from JLab and also from JLab 12. Here's an example of what is the projected precision for positive pions. These are the blue data points compared to the red ones, which were already published. So these will be much more precise and will allow multidimensional binning, for instance, to study pH perp dependence for fixed X. Now I will come to transversity. This is actually the third TMD that would also survive integration of a transverse momentum, so it has a collinear counterpart, the same for helicity and the unpolarized distribution. Now, transversity has been mainly studied in the Collins fragmentation framework, coupled to the Collins fragmentation function. There are other ways, like looking at transverse lambda polarization or dihedron fragmentation, which even allow then a collinear extraction. Now, these are the very first data, actually, and evidence already now 15 years ago from the Hermes proton data, which clearly showed that transversity and the Collins function are non-zero. And there was quite some puzzle back then that they had such large pi minus asymmetries, opposite in sign, which then led to the realization, yes, you have disfavored Collins fragmentation functions that are large and opposite in sign to the favored one. So in this cartoon, you have a transverse polarized up quark, and you produce a pi plus. The pi plus goes favorably to the left, while the pi minus goes to the right. This, of course, then leads to various cancellations and single spin observers. And this is an example now. These are now much more data that have come in the meantime. There are results, a lot of results from COMPASS. You can see here on the right side a comparison of the COMPASS data, the proton data in this case, also with the Hermes data, which has actually quite a nice agreement. And there are new results also from Hermes and actually Jefferson Lab here on a helium-3 target, which is basically a neutron target. So, and to point out, despite the different Q squares you have in COMPASS and Hermes, you don't really see a large effect when you compare them directly. So there seems to be no strong evolution effect in the actual symmetry. You also have results for kaons, K plus and K minus in case from Hermes here. Where you see also a large asymmetry for K plus, the same for compass, and a more vanishing asymmetry for K minus. Compass also has K0 results. Now the K minus can be a cancellation, basically cancellation of the unfavored U and B fragmentation, forming a K minus, because you have also the opposite signs of up and down transversity. There's a relatively large K minus asymmetry reported by JLab for a helium-3 target, which does not really yet fit into that picture. Now, Alessandro already mentioned there have been a reanalysis of the full transverse target data set by Hermes, including all the azimuthal modulations that are possible on the single and double spin asymmetries. And we also included now protons and antiprotons. This is what you see on the left side. What you can see here, the Collins asymmetries are actually consistent with 0 for protons and antiprotons, which can well be because this is now a spin 1/2 final state, and you could well have a vanishing Collins effect for those baryons. And as Alessandro also mentioned, the analysis now performed in a 3-3 binning in X, Z, and PH-probe, which will allow a much more detailed analysis of the asymmetries. And the analysis also now includes 2 choices, either with the depolarization prefactor, this epsilon dependent factor, or without in the extraction. We also have included now the high Z region here indicated with open symbols, but only when looking at the Z dependence. So the projections in X and PH-probe are always only in the range up to 0.7. But you can still study this semi-exclusive region, or the transition region to the exclusive domain. And in the particular case here for the Collins function or Collins asymmetry, you can see that the asymmetries remain large, actually even seem to increase further when you go to larger Z for the positive meson for pi plus and K plus. Now we have already discussed a little bit extraction of transversity in the tensor chart before, and debated the validity of the various extractions. And there's this, what we call maybe the Collins trap, because of the opposite sign of the favored and disfavored Collins fragmentation function and similar magnitudes. They're not equal, but they're similar. You can write down the asymmetries or the modulation for pi plus and pi minus, which are the most important one in the extractions. And you will find that basically they relate to the same combinations of transversity and the Collins fragmentation function. So it's almost impossible to cleanly disentangle U and D transversity. And maybe current limits are driven mainly by the software bound. So it's very important actually to find another asymmetry that will help to disentangle. And that is actually data that comes from a neutron target or neutron targets. And in that respect, it's very important that we will get data from compass on D transversity and with a neutron target, and actually more maybe helium data from JLab-12 and later EIC. And this is actually not only a problem for transversity, but it's also valid for all the other chiral odd TMDs if they are probed with the Collins fragmentation function. So a little outlook in that respect is here given here. So we have currently much more proton data available than the deuteron data. Actually, it's mainly the deuteron data from a compass and the sparse data from neutron data from the helium-3 data set from JLab. So compass will now add another year of transversity running, deuteron transversity running. And this will have clearly a large impact on the D transversity. You can see in the bottom, on the left side, you have the current data points, the open one for proton and deuteron target. You can see that the error bars are much larger for the deuteron data set. And for the closed symbols, this is the projection, what will be the situation after the additional data taking. So you will have a huge improvement in the deuteron data set. And the impact you will see on the extraction of transversity is quite substantial already for the up quark, which is not the main focus for a neutron target, but it's still, you can see at high X increase in precision by about a factor of 2, and a much bigger improvement for the D transversity, which is factor 4 at high X. Now, it's also important because it will reduce correlations between U and D transversity, which is important, for instance, when you calculate the tensor charge, where you take actually the difference between the two. Let me come to other TMDs now. These are really dependent on transverse momentum. The first one is plate velocity. This is again a chiral-Ott function, and it therefore requires again a Collins fragmentation function or a similar chiral-Ott fragmentation function. Now there are various data sets available, but all of them, be it on proton target, deuteron target, or even the helium data from JLab, the asymmetries are consistently small and actually consistent with 0, which can be a cancellation effect, as mentioned before. You have opposite signs for the fragmentation function and possibly also the TMD, but it could also be just that plate velocity is 0. Another possibility is that if you look at the cross-section, actually, the plate velocity contribution to the cross-section is suppressed by 2 powers of pH perp. So this is, of course, we look at small pH perp physics here, and that can be also a reason that we do not see now a sizable signal, and we need much more data and precision before we can actually make out plate velocity. The other chiral-Ott function, which I will talk about today, is the Wormgier-1 function, H1L perp. Now, here, the situation is similar as before, mostly 0 results at Compass and Hermes, both for proton and deuteron targets. And the only exception, notable exception, is actually the class data plotted here in the bottom left. These are the triangles. For pi plus and pi minus, both a negative asymmetry is seen, which is would be a signal for H1L perp. It's a little bit surprising that both of them have the same sign, while the pi 0 results are more or less consistent with 0. And that also does not change with the new data shown in the middle for the pi 0. It's still consistent with 0. And now I have to do something I don't. And you can also see that the Hermes and the Compass results do not support a large Wormgier function or modulation. This is different for the Wormgier 2. This is a chiral-even object, G1T, and thus couples easily to the ordinary fragmentation function D1. Here we have various data sets that are actually giving reason to hope that we can extract the Wormgier function, because the first actual indication was the one from JLab on a helium-3 target, where they saw clearly non-vanishing pi minus asymmetry, and thus a non-vanishing G1T. But also the data from proton target, here is preliminary Compass data in the top right, and also now the newly available Hermes data show a clearly non-zero signal for the Wormgier function. Now, one of the most discussed TMDs is probably the Sievers function, besides the transversity and Collins fragmentation function. So this is a plot of the original Hermes publication of the total Hermes set for pions. And the nice thing about the Sievers function, actually the same for the G1T, is since it couples to D1, one can do a much easier extraction, because one does not have to involve 2 unknown functions. The only thing is, of course, one needs the TMD counterpart of D1, which is parameterized and also now extracted from the amplified data. Now, if you then just assume, for instance, that the pi plus production is dominated by U-quark scattering, which is a quite reasonable assumption, you can easily deduce from the pi plus data that the U-quark Sieber's function must be smaller than 0. I'm putting out the minus sign in the equation here in front of the ratio. Looking at the pi minus, which comes out basically 0, which means there must be some cancellation effect because U-quarks will still contribute to pi minus. So there must be something that brings it to 0 from the positive asymmetry, which can only come then from a d-quark Sieber's function, which is opposite in sign to the U-quark. This is also seen in these extractions. Alessandro showed various of them. I also showed the plot here, which shows the displacement or the asymmetry of the quark distribution for up and down quarks in a transversely polarized nucleon. And these opposite signs and distributions, of course, can then lead to cancellations again. And this is nicely seen in the deuteron target data from COMPAS, which is basically consistent with 0. There are also new results from COMPAS and also actually from JLab, from a helium-3 target. And there might be some discrepancy between Hermes and COMPAS here. It's not clear whether this is Q-square dependence, evolution effect, or just different kinematics other than Q-square. And I think more detailed analysis will figure this out at some point. Now, we have looked a little bit more into the pion data and also included now the high Z region. One reason is to see, for instance, the impact of pions coming from exclusive vector meson decay or production. And it's known that if you go to larger values of Z, the contribution from exclusive mesons increases, especially for pi minus and pi plus, where you have the dominant channel of the rho 0. And what you can see actually, first of all, that you see a change of trend in the pi plus, that the large Z region you turn and go to negative. And this is actually an indication that indeed you have contribution from vector mesons, because if it comes from a rho, the pi plus and the pi minus should have basically the same contribution because of charge conjugation. So they should reach similar asymmetries. And the particular point here, which we have seen at large Z, actually, incidentally, is also seen at COMPAS. Furthermore, we extended our studies of the pion-kaon difference, which came actually quite to a surprise or unexpected if one really just assumes U-quark dominance, because then pion and kaon should be quite similar. But of course, there had been various explanations, like a different KT width for the fragmentation functions, and also different contributions from strange quarks versus anti-D quarks in case of kaons versus pions. But what is also surprising or striking is that for the high Z data, the kaon rise while the pion drops, as discussed just before, which could be also an indication that the vector meson contribution is much smaller, which is actually seen. The main contributor is the phi production, and it stays below 10%, while for the pions it goes really up 30 to 50%. Larger amplitudes had actually also seen already also by COMPAS before. And there's a surprisingly large K minus asymmetry, which has not been seen by neither COMPAS nor Hermes, but by JLab. Very new are also the results for protons and antiprotons, here compared to the pi plus data. What you can see is that you actually have similar magnitudes in the asymmetries when you compare them, and it could be that this is a consequence of U-quark dominance in both productions. If you remember, actually, it was argued that the Sivers effect is basically a quark jet effect. That already the asymmetry is induced when the quark basically travels through the hadronizing quark travels through the color field of the nucleon. So this may be the reflection of it, that also protons will have a large asymmetry. This is a difference to the Collins effect, where you really need a spin orbit coupling or spin effect in the fragmentation part. Here you do not need it. Here you need only basically a tagging mechanism of the scattered quark. We have looked a little bit at the ratio, for instance, for protons versus antiprotons, because of course, if you talk about baryons in the final state, they are much more difficult to produce in forward kinematics. And there's always the danger that maybe the protons come actually from the target remnant, because there you start actually already with the proton. So this is a plot here, the yield ratio of protons to antiprotons. Clearly, when you go to higher Z, this increases because it's easier to produce a proton than an antiproton. But if you go to low Z, when you reach really the target fragmentation region, you see also an increase of the proton yield, but this is below the 0.2 in Z, which we apply in the data. So possibly actually indeed, the protons we see here on the left side are actually a fragmentation, current fragmentation protons. Also, Compass has performed a multidimensional analysis. Actually, this is a two-dimensional analysis, which was done in view of the Trillian data. So the data was split in 4 ranges in Q square and then analyzed in the different kinematics. This, of course, also allows a much more detailed evolution study. A step further, as mentioned by Alessandro already, is now the 3D analysis by Hermes, where the data was actually binned on a grid of 4 × 4 × 4 bins, so 64 bins in total in X, Z, and PH perp. So these data then, of course, reduce systematics. They are all statistically independent, so they disentangle correlations. And you can also isolate phase space then regions which larger signals or which you would like to exclude actually from phenomenological fits. Clearly, this will allow much more detailed comparisons with calculations. And in the publication, we actually have accompanied these analyses of their symmetries by kinematic distributions to help actually or to guide phenomenology. And this is one example here, where we show here the Q square versus PH perp basically, because if you want to be in a TMD region, TMD formalism, you need, of course, a large Q square compared to the transverse momentum scale. And the diagonal basically indicates where the two would be the same, and above the diagonal, you are in a safer region, while if you are below, you are in a not so safe region, or even in the wrong region. In the last minutes, I don't know how many I still have, I would like to spend some time on twist 3 modulations and the ones which actually are non-vanishing. The first one is sin phi UL, so a longitudinally polarized target in the sin phi modulation. And there it's important because actually this was the first one, this is the starting point of TMD physics actually. It was the first one observed at Hermes, which really started a lot of activity in this field, in fact, including the realization that the Sivers effect actually can survive. Back then, it was mainly because one thought that with the UL asymmetry, you can actually measure transversity because you have a mixing between the theory moments and the experimental moments. This is because you have this small transverse component of the target polarization vector, which goes with the sign of theta gamma star. So because in an experiment, you polarize the target with respect to the lepton beam. The theorist polarizes with respect to the virtual photon direction. So then you have this mixing. This is the leading equation. There are corrections to this. And so if you want to actually extract clearly the moments with the photon direction, you need actually data from both target polarization states with respect transverse and longitudinally polarized data with respect to the beam direction.
Sorry, Gunnar, you used 30 minutes so far, so please.
30?
You have, yeah, but you can still use few minutes.
Okay, then I will go faster.
Thank you.
First of all, the sine phi UL was found non-zero, and actually it is the genuine twist 3D contribution that is non-zero for the pi plus, and it's clearly non-zero. This is the red data points for pi plus. And this also has been seen by COMPAS. And this is in clear contrast to, for instance, one object type approximations shown in green here that really predict a small asymmetry. Here are the new data also for pi 0 from class, which also show you a clearly non-zero asymmetry. The other subleading twist is the sine phi LU. Alessandro flashed it already. Now this one gets various contributions, other Burr-Mulders. It gets some naive T-odd G perp, but it's coupled to the D1, so it's maybe not so much suppressed. There's a contribution that comes with the interaction-dependent fragmentation function G perp tilde. And last, which is actually one which is very interesting, comes with the E. It's a twist 3 function that actually survives integration over 100% momentum. And as I mentioned here, also it's linked to the pi nucleon sigma term. So it's also quite an active field of research, this beam spin asymmetry. Again, all these terms actually would vanish in the Banchero-Wilczek type approximation, but they don't in actual data. Here's a comparison of the Hermitian class data for hydrogen targets, so for proton target, and they are clearly non-zero. Pi plus is positive in both cases. Pi minus, actually, if you look at the Z projection, one is a little bit puzzled because Hermes is positive and class negative. But if you look at the last term, actually, and it's a Collins function, you have this kind of behavior you see in the class data, opposite sign for pi plus and pi minus. And this is actually suppressed at lower x, and the class data, in fact, sits at higher x. And if you look at the x dependence, there's actually a trend going from positive asymmetry for pi minus at lower x to negative one at higher x. On the other side, the data, the comparison with COMPAS is for the deuteron targets fully consistent. The very last one is the sine phi S modulation. Again, it includes many terms because it's a subleading twist distribution, but it has a non-vanishing collinear limit. And the interesting part is this is this H tilde, which is related to the Collins function, and it's also now discussed a lot in theory, because also for the EN MPP scattering. So this is a quite interesting asymmetry in that aspect. And here you have the results, the new results, and they are clearly non-zero. They are sizable and strikingly increase very much with C for both pi plus, pi minus, and a K plus. This has been seen also already at COMPAS. And so they are opposite in sign, so it actually supports this Collins-like behavior. This brings me to the conclusions. And I think really the first round of CDIS experiments and measurements is coming to an end. But we have already various indications of flavor and spin-dependent transverse momentum. Transversity is non-zero, quite sizable, and it's clear that I think it's clear that d-quad transversity is difficult to access with only a proton target, and COMPAS D transversity will be very useful. We have clear evidence that the Sievers and Chiral even Wormgear functions are non-zero, but there are no signs for Pretzelosity so far, and also for the Chiral odd Wormgear, the data or the situation is not yet conclusive. I also showed 3 examples where twist-3 effects are really large, and this is often in conflict with Banchero-Wilczek type approximations. And now a new round of measurements is coming up, and I think I refer again to the talks which will come, but I would like to thank the organizers a lot for bringing us together here virtually, but it's, I think, very important that we keep discussing.
Thank you very much, Gunnar, for this talk, which was very comprehensive, and I I'm checking. I had a hand from Franco Bradamante. Franco, please.
Yes, the microphone off.
Franco, your microphone is muted. Can you unmute it to pose the question?
Of course, I'm sorry. Gunnar, first of all, congratulations for showing us results, new results 10 years after the shutting down of the experiment. Now the question, what else? Which more results do you have in the pipeline? Just to know.
Yes, yes. In the moment, not too many. This is just due to the fact that manpower is winding down quickly, and we are still have the option of looking at lambda polarization also. Also nuclear data we are still analyzing, or again analyzing. There have been some analysis, also dihedron fragmentation. There's a huge data set which we took an unpolarized target similar to COMPASS for the DVCS program, which has not been analyzed in terms, for instance, multiplicities. But that is all has to be carried out by people who do not really get funding any longer for Hermes and do that more or less on the side. And this is, of course, a major challenge. So whether or not there will be more papers coming out of Hermes, it's difficult to predict. I think two analyses we have, like I said, lambda polarization maybe, and the nuclear studies, they might still come out in the near future. Everything else is at the moment more difficult. But if there are ideas and if there are people interested, of course the data set is there. And if there's something particular which can be done maybe only at Hermes or is needed from Hermes, we are always open to people to jump on it and to analyze the data.
Thank you. I think this answers Franco's question. Alessandro, you have a question.
Yes, first of all, Gunnar, thank you for showing the subleading twist part. In my talk, I had no time to touch it, but I believe that it's very interesting, very important, and it may also explain some discrepancies between higher energy experiments and lower energy ones, like maybe class. And I agree with you that there are a few very interesting observations already now. But first of all, there is the issue from the theory point of view of establishing factorization, and in particular TMD factorization as a subleading twist, which is an open issue. Then you mentioned the E of X, very interesting function because the integral gives what we call a scalar charge. So we spoke about axial charge, tensor charge, vector charge, and the last one is the scalar charge, so the integral of E of X, so very interesting. And last but not least is H tilde that you mentioned, the H tilde fragmentation function. There is an observation that if you do inclusive DIS, this sign phi modulation must be zero, which in turn means that the integral over Z and sum over hadron of H tilde should be zero. Do you think the data are supporting this effect? So the fact that the integral over Z sum over hadron is zero for H tilde.
So we have done the sum already at Hermes actually by analyzing the inclusive asymmetry, and that inclusive asymmetry was found to be vanishing at a very high precision, 10 to the minus 4 level, 10 to the minus 3, sorry. The opposite signs here also support that there will be some cancellation effects. It's not clear, however, if you sum them easily, you would have to weight them all, of course, with the multiplicities, basically, with the unpolarized cross-section, to get from the asymmetry to the actual polarized cross-section. But indeed, the opposite signs support the idea that if you sum over all hadrons, you will get a vanishing asymmetry. In particular, also you have these large asymmetries at large Z for the positive, but in fact, it's the pi minus that also survives at lower x, where we have, and lower z, where we have more counts. So that probably compensates for the larger symmetry you see for pi plus and k plus at the very large z. So yes, I think it's not excluded that when you sum over all pions, all hadrons in the final state and integrate over z, that in fact you will get something which is consistent with zero.
So I think the discussion is very interesting, but we are also running behind schedule. So let us thank Gunnar once more. And I propose we pass to the last talk of the session by Marco Contalbrigo.
Let me set up the things. Just tell me if you can see my screen.
Not yet your slides.
But you can hear me at least.
Yes. Now.
Okay, let me see. So stable dividend. It tells me that I'm sharing the screen.
Yeah.
Can you
correct.
see anything?
Yes, we do.
Okay. So it is a pleasure to have the opportunity to show you the electron-ion collider project that became an official project of the...
Sorry, we don't see your slides, however. We see your screen. Yeah, now it's fine.
It's so slow?
Please.
Okay, let's hope. Okay, Electron-Ion Collider became an official US Department of Energy project at the beginning of this year, and also with the site selection to BNL. So now the opportunities of these long-awaited machines are becoming real, but still requires the support of the community to really identify the compelling physics topics and the technologies that we want to exploit in order to make the experiments. Let me start with the legacy of the HERA collider that was, let's say, our example of the past for an electron-proton collider. What we learned there is that the perturbative QCD can be a precise science that allow us to make calculations at the precision level and have a predictive power. So this was important, pretty important achievement. But what we want to do now is to go beyond the perturbative regime and explore QCD.
Marco, sorry, I'm still on the first page. Can you maybe? All right.
I don't know.
Now we see. Now we see the HERA legacy.
Well, I'm wondering, however, if all the times I will change the slide, it will take us several seconds. Okay, let's see. I'm now on slide 3. I hope that is there, where you can see that there are quite precise information on the part of distributions that we achieved so far. On the left is the unpolarized one, and on the right, the helicity one. What you can...
There is still a problem. We are still on slide 2.
Still on slide 2. Yeah, still on slide 2.
Okay. Can I stop the video? Maybe that is
now we
slowing
see
down.
Yeah.
Let me see. Slide 3. I move to slide. One second.
Yes.
Slide 4. Did it change?
Not yet.
Not yet. Now, yes.
Now.
Ooh. Okay. Let's hope. Maybe without the video will be a bit faster. Let's see. Okay, what I would like to point out is that if you see on the left, one of the less known part of distribution is the one of the strange. And this is probably because it is difficult to isolate signals out of the light quark C that are related to strange. And this is one of the goals of a good particle identification in final state that are able to identify hadrons that are sensitive to this flavor. On the right, you see that the information for the polarized distributions is less precise and seems to suggest that the major features concentrate in the valence. This reflects in a plot that was already shown today by Alessandro, that is comparing the many moments that we extract from the experiments to the one of lattice. And again, on the left, as pointed out by Alessandro, there is still a large uncertainty in the calculation that most likely, in my interpretation, is due to the fact that you have a large contribution from the sea. And so it's more challenging for the lattice calculation. On the right, if we, let's say, make the assumptions that the sea is not playing a major role, the situation seems to be under control, surprisingly enough, because from the experimental point of view, instead, these distributions are more difficult to reach. However, what is the focus should be the transverse degree of freedom of the nucleon, because this holds at the scale of the confinement and should bring us the pristine information on what should be the structure and dynamics inside that confined state that is at the base of our known matter. So we have examples that came from the past that challenge our comprehension. You know the single spin asymmetries, of course. You know the proton spin budget, where you have contributions from the correlations of these transverse states, as an example, the orbital motion of the quarks. But there are also new bright challenges that we have in front of us. One of these is the transverse distributions of the charge in the nucleon. And you know that we have a puzzle now in the proton radius, and even a program that wants to extend the COMPASS data taking to access this issue with, for the first time, a muon beam of high energy. That is the AMBER project. And below you see results from the heavy ions collisions, where you are looking for the quark gluon plasma and the effects of the confinement. What the experiment found is that, let's say, signals in the final state that were originally associated with the plasma due to the fact that they were evident in heavy ions collisions, have similar or almost identical features also in a reaction where you have a simpler initial state, where you have simply a proton, and so may originate by the distribution and the fluctuations in the, let's say, transverse plane of your partons in the initial state. So all of these move to the fact that, as we know, our baseline confined state, that is the nucleon, is a pretty complex object. And in order to understand it and explore the universe of the strong force, we needed to go beyond the perturbative regime, move to the non-perturbative one, or at least to a multi-body description. That will allow us to access many different dynamics process of the force that we know to be the strongest. So that should be very peculiar. I'm not going to list them, but yeah, I put here, and you know all of them pretty well, I think. So this is at the base, I think, to the need of an electron-ion collider. The physics was anticipated in many papers in the last decade, and based, I will say, on the prequel that came from Hermes, Compass, and GELAB that opened such kind of studies with the first measurements, and are still doing that. We had in the past 5 years the evaluation process that started with the long-range plane in 2015, when this electron-ion collider became a priority for the Department of the Nuclear Science Division of the DOE, and ended last year with the National Academy of Science review that is not only involving the physics, but also the General Academy of Science, that endorsed the project. And this allowed the project to start with the critical decision 0 at the end of last year. And the site selection that was at the BNL, where pre-conceptual design of the machine was already existing. And now it's continuing with a so-called yellow report that the community is writing and preparing in order to, let's say, provide a comprehensive description of the project and the scientific goals. So let me show you this plot that wanted to stress the fact that for the electron-ion collider, the goal is not to explore a specific corner of the QCD dynamic ranges, but to live in the transient regions, moving from the perturbative description down in Q towards the hadrons, in order to understand the confinement and their properties, and also to move along X and in regions at low X, where you may approach the gluon saturation. That is a new regime that was maybe touched in the experiments so far, but not in a way that allow us to do really a study of that non-linear evolution of the strong of the matter under strong force. In order to do that, what you want to have is a machine that have, let's say, enough energy, but is not necessarily at the frontier of the energy. Instead, you see that it is in between what we had in the past, so fixed target experiments, and what was provided at HERA with the very high energy collider. But you want to have polarization there in order to exploit correlations, and ions. One of the, let's say, flagships of the ion use is to enhance in the collision in an effective way the gluon density sensed by the probe, and so extend the saturation scale range to values where you can indeed approach a perturbative regime. So you have still a regime that is dominated by a very strong force, but the interactions that are at many body between partner and partner are perturbative. So it's a regime where you can, in principle, do calculations. And this came at a variance with what we had in the past, as an example in ERA, as you can see. So what is the topics and the needs? So you want high luminosity and polarization. This in order to explore the parton distribution in space and momentum. and access correlations with the angular momentum and specifically with spin. This will be important to search for the Hadron emerging properties that came from the first principles of QCD, and also will allow you to access information or signals of new physics. There are measurements, precise measurements of the Weinberg angle, and the potential to search for exotic states if the luminosity is high enough. With the use of ion beams, what you can look for is the hadronization in cold nuclear matter. This will be a benchmark of the heavy ion collisions, looking for the quark-gluon plasma, but also looking how the quark fragments toward the final observed hadron in the matter at a variance with what you can measure at plus and minus machines in vacuum, and this will set light in the confinement origin, hopefully. Finally, as I mentioned, if you join the ions with high energy, you can access new channels like enhanced gluon density. You can access jets and heavy flavor physics and get enhanced sensitivity to gluons and their dynamic toward the saturation. So all of this just a machine that have let's say an energy that is in between the fixed target experiments, but is not so high as Hera, but has significant luminosity. This machine will, let's say, extend the reach of the ongoing measurements. There is still, as mentioned in the previous talks, the goal to have a Hadron measurement with a transverse target at COMPASS next year, or the next couple of years, let's say, and a comprehensive program of investigation in the valence region at JLab at 12 GeV. Still in projects that you exploit at different scattering. There are also other elements in the landscape that make the situation pretty promising. We will have new measurements of the fragmentation in vacuum from the Bell 2 experiment that will be at the luminosity frontier and started data taking recently, I think 1 year ago. And the project to insert a fixed target at an LHC that will be unpolarized after this shutdown, and hopefully could be polarized after the next shutdown, in order to provide a bridge between the physics, let's say precise physics at the electron-ion collider and the hadronic rich phenomenology physics that you can have at a LHC. From the theory point of view, in the last years there were really important progresses and achievements in lattice, with the calculation that were extended to the disconnected diagrams, and with the attempts to move beyond the Mealy moments and provide even the dependencies of the functions on relevant quantities like the Bjorken X. This create, let's say, a global framework that is really promising to reach the goals that I just mentioned before. Going a bit more into the details, you see that it is extending a lot the reach with respect to fixed target experiments. Here, as a benchmark, I use COMPASS, that I think is the one that used that reached the highest central mass energy. But you see that the IC will enter an uncharted region, and we bring their polarization and ions, and so sensitivity to gluons and to the evolution. And this will provide you compelling measurements, as an example, for the helicity of the partons and sensitivity to the orbital motion. Novel sensitivity on the evolution and details at, let's say, moderate and low X of the TMDs and GPDs, moving toward constraints of the bigger distributions. And accessing, as I said, jets that are the best surrogate for the partons and allow you to look for correlation in the fragmentation, look into the structure of the jets themselves, or correlation among different jets. In the bottom, you see here example of digest events where you can have analysis of the distribution of the leading hadrons or the jets themselves that are correlated to the gluon linear polarization in the target. So this will be new windows that only EIC can open. And together with that, the PDFs of the nuclei, of the nuclear target, that in a region that match well with the measurements done at the RIC and LHC in the heavy ion collisions. So we'll provide, let's say, baseline for the interpretation of those data. Finally, you will look for signals of the saturations that can come from the diffractive processes, or again, in the distribution of the events in the final state, where you will have enhanced or depletion of the cross-sections that are anticipated by saturation model that you cannot reproduce by the standard QCD matter. All of these goals are now pursued by a large community of the order of 1,000 scientists. You see that one of the major community besides the States is in Europe. This EIC community has a structure, a recent structure with a steering committee, institutional board and other committees, and meet together on a year basis. And now every 2 years plan a meeting in Europe to acknowledge the interest that we have also here. And you see that the first interesting enough was in Trieste, as we are meeting today. So, as I said, at the beginning of this year, the site was chosen. It is BNL. There is already a conceptual design that is being refined. And you see on the right, there in order to accomplish the goals of having electron and ions colliding together. The lattice is already well defined. The most studied is the blue curve, but there is also option to move to the red one in order to optimize the performance towards the science. So let's say globally, what you want is a high luminosity. That means to run between 10 to the 33 and 10 to the 34. That is of the order of 1,000 times ERA. You want a flexible center of mass energy, and as I mentioned, polarized beams and ions. The interesting point is that both curves, red and blue, can, in some sense, coexist in the same machine. And one of the options is optimize the interaction point if you have more than one, in order to best match to the different energy regime. There is the option, because there are two large areas already existing, one coming from Phoenix that now is being upgraded to Super Phoenix, and one coming from STAR. And so in principle, these two IPs can be mirror each other or optimize for the different energies and science scopes. There is management working, put in place to work toward the project that is a share between the BNL and GELAB, that were the laboratories that studied the EIC and proposed EIC to the American Department of Energy. And this is the timeline, a sketch of the timeline. You see that in the next years, we will have several critical decisions, steps towards the finalization of the project before the real construction start, that is foreseen in 2023. And the first collisions with an aggressive schedule are foreseen around 2030, and the full operation around 2032. The community in these initial years had to work strong in order to define the scopes of the detectors that we want to put in place. Those are challenging because they should match the capability to run a high energy, so to reach large Q square, but also to be precise enough to access the typical scale of confinement, so a few hundred MeV. They wanted to detect all the remnants in order to allow exclusive physics and have excellent PID in order to provide flavor sensitivity. There were many conceptual designs that were proposed. Now there is effort in order to make them converge to something that can work and cover the physics. This is done within the community. And this slide shows you a middle-term horizon that we have in front. So there is an R&D program that is ongoing and still active in order to try to identify the technologies that are suitable for EIC. This year, there is a yellow report activity that is we have the scope to advance the detail and the state of the requirements and technologies for the detector concepts. That is now close to the end. And there was this year an expression of interest call to understand a potential interest in contribution for EIC that was worthwhile, and now is an evaluation process. Next year will be pretty important. There will be most likely a call for the detector proposals in this case. So really proposal to and availability to construct detectors at the EIC that will be followed by the initial organization into collaborations. And there was also let's say, discussion in the community that was that will be, let's say, boosted by a series of workshops on the scope and the feasibility of a second IP at EIC. So just a flash before the end of projects and technologies that are being explored in Europe for EIC. There is interest in silicon tracking for the vertex scenes, for the vertex and the tracking at EIC. There are interest in the particle identification that are based on the developments that were made for the experiments here in Europe. So for the silicons are based on the development for the ALICE ETS3 with new CMOS technologies for the detectors. The barrel DIRC is based on the studies for the Panda DIRC, that is an experiment in Germany. And the forward PID is based on development made for Compass, but also at Hermes and LACB, so expertise in the rich detectors, let's say, in Europe. Quite interesting. There is a challenge because you want to have single photon sensitivity in a magnetic field, and so we had to look for new kind of detectors, for photon detectors there. One possibility is silicon PM, and new electronics that are able to deal with them, considering their limited tolerance to radiation. And there are also developments that derived from the COMPASS technology on the gaseous detectors, improving the photon cathodes and the path readouts. So there are many different activities where European collaborators can find satisfaction. So altogether, the electron-ion collider is a high-energy, high-luminosity collider that match together electrons that are elementary particles and complex proton and ions systems. It is funded by DOE and with the scope to be able to take data in the 30s. We consider it a unique opportunity to move from phenomenology to a rigorous treatment of QCD as a total, not only perturbative QCD, and this should allow us to reach potential for breakthroughs on the strong force. The detectors are challenging. They should match IQ and low PT sensitivity. And within the project, one detector is already accounted, so there is wide space for contributions. And the community is really supporting newcomers because there is a high interest in international cooperation for such a kind of project that will be unique in our future. So thank you so much.
Thank you very much, Marco. So I don't see hands raised. Let me start with a question from myself. How important is to have polarized deuterons, and are they foreseen in RHIC accelerator?
Well, the importance you know pretty well, and yes, they are foreseen there. There is, well, potentially there is many, let's say, light species that can be polarized at the EIC. Let me see here. Deuteron, helium, maybe even something that is heavier than that, sorry. What will be really achievable, we will see, but deuteron is definitely on the table. And we discussed today how important it is to access flavor sensitivity together with the final state hadron identification.
Absolutely. So, is there any other urgent question which we want to ask Marco, or his presentation of this very interesting and appealing perspective of the electron-ion collider was clear and comprehensive? All right, I don't see any request for questions, so let us thank all the speakers again. It was a very, very stimulating and nice session, and I close it. We will reconvene after lunch.
Yes, we will start again 2:15 in order to have an hour of break. So see you at 2:15.
Marco, and upload your slides or send them to us. Don't forget that.
Now, as you see, my internet connection is not really bright, so I will.
No, that's the reason I was checking if they were there in order to share eventually my screen, but this was not the case.
Yeah, because I was not able before, so we'll try now during lunchtime.
Okay, thanks.
Okay, bye.
So, hello, good afternoon, and welcome back to the third session of IWHSS. Can you hear me? I suppose, yes?
Yes.
So, thank you, Fulvio. So, in this session, we will have 5 talks, so it is quite a long session. We will have Jianqie Peng, then Oleg Heiser, Benar Mulilu, Marco Radici, and John Terry. So we will start with Jianqie.
Okay. Yeah, good afternoon, good morning, and good evening, depending on where you are. So yeah, thank you for the opportunity for me to talk about the recent results and the future prospect of diamond production. So let me So when we talk about diamond production, we have in mind about the dry process, which is shown, the underlying diagram shown here. So the deep inlet scattering is shown here. So as we know, they are both an electromagnetic process, and they are closely related to each other. One is using the lepton beam, and the other will be using the hadron beam. And since both are electromagnetic process in nature, so the mechanism for both reactions are very well understood. So indeed, they have both play a major role in being used as a tool to probe the partonic structures in the nucleon or in the nuclei. So because of this very nice property, I think over the last 35 years, it was really long duration, we carry out several Drell-Yan experiments at Fermilab. So those experiments are listed here. So it's actually quite interesting that the first experiment was proposed in 1986, was completed 2 years later, then followed immediately by another experiment, completed 2 years later, and then followed by another experiment, etc. So, so the program is still going on, and I think we just completed 2 or 3 years ago the sequence experiments, which I'm going to present some of the results there. And a new experiment actually is being prepared right now and is scheduled to take data next year. So one can see that the first experiment was proposed in 1986. So it's interesting to see what prompted us to propose the first experiments. So as many of us probably remember that in the early 80s, there was this discovery of the ENC effects at CERN. So what's shown here is in the deep inlet scattering, when you compare the iron versus deuterium structure function, one can see a very interesting pattern as a function of the Buchanan X carried by the parton. So there was this, there were many different theoretical models proposed to explain the ENC effects. And one can see that all of them can pretty much explain the EMC data at that time. The ENC, the deep inlet scattering is sensitive mostly to the quark structure. At the very small x is sensitive to the combination of the quark and antiquark. Therefore, at that point, it was raised by some theorists, I think Jerry Miller and collaborators, saying that in order to separate the different theoretical models, it would be useful to have a reaction which can single out the antiquark structures in the nucleus. Okay. Therefore, just as an illustration, if one plot the Drell-Yan cross-section ratio for iron over deuterium, then the different theoretical models which sort of converge here for the deep inlet scattering will start to be different. Okay, Therefore, the idea is that if you can measure the Drell-Yan for the nuclear dependence, you will be able to distinguish the different theoretical models. So that was the main motivations why we proposed the measurements in 1986. So experiment was carried out in 2 years, and then the publication actually was in 1990. So one can actually see a very striking behavior just from this very simple analysis. If you just plot the cross-section on the iron over deuterium, if you plot the ratio as a function of the muon mass here, you can see that the Drell-Yan region, the ratio is pretty close to 1. However, at the resonance region, for example, of the J psi, you can see that that ratio actually is very different from 1, dropped by about 20%. If you go to the higher mass region, to the Upsilon resonance, then it's also deviating from 1. However, it's not as big, roughly dropping to about 90%. If you plot these nuclear effects as a function of transversal momentum, you start to see some rise as you go to a larger transversal momentum. If you plot this nuclear dependence as a function of the x Feynman, which is the fraction of the momentum carried by the dileptons, then you see a trend that it is dropping as you go to higher value of x Feynman. Okay. So this is the result we obtained just by plotting the ratio as a function of those kinematic variables. Here is, since the main purpose is to check the ENC effects, therefore you can just compare the iron over deuterium. For the Drell-Yan data, which is plotted here, you can compare that with several different ENC models. And one can see that actually the data already were able to exclude some popular ENC models just from the behavior of this Drell-Yan cross-section ratios here. So here is the plot showing the this nuclear dependence for various kind of nuclear targets, plotted as a function of the X target here, okay. So actually it's very interesting to see that while we were performing these measurements, we measured using the deuterium target and also a number of nuclear targets. In fact, during the experiments, we also wanted to measure the cross-section using the hydrogen target, the liquid hydrogen. However, we ran out of time, so we could not do that. So it's very interesting when we were trying to look for very large nuclear dependence in this experiment, but did not find any large nuclear dependence, perhaps with the exception of the very small X where we see some shadowing kind of effects. And we could not measure the hydrogen target, but a few years later, we performed the measurements using the hydrogen target. And to our surprise, actually, that when we go from the deuterium to the hydrogen target, the cross-section ratio that we obtain by comparing the hydrogen and deuterium actually show a very large effect, much larger than the nuclear dependence we wanted to observe but did not observe in the first place. So when we compare the lightest target, the hydrogen over deuterium, actually the cross-section ratio show a very striking. So this is related to the cross-section ratio. And the reason for this very striking effect is because this cross-section ratio of the deuteron over the proton is really related to the d bar over u bar. This is now a very well-known story now. So we actually observe this very striking behavior of this flavor asymmetry based on this comparison of the hydrogen versus deuterium target. Okay. And we also observe a very intriguing X dependence of this asymmetry. At a very low X region is consistent with being symmetric. Then it starts to rise linearly, and then at the highest X region, it starts to fall down, okay? So this data generated a lot of interest. So many theoretical models were proposed to explain this somewhat surprising flavor asymmetry, and especially the X dependence of this flavor asymmetry. Here's a collection of partial collection of the theoretical models. I actually would like to emphasize that all these theoretical models, they can also have implications on how the flavor structure of the polarized C should look like. And in fact, they also have implications on the asymmetry between the strange quark and anti-strange quark C, which actually remain to be checked experimentally. So one very interesting theoretical model was a statistical model, and which actually can very naturally explain this quark flavor asymmetry. So as an illustration, I'm showing actually here, this is a workshop at Trento, actually we organized in 2013. So this was taken from the slides given by Jacques Sauveur. So I will not go into the detail. He was trying to explain why the statistical model can actually explain this flavor asymmetry, both for the unpolarized and polarized C. The bottom line is the following. In this statistical model, they are trying to make a connection between the flavor structure of the antiquarks with the flavor structure of the quarks. Okay. Therefore, by having some experimental input of the quark flavor structure, they can actually predict what is the antiquark flavor structure. And also in this model, they made a natural connection between the spin structure of the quark and the spin structure of the antiquark. Okay, so from this connection, one can again make predictions how the polarized C should behave. So they actually have some very interesting predictions here. Also in that workshop, this is what Jacques Sauveur showed, that he was showing the calculation of the statistical model versus the Fermilab EA66 data. So one can see that for the small X region, the calculation is in very good agreement with the data. However, at the largest X region, then the theoretical models start to deviate. Okay. So this is just reminding us, so he was actually emphasizing in his talk the importance of measuring the d bar over u bar at the large X. Okay. So, so this was realized by the experimentalists. So new experiments were proposed with spokesperson Paul Reimer and Don Gisman. So the previous Joyan experiment at Fermilab were performed using the 800 GeV. So the experimental bin lines is shown here as the red line here. And in fact, the experiment was performed in this region. However, the 800 GeV accelerator was no longer available. So for the new experiments, we actually used the lower energy of 120 GeV just from the main injector directly, shown as the yellow line here. So the beam was attracted to a different area. And in fact, the new experiment called the Sequest will have to essentially build a new experiments from scratch using some of the existing detectors. However, it's an entirely different experimental area. So it took some effort and time to actually get this experiment going. And so the commissioning started about 2012, and the data taking was completed in 2017. So I'm going to present some of the first results from these experiments. So as we'll know that the main motivation for doing these experiments is to determine the d bar over u bar. But when you use a lower beam energy, you can actually extend this measurement to higher X region, okay, in order to shed more light on how this d bar over u bar is behaving for the largest X region. The earlier measurement actually suffered from very poor statistics. So this shows actually the experimental data obtained from sequence. So this roughly about 50% of the data we have collected. So this half of the data have been analyzed and actually written up for publication. So this shows the dimuon mass distribution when we have the liquid deuterium target here. So the different color here correspond to our understanding of the various contribution to the dimuons events. In order to extract the Joule-Yang cross-section, which is with a mass cut greater than 4.2 GeV, we can see that there are some actually additional contributions. The red line corresponds to what we think that Joule-Yang contribution is. There are also the contribution from the target flask, as well as from the accidental backgrounds. Because the beam intensity we used for this experiment was quite high. It's on the order of 10 to the 12th per second. Okay, therefore the accidental rate is significant. So we actually, from using these single muons events, we can construct the accidental backgrounds shown in the green curve here. Therefore, when you add all these components, the data can be quite well explained. Therefore, one can extract the Joule-Yang using this decomposition method of the various contributions. Another actually interesting method was developed by the collaboration, which is to say that the accidental backgrounds should vanish if the beam intensity is approaching zero, okay, because there's no longer any accidentals there. Therefore, if you plot the cross-section ratio as a function of the proton beam intensity, which are shown as the red points here, you can then try to fit this experimental ratio here. And from this fit, you can extrapolate this cross-section ratio to the limits of zero beam intensity. So by definition, there should not be any accidental contribution there. So using these two methods, actually, we just observed very recently that they gave entirely consistent results, okay? And therefore, this is the cross-section ratio now obtained from these experiments, reported about a year ago by Jason Duff, okay, at the Deep Inlet Scattering 2019. This is labeled preliminary, but we actually have slightly different results, which is still consistent with this, which is being submitted and actually accepted for publication. I'm going to mention that status later. So this was presented at the Deep Inlet Scattering conference about a year ago. And this was in April. So I would like to show this email we received, actually sent to Jason Duff and myself by Jacques Sofer, actually, right after the Deep Inlet Scattering conference. We got an email from Jacques. What I did not realize was that Jacques was already very ill. He was sending this email from hospital. So he was very excited to see this results, and he sent us actually a plot in this email. So the plot he sent us was the following, that he was comparing the calculation of the statistical model, which was shown in this red curve here, with the new data we obtained, okay, from the sequence. And he was very happy to see that our new data can now be actually very well explained by the statistical model. So, we really appreciate all the interest and guidance of Jacques Sofer, and I would like to take this opportunity to pay my tribute to Jacques Sauveur, who passed away actually soon after he sent us this email. I would also like to update even though what I'm allowed to show here is only the preliminary results, but the final results actually have been written up and was submitted for publication. And it was just very recently accepted for publication in Nature. So I think the final result will be posted to the archive once we see the article in Nature. So as I mentioned earlier, that we are seeing also not only the Drell-Yan, but also the J-psi resonance. Therefore, a very natural question would be, what would be the cross-section ratio when you compare the deuterium with hydrogen, not for the Drell-Yan, but for the J-psi? This is an interesting comparison because we know that the Drell-Yan is an electromagnetic interaction process. Therefore, as we mentioned, it's sensitive to the quark and anti-quark distribution in the nucleon. On the other hand, if you measure this cross-section ratio for the J-psi, since J-psi is a strong interaction, it can actually proceed both by the quark-antiquark annihilation as well as the gluon-gluon fusion. So the Drell-Yan is not sensitive to the gluon distribution, but the J-psi production actually is sensitive to the gluon distribution. Therefore, it will provide actually the partonic information complementary to the Drell-Yan data. So this is, however, there is some difficulty because unlike the Drell-Yan, which has very well understood reaction mechanism, the J-psi production being a strong interaction still suffer from the fact that the production mechanism is not completely understood. However, it's all agreed upon, I think, by us that the main contribution of the J-psi production is illustrated in this diagram. So it's from the quark-antiquark annihilation, not into photon, but into a gluon, okay, and then which produce CC-bar pair, and then which hadronize into J-psi later. Or it can involve a gluon-gluon fusion, okay, as shown in this two diagram here. Therefore, for this reason, the J-psi production is sensitive to the gluon, okay, unlike the Drell-Yan. The relative importance of the quark-antiquark versus the gluon-gluon depends on the kinematics. So what's shown here is just an illustration that with our beam energy for the proton-induced reaction, then you can see that the red curve corresponds to the contribution from the gluon-gluons. So at the low rapidity region of the X Feynman is dominated by the gluon-gluon, but then at the high X Feynman region is dominated by the quark-antiquark now, okay. Therefore, we have analyzed, or the students have analyzed the J-psi data by doing this mass fit. So one can see that in addition to the Drell-Yan continuum, one can also extract in this purple curve here, the amount of J-psi, okay, for both the hydrogen and deuterium target. So based on this mass fit, one can actually obtain this cross-section ratio for the J-psi plotted as a function of the X target. So this is the ratio I showed earlier for the Drell-Yan. So one can see that it's quite different from 1 for the Drell-Yan shown in the red data points here. For the J-psi, which covers a somewhat different kinematic region of a small X target, the ratio is actually consistent with being equal to 1, okay? So this different behavior of the cross-section ratio for J-psi versus Drell-Yan actually is reflecting the fact that the J-psi production is more sensitive to the gluon process. Therefore, since the gluon in the hydrogen and deuterium are supposed to be very similar. So this is explaining why we're seeing these differences here.
Gentil, you have 1 minute, okay?
Okay, very good. I also want to show the nuclear dependence. So after all, our program started with the nuclear dependence at Fermilabs. Therefore, this new measurement actually allowed us to make some additional. So this was what obtained in the first experiments. It's restricted to very low X2 X target region. So with the new experiment, we hope to extend this to a higher value of the X target. So these are the results actually obtained by Arun, a student at Rutgers. So what one can see is that for this A dependence, the new data which extend to the larger X target for the different target different nuclear dependence. So this carbon over deuterium, iron over deuterium, and tungsten over deuterium. So, so for the overlapping kinematic region, they are consistent, but then they extend the trend to somewhat larger X value. Very interesting result actually was the following, that if you plot the nuclear dependence as a function of the transverse momentum, which is actually of great interest these days to see the transverse degree of freedom rather than not only the longitudinal degree of freedom, then one can ask, how does the nuclear dependence change as a function of the PT? Okay. So one can see that this nuclear dependence actually is quite dramatic. Actually, if you compare the tungsten over deuterium, the cross-section actually is increasing very rapidly as you go to higher PT. So, these are the new results coming from these experiments, and I think together with the previous data with the pion-induced nuclear dependence, I think one can probably get a very interesting pictures on the how this PT distribution is changing when you go to heavier and heavier target. So let me just, so I probably just want to show one more slide. I think the data analysis is still ongoing, and there are many other physics goals for the sequence that we would like to accomplish. Certainly, we would like to analyze the entire data sets. Okay. So at the same time, we're preparing for the next experiment, the 1039, the co-spokesperson Keller and Liu. So the main purpose, as probably many of you know, is to measure the Sievert's asymmetry. But when you use the proton beam, then it is complementary to the compass, namely that it will be sensitive to the Sievert's symmetry for the C quark now, for the up U bar and D bar. I just want to point out one thing very quick, which is that this is not mentioned in the proposal, but because of the experience from the compass experiments, we know that one of the single spin asymmetry here is also sensitive to transversity of the target. So if one would be able to extract this asymmetry, then this can provide very interesting new information on the transversity, not for the valence quark, but for the anti-quark now, okay. So this, I think, would be very interesting. So since I run out of time, I will skip the other topics, which is the possibility of measuring the exclusive Drell-Yan, which can actually complement the compass measurement and the ongoing JLab, and also the, yeah. So let me just show the summary slides. So the new results are becoming available for the diamond production experiments. Yeah, both the JSI and Drell-Yan from the sequence experiment at Fermilab. New experiments, I think, is underway, and we expect to start taking data later part of next year. I did not have a chance to mention this, but after so many years of the Drell-Yan, we have yet to measure a single exclusive Drell-Yan cross-section. So the opportunity of doing that, I think, is coming up actually with the high momentum pion beam line at J Park. Therefore, a letter intent was submitted there. So I think one can certainly expect more interesting physics result to come. Thank you.
Thank you, Genchi. Very interesting talk. And we are now open to questions. We have a question by Franco.
Hi, I'm really puzzled by the discrepancy between your measurement and the results of E866. The results are obviously incompatible. I mean, is there any reason found? Is there any problem in the 866 experiment or data analysis?
Yes, I'm sorry, I do not have the ability to show the latest plot comparing our results from the sequence with the E866. The comparison of the cross-section ratio is somewhat misleading because it's a different beam energy. Therefore, we are sensitive to different value of the flavor asymmetry when you change from one beam energy to another beam energy. However, it does not explain why, so that kinematic difference cannot explain why we are seeing this difference at the highest value of the X target. So this is why we are very careful trying to check whether the new results obtained here are reliable. So this is why we carry out 2 independent analyses. So far, we are confident that the new results here obtained are correct. But we are not ready to say that the old measurements from the previous 800 GeV measurements were wrong because we simply do not have evidence that we can find that would show us that those analyses were wrong. So I can only say that we are still trying to understand this difference, and we are not ready to say whether the old results we published have some problems, since we do not know what was the real reason between this. Of course, the very interesting possibility which we cannot exclude is that both are correct, and it's because of some physics that we probably overlooked, which can account for this difference. After all, we try to explore a region where the cross-section is very, very small. Therefore, it's possible, this is just my very wild guess, that it is possible that, for example, the earlier measurements perhaps is experiencing some contribution from additional process that we are not quite aware of. Anyway, I'm sorry, I cannot give you a very specific answer, but we are still thinking about this. Yeah.
Thank you.
Okay, and we have a next question by Oleg Denisov.
Hi, Genchi. What is a fraction of statistics you have analyzed for your last experiment?
Yes, right. So I try to mention. Yes, I try to mention that we have analyzed about 50% of the data collected so far. So we are in the process to analyze, to include additional data there for our final results. So the accuracy will be improved somewhat.
But not by a good factor. So that was my question. Was
yes, the statistics actually, unfortunately, it cannot give us a big factor. But as far as checking the behavior at the high X region, I think the additional data can certainly help. And also they were taken in a somewhat different setting of the spectrometer. Therefore, they also provide some helpful systematic check. For example, some chambers were added for the second part of the measurements. Therefore, both increase the spectrometer acceptance somewhat. And also it provides some additional tracking ability. So that can allow us to study the systematics in an improved fashion. Yeah.
Okay, thanks a lot. And just to not forget to remind people that we have as well very extensive Dralian program here at CERN, which will be done by under the umbrella of the AMBER experiment, which has got a recommendation for approval. So we were missing Dralian data for almost 3 decades, but now seems we just have this breakthrough, and we can expect a lot more data, Dralian data, in the next couple of decades.
Yeah, thank you. Thank you, Oleg, for mentioning that. I was assuming that that topic will be covered by other speakers, so I did not include that in my talk. Yeah.
Yes. Okay. So we have to proceed now, I think. Thank you again, Jianqie. And so, okay.
So
And
I stop sharing now.
Thank you. We proceed now with the talk by Oleg Heiser.
Yeah, hello. Let me just pull up the laser pointer. Yeah, thank you very much for the invitation and this opportunity to talk about the RIC Cold QCD program. So this is really a huge field to cover, and I hope to get through this in the time that I've been given. So instead of a long introduction, I just want to point out the 3 main pillars of the RIC Cold QCD program, namely the gluon polarization, the C-quark polarization, and then what's historically been called transverse spin effects, which actually covers a lot more detailed, smaller topics at this point, and all this has been written up in several write-ups over the last few years. I'm going to start with the C-quark polarization topic. Actually, a short overview first of the RIC facility. So this is an aerial view of the Brookhaven campus. You can see the RIC, the relativistic heavy ion collider, here in the background, 4 kilometers circumference, with the 2 big experiments, Phoenix and STAR. And the relativistic heavy ion collider actually, as the name suggests, is a very versatile heavy ion collider, which really started out as a gold-gold collider, but it's very versatile, both in terms of species. We have collided various species: copper, ruthenium, zirconium, deuterium, helium-3 with gold, and even asymmetric and at different energies. But for the purpose of this talk, I'm going to talk about the polarized proton program, where we have what we call the blue and the yellow beam. They're both bunched. One goes obviously clockwise, the other one counterclockwise. And we can collide at different interaction points, Phoenix and STAR, bunches with different polarizations. The initial stable polarization in the machine is transverse. So we have the transverse spin program, and we can use the spin rotators independently around the 2 experiments to rotate to longitudinal to have then helicity asymmetries. And this is just a summary of now almost 20 years of polarized proton collisions between 200 and 510 GeV center of mass energy, summarizing as a function of time that we ran each year, the integrated luminosity, and it also mentions the beam polarization, which typically sits at around 55 or 60%. And you can see the improvements over the especially last couple of years. Then just one slide about the experiments. So Phoenix and STAR, they have from the very start followed very different philosophies. Phoenix has focused on very high resolution electromagnetic calorimeters with a very, very high rate of data acquisition, complemented by a drift chamber for tracking and the central magnet, whereas STAR has this large acceptance central time projection chamber with a 2π acceptance between -1 and +1, which is then surrounded by electromagnetic calorimeters and supplemented by an NCAP calorimeter, which extends this out to a rapidity of about 2. And then both experiments have these global detectors, beam counters, 0-degree calorimeters, and both also at one point or another had these forward electromagnetic calorimeters in the region between 3 and 4 in Phoenix in both beam directions, and STAR only in one beam direction between 2.5 and 4. I'm going to show some of those results. So the first topic that I just briefly want to touch on is the C-quark polarization. That's already been a year old at this point, but I think it's very important because this really is the conclusion of the initial W program from the RIC spin program. So it covers the years 2009 through 2013. And this slide really summarizes now the world data that we have from proton-proton collisions at 500 GeV, where we measure the single spin parity-violating helicity asymmetry and W production. And what STAR has measured was the electronic decay in the barrel and NCAP region. So the results here show for W minus and W plus the AL asymmetries. And Phoenix has measured in the very mid rapidity with their 2 arms, the electronic decay asymmetry, and then also the muon program at forward and backward rapidity with slightly reduced statistical accuracy. But this now is the world data set from PP collisions published 2018 and 2019, and the impact studies already show how much improvement we expect from the C-quark asymmetry, the delta U bar minus delta D bar, and then PDF Pol 1.1, you can see from the green to the blue the impact that the RIC data actually has on this measurement, on this property. The data also has been used for studies of the flavor composition of the sea, and this really ties into what Jianqi just showed. This is a different version of the plot that he showed in his talk, where you can see the new sequest preliminary data. And the RIC data, the W plus over W minus cross-section ratio that we can extract from the data, in this case from the STAR experiment, between -1 and 1.5, really fill in a region between 0.1 and 0.3 in X here that will complement the existing data. So this is from runs 2009 through 2013. A publication of this is currently in preparation, but there's additional data of about the same luminosity on disk already that has been analyzed, and the results of this are expected very, very soon. And this can also be used to analyze this as a function of the, so this is as a function of the electron rapidity, but with the full reconstruction that has been developed for the transfer spin asymmetry. This can also be shown as a function of the W rapidity itself. Another measurement in that context, which is interesting, I guess Alessandro has talked about this in the morning a little bit, is in terms of unpolarized TMDs, where we can look at the Z0 differential cross-section as a function of PT, which is experimentally very, very clean. And as I mentioned, also fills in between X between 0.1 and 0.3, and nicely adds to the world data that we have from the LHC Tevatron and fixed target experiments. So then the second big topic, the original RIC spin topic, I think you can call it, is accessing the gluon polarization. So these are all double helicity asymmetry measurements at various collision energies, 200 and 500 GeV. I won't go into much detail here about how we actually get to the gluon polarization from this as a function of PT. We can talk about this later if there are questions. Just a brief mention about the observable here, this double spin asymmetry, this double helicity asymmetry needs input from the beam polarization, as I said, between 55 and 60%. So that's also one of the largest systematic uncertainties, is the beam, the uncertainty of the beam polarization. And then we need to know the residual transverse polarizations from the spin rotators, which has to be measured, and the relative luminosity, which needs to be very well known. This observable is on the order of 10 to the minus 3 or 10 to the minus 4 maybe, so that the relative luminosity really needs to be on par with that. And overall, we match this very well from comparison of rates in different detectors, BBC vertex position detectors, or 0-degree colorimeters, and others. So this slide is kind of old news, but I think it's always the starting point that we should talk about or should be aware of, that the gluons are actually polarized in the proton, which mostly inclusive jet asymmetries from star at 200 GeV have shown this data from 2009, when this was included in the first global analysis of CITES, DIS CITES data and the RIC ALL data. It really showed that there is a non-zero polarization of gluons in this limited range between 0.05 and 1 of gluon X, and this has also been shown in a different global analysis from the NNPDF group in a somewhat different range, but still a significant 3 sigma non-zero gluon polarization. So the question now is, how do we improve on this measurement? And there are a lot of inclusive measurements from Phoenix mostly, but also from STAR, where we have the J-psi asymmetries at 500 GeV. The jet asymmetry, the Pi-zero asymmetries, excuse me, from Phoenix at mid rapidity, the charged pion asymmetries that have very recently been published, which actually allow you a more direct measurement of the sign of the gluon polarization itself, and then also recently this isolated direct photon measurement, which admittedly has still fairly large uncertainties, but the asymmetries are also expected to be quite sizable, I would say. The flagship really goes back to the jet asymmetries, and this shows you the inclusive jet asymmetries at 500 GeV. So this is a higher energy than what was originally included in that global analysis. And you can see how this can be related if we measure this as function of the parton of the jet PT, how this can be related to the X of the parton that's that in this case would be the gluon X, how we can access the functional form, if you want to call it that in this case already. So the impact here is rather limited. We can increase the energy to get to lower X, but where it really takes off if we look at dijets, because in that case we have access to both rapidities of the two jets, and we can more or less restrict or constrain the X1 and the X2 of the two colliding partons. And that really allows us to scan in more detail through the functional form itself. So this is the first dijet asymmetry at 200 GeV that was, excuse me, that was published in 2017. And then we can also look at the extended acceptance that the star barrel actually has, where we have the TPC at the mid rapidity, which is the blue region here, but then we also have the end cap, which goes from 1 to 2. And we can combine the jets in different topologies. So we can have a backward jet combined with one that sits in the end cap. We have a moderately forward jet combined with one in the end cap, or we have both jets in the end cap. And you can see how this really changes the X1 and the X2 of the two partons that collide, and how you can really scan into the low X region of the one proton in this case. And you can see the data here with statistical and systematic uncertainties, how it compares with theoretical expectations, and how this will actually then improve the measurement. Then last year we had the first publication of the dijets at 500 GeV. This only includes the central barrel, so this does not include the end cap, as I've shown on the previous slide, but the improvement, the increase in the center of mass energy already allows you to go to lower X already, as I mentioned before. So we have, actually in this case, we have the forward and backward rapidity regions, so positive and negative rapidity. We have the mid rapidity here, and then a combination of forward and backward, which kinematically is about the same as the mid rapidity in this case, but the partonic cross-section or the partonic asymmetry is slightly different. So this is why we split this in two different bins here, where the theory curve actually changes slightly from one to the other. So they're different measurements. And I should also say that all of these jet measurements now are fully corrected for the underlying event, and then they're corrected back to the partonic level. And then I think this is the concluding slide on the gluon polarization, or the second to last, I should say. These are recent results from 200 GeV. This is from the 2015 data, which improves on the 2009 data, the original measurement. So these have just been very recently released at the users meeting. It should have been this summer, but it was this fall in an online virtual meeting. You can compare the previous measurement with the improved measurement with improved figure of merit and improved systematic uncertainties, reduced systematic uncertainties for different rapidity ranges here. And on the right side, we can also see this new result for the dijet asymmetry is very consistent with the previous measurements, although that's always a kind of weird statement because it essentially tells you that the previous measurement with the worst statistics is in agreement with the new measurements. But they agree very nicely and should have a nice impact on an upcoming global analysis. The 200 GeV result at this point is in preparation for publication, and I should remind you there's also still 510 GeV data on disk where we have seen partial preliminary results before, and we should expect the final results from those very, very soon. One short statement on forward asymmetries. These are pion asymmetries from STAR in this forward calorimeter at 500 GeV. The statistical uncertainty here, if you compare the results with the theoretical expectations, is rather limited, but it will still have some impact on a global analysis. And the nice thing about this measurement, if you go that far forward, is that you actually reach much lower X values, down to 10 to the minus 3 in this case. So for the remaining time that I have, I want to focus on the transverse spin effects, and this will specifically talk about the transverse spin structure of the proton, but also the multidimensional landscape of nucleons and nuclei in terms of TMD functions. So I don't want to linger on this slide too much, just a brief statement about these huge transverse spin asymmetries that we have known to exist in proton-proton collisions over the last now, I think, over 40 years, starting at 5 GeV all the way up to 510 GeV for charged pions, neutral pions, asymmetries up to a range of 40% or so, pretty independent of collision energies. And these measurements actually have triggered a lot of theoretical interest and a lot of speculations in the early days of RIC, but you really have to be careful when you talk about PP collisions, what you measure and what you want to extract there. So you need to know what observable you're actually looking at in terms of a transverse momentum dependent observable where you need 2 scales, or you have a twist 3 observable where you only have 1 scale. And the right side here shows how the RIC data if you're able to really extract a TMD observable, how this really nicely complements the world data in terms of CITES fixed data measurements with Drell again proposed measurements from RIC and the mid-rapidity jet measurements from STAR, proposed forward jet measurements and partially existing now forward jet measurements from STAR and the W program here at very high Q² values. So more of a stamp collection again. Yeah, I apologize for this, for the inclusive measurements, which really summarizes a lot of the measurements from the Phoenix experiment in terms of single muons, which have fairly large statistical asymmetries, but if you could improve on this, the expectations or the theoretical projections really point to possibly pretty large asymmetries that you can pick up there. The historical flagship from Phoenix, I think the Pi0 measurement was the very first measurement that they published in this case. These asymmetries are consistent with 0, and they're so precise that even if you blow up this low PT range, you barely can make out the statistical uncertainties, which is related to a gluon twist 3 correlator. This has also been measured in PA collisions now, also consistent with 0, similar measurement with eta mesons, and you can look at the jet asymmetries at mid-rapidity, also consistent with 0 here. A more recent release, the direct photons here from Phoenix from this summer, with at mid-rapidity. Admittedly, again, the uncertainties are fairly large, but this really shows you that the expected asymmetries are not that far off from the uncertainties at this point. So there's ground to be made, I think. And then moving on to really TMD measurements, where we, as I said, have the 2 scales that we need for this observable, which is a hadron asymmetry in a jet. So the PT of the jet gives us the hard scale, and the JT, which is the relative PT of the hadron with respect to the jet axis, gives us the soft scale. You can look at different asymmetries in this case, different modulations where you have the polarization and the hadron in the jet. One of this is a combination of the Collins TMD with transversity, and there are other Collins-like asymmetries which relate to the linear gluon polarization, which really was the first measurement of this data of this function at all. I'm not going to show this, but you can look this up in the publication that I have here, because this is already from 2018. What I want to point out here, this is the measurement that you probably know, where we have the 500 GeV hadron and jet Collins asymmetry measurement as a function of Z, with the theory predictions for pi plus and pi minus in the jet, which agrees fairly well with the predictions. That has been a preliminary with improved statistical uncertainties at 200 GeV from 2012 data, but we now have a very recent addition here, new data from 200 GeV from 2015 already, where you can see these much reduced statistical uncertainties for the pi pluses and the pi minuses, many sigmas away from 0, even though the asymmetry here is only on the order of 1%, both in forward and backward XF ranges. This has been calculated for charged pions, but it's also completely separated from kaon asymmetries, and proton asymmetries have been shown. I'm not sure if they will be included in the publication that's now in preparation. So then we can go forward. And
Oleg, you have 1 minute. Okay.
Yeah, I'm going to speed up. At forward rapidity, we don't have the tracking information, but we can look at Pi0 asymmetries in jets, and this has been recently released. There's also a publication in preparation right now for the Collins asymmetries of pi zeros at this forward rapidity range. It's very small, consistent with zero. And the theory uncertainties here are fairly large, so it will have a nice impact also. This has been used also to look at jet asymmetries, which are consistent with previous results, namely the Andy measurement at 500 GeV. So there's no big surprise here, but a big improvement. And then you can also look at the pi zero asymmetries themselves, which really go back to what I started the section with, which are large asymmetries and are still not understood where they really come from. And you can look at this as a function of the isolation of the pi zero in terms of how related this pi zero might be to a jet or not a jet. And you can see that the isolated asymmetries are a lot larger than the non-isolated asymmetries. In this context, I should point out that there was a recent publication from the Rick F. collaboration where they looked at very, very forward pi zero production with their calorimeter eta larger than 6, and this really goes down as a function of PT to be consistent with zero. I think what most people would have liked to see in this talk is the question of non-universality of the Sivas function, where we look at the W boson single spin asymmetry, tensor single spin asymmetry, and these plots I'm sure I've seen many times before are the projected uncertainties. Unfortunately, the result is not quite ready yet, but there has been huge progress in the last few months in terms of understanding the detector and possibly understanding the full reconstruction of the W itself from the recoil in the detector. Another nice measurement that has recently been released is a Sivas asymmetry that can be looked at in dijets, where we really look at the back-to-back jet production and then try to pick out a KT, a transverse kick in the back-to-back jets, which then is related back to the quark flavor by charge tagging. So that's a very detailed study that has been done here. We would expect the asymmetry to be very different as a function of the total eta of the two jets. And the measurement somewhat confirms this. If you look at the average KT for U quarks and D quarks, you see that there's a big, very significant difference in the two. The J psi production UPC, just one word, it's one way to look at the GPDE. In PP collisions, the takeaway here is that we have a measurement which is consistent with zero. If we want to use this in the future, we need to first improve the statistical uncertainty, which is quite large, and then go to a lower invariant mass here, where the asymmetry actually is expected to be quite a bit larger than where we currently sit here. And then one word about nonlinear gluon dynamics, which goes beyond the polarized PP program, which is a new measurement, a new release that we've seen this year, where we look at forward rapidity dihadron pi zero correlations in PP and P gold collisions. And we look at a high PT pion, which is a trigger, and an associated pion at lower PT, the back-to-back correlation, and then we can look at the width and the area of these correlation functions, and we see that there's actually a suppression if we go from PP through P aluminum to P gold, which really suggests that there is a regime of nonlinear gluon dynamics that we end out, namely a gluon saturation regime. More details about this, if there are questions, you can ask about it. And then I think I should just wrap up here. There are plans currently going on to build a star forward detector upgrade, which should be ready for data taking by the end of next year. So that would be run 22, which hopefully starts in very late 2021 or early 2022, which consists of different stations of trackers and electromagnetic and hadronic calorimetry at the fault rapidity range between 2.5 and 4 in eta, which really allows us to improve on measurements that we've made at the mid rapidity in the fault region, or improve measurements that we've done in the fault region with different observables. And a lot of these go back to results that I've shown throughout the talk. Here are a few other projections that I unfortunately don't have the time to go through in detail, but you can ask about this if you want to. So I'm going to conclude here with the summary. RIC data at mid and fault rapidity has really made significant impact on our understanding of the gluon polarization, the C-quark polarization, and transfer spin effects. Upgrades that we're currently building to these existing facilities are important. There's a RIC run scheduled for 2022 with transversely polarized PP collisions at 510 GeV. And then hopefully in parallel to S Phoenix, we will also get some data with PA collisions, P gold collisions, excuse me, at 200 GeV. So these measurements will be complementary to and will also inform the experimental requirements for the future electron-ion collider, which I think we're all very excited to see in the next 10 years or so. Thank you very much.
Thank you, Oleg, for this very complete talk. I believe we have a question by Franco.
Sorry, I had forgotten the hand raised.
Ah, okay, but then we have a question by Oleg Denisov.
Hi, Oleg. What do you mean about your what is projections for your perspective about the Sirius W, the asymmetries in terms of astronomical time?
I can give you my personal opinion on this. This is a RIC talk, so I can't really talk about the star internal deliberations, but I'm one of the main analyzers of the data, so I think I'm allowed a personal opinion here. We have seen the asymmetries. There are some things that still need to be checked because they don't exactly look like what we maybe wanted them to look like, although we should not want them to look like anything. One of the big problems was that the calorimeter calibration needed a lot more TLC than had initially been expected, and that went back to the TPC calibration and how the tracks were actually reconstructed. So that has been solved. The calibrations are in very good shape right now. The other issue that I see right now is that the full reconstruction of the W's might introduce some uncertainties that we haven't seen in the previous data from 2011, just because of the statistics that we have now. So that needs a little more studies, and if everything else fails, it might need a different analysis procedure.
Because
in terms of astronomical time scale,
because I got the impression that you have a deal with our Drell-Yan analysis group, because after first year of Drell-Yan data taking, we have published a result after 1.5 years. Now we are 3 years away from our second Drell-Yan data taking year, and we have published only result for the 50, not even published. Well, we release results from 50% of our data. Did you make a deal between your W analysis group and our Drell-Yan to publish the result in the same time? So this is why I wonder when it might happen.
Well, I think that I don't know if I can't see the participant list. I don't know if Bakur is on the board. I think the deal that we had last year was that we wanted this out by this year, early this year, and it hasn't happened. So I don't think there is a deal. No.
Take it as a joke, but as a push as well to our Julian group, because
yes,
I understand your problem because you have really much larger statistics compared to your first run, and we have a comparable one. So please.
Okay.
Katerina, I have involved you, certainly, you know.
Yeah, I feel the pressure. I can personally, I know. From all sides.
Thanks a lot for both of you.
Okay, so we thank again to Oleg, and I think we need to proceed now. So next we have Benar Mulilo. Hello, Benar.
Hello, I'm just sharing the screen.
Yes, you are sharing not the talk, I believe.
Okay, sorry. Let me just do that again.
Okay, now we have it.
Yeah, sure. Okay. Are the slides visible? Hello?
Yes.
Yes, yes.
Okay, thank you very much. So I want first of all to thank the organizers for giving me this opportunity to talk at this conference. So on behalf of the Phoenix collaboration, I would like to present the Phoenix preliminary results of forward neutron transverse single spin asymmetries in inclusive triggered transversely polarized proton-proton collisions at the center of mass energy of 200 GeV. The talk is outlined as shown in this slide, starting with a brief introduction, forward neutron cross-sections, and then transverse single spin asymmetries. And then I'll talk about the neutron detection system at Phoenix, the unfolded asymmetry extraction procedure, Phoenix preliminary results, and then I will summarize the talk. So forward neutron cross-sections in proton-proton collisions have been studied at CERN using the intersecting storage ring, and also at Phoenix using the relativistic heavy-ion collider. And what we see here are differential cross-sections as a function of X Feynman, studied starting from the lowest center of mass energy to the highest center of mass energy at ISR. And then the cross-section results were also reproduced by Phoenix, even at higher center of mass energy equal to 200 GeV, using two different function forms of the transverse momentum, that is exponential and Gaussian, that were used at ERA and ISR respectively. All the results show the differential cross-section with a peak at very high X Feynman, indicating that the forward neutron carries a large fraction of the proton energy. These cross-sections were well explained by theory using the one pion exchange model, in which a pion is exchanged between the interaction of two protons, producing neutrons with a spin flip. Phoenix went further to extract the neutron transverse single spin asymmetry using the one pion exchange model, and they calculated very large negative asymmetries at different center of mass energies of up to 500 GeV as a function of the transverse momentum. But then the problem was that using one pion exchange model, the asymmetries are not so large as was observed by Phoenix. So where did the large fraction of the asymmetry come from? Well, theorists then gave us the answer that this might have come from the spin parity +1 A1 2060 region particles, and that these asymmetries in proton-proton collisions are produced by the interference of the spin flip, as in the case of pion exchange, and the spin non-flip, as in the case of A1 region amplitude exchange. This model is known as the Regge model. And when theory was compared with Phoenix asymmetry data, which was unpublished, and the data was not unfolded, we saw some good agreement between theory and data here. So we've continued with this study of asymmetries as a function of transverse momentum in proton-proton collisions by making sure that we unfold the data due to reasons that I'll look at in the following slides. So as Oleg just pointed out, this is the layout of the relativistic Kevarine collider at RIC at Brookhaven National Laboratory in the United States. So the two beams are circulating clockwise and counterclockwise, kind of collide at different experimental setups here, our interest being Phoenix. And the Phoenix central detector is shown on the right-hand side. So we just focus on the forward neutron detection system here, which are 0-degree calorimeters, ZDCs, which are schematically shown in this figure here. So we have two beams which are circulating clockwise and counterclockwise. We have the transversely polarized proton beam traversing from the south arm of Phoenix to the north arm of Phoenix. And then we have the yellow beam, which in this case is the proton beam traversing in the opposite direction. The two beams then collide at Phoenix, and forward neutrons at pseudo rapidity greater than 6.8 are measured and get detected by the 0-degree calorimeters here, which are made of copper tungsten alloy and comprising 3 ZTC modules here, ZTC1, ZTC2, and ZTC3. We expect that maximum hadron shower will take place in the second ZTC. So we place the shower maximum detector between CTC1 and CTC2 to be able to detect the neutron position with a positional resolution of roughly 1 centimeter. The other important observable here is the energy of the CTC. So the energy resolution is roughly 20% for 100 GeV neutrons. And the acceptance of CTCs is only 5 centimeters in the transverse plane. So we see that the acceptance and the resolution are very limited. And therefore, we expect that measured variables such as transverse momentum, position, azimuth are considerably smeared due to this limitation here. So we've got to kind of correct for this smearing in transverse momentum when we calculate asymmetries. So we try to unfold the asymmetries as a function of the transverse momentum in order to take care of this smearing effect induced by the ZTCs. So to get the transverse single spin asymmetries of forward neutrons, we first ensure that we have high neutron purity, and the basic selecting criteria was according to these important 3 cuts here. We first required that the ratio of the energy deposited in the second CTC to that of the total energy be greater than 3%. This is for photon elimination, because we expect that most of the photons will have been stopped in the first CTC as they are electromagnetic in nature. So the total energy is calculated as the sum of all the energies in CTC1, CTC2, and CTC3. So we just get 40 to 120 because the energy resolution for 100 GeV is about 20%. Then we also require the acceptance cut of 0.5 to 4 centimeter, which correspond to the inner and outer radii cuts, with the inner radii of 0.5 centimeter being to counteract the left-right dilation at the center. And then we require the 4 centimeter, which is used to reduce neutron edge dilation as we get close to the edge of the acceptance of the CTC. Then we finally eliminated, if not almost, all photons by applying this SMD threshold cut of 0.003 GeV by requiring that the number of SMD scintillators firing in the horizontal and vertical direction be greater than 1, firing above this SMD threshold energy. So the first thing in the unfolding business was to try and get the smearing response metrics for the 0-degree calorimeter. So this is quite technical here. So we are trying to correct in transverse momentum and azimuth, which is a 2-dimensional problem or histogram problem. But when we use SVD, singular value decomposition, we only need 1-dimensional histogram. So we kind of map the 2-dimensional PT cross phi to 1-dimensional PT phi index by applying this relation here, where I is the 1-dimensional PT phi index, which is simply equal to the product of the ith PT and the number of phi bins, then plus the ith phi. Then this way, we're able to get the smearing response matrix, which was obtained as the generated PT phi index, plotted as a function of PT phi index reconstructed. As we can see here, the elements are not perfectly diagonal, so there's considerable smearing here, which has to be corrected. So we applied now the singular value decomposition of this response matrix to correct off diagonal smearing in transverse momentum as well as azimuth. Continuing with the unfolding procedure, we first obtained the spin-dependent 2-dimension data used not only in transverse momentum, but also the azimuth angle. And then we try to execute the unfolding via TSVD in sense route using the reweighted smearing matrices, which has just been talked about in the previous slide. Then asymmetries were finally calculated using the relative luminosity formula shown on the right-hand side here, with P being the average beam polarization and Y plus minus as a function of phi here being the neutron fields observed to the right and left respectively. And then we have the luminosity, which is unity here, and AN are the calculated asymmetries. Then for the systematic uncertainty studies, we utilize 5 different Monte Carlo generators, many of which were hadronic in nature, as we expect in PP collisions. And we also tried to sample the electromagnetic one just to check if there were remnants of electromagnetic showers using UPC. The smearing matrices that were used for decomposition using SVD were reweighted by using 3 different function forms. That is a polynomial 3rd degree, power law, and exponential functions, with here lambda pi being the phase shift, with lambda being the spin up and spin down. And then we have A, B, C, and D, which were free parameters that were valid in order for us to obtain the minimum chi-square between the experimental and reconstructed asymmetries. So the minimum chi-square was obtained in this way. Then we just look at some Phoenix preliminary results that we got so far. So this is based on a polynomial of third degree reweighting. These are shown as unfolded asymmetries as a function of the transverse momentum, with the observed asymmetries shown in blue, while the corresponding unfolded asymmetries using the polynomial 3 are shown in green. The boxes depict the systematic uncertainties, which are simply root mean square ranges of all unfolded asymmetries in each transverse momentum bin, using polynomial 3 for each of the generators that were used: DPMJ, Pythia 6, Pythia 8, OPE, and UPC. The light green shaded—
2 minutes.
Yes? Sure.
2 minutes.
Yeah, sure. The light green shaded region shows chi-square below 10, and chi-square is small below 0.2 GeV and large above 0.2. In this slide, we saw the unfolded asymmetries as a function of transverse momentum based on the power law function. The observed ones are in blue, while the unfolded ones are in yellow. Once again, the boxes depict the uncertainties arising from using power law for each of the Monte Carlo generators. We also observed the unfolded asymmetry as a function of transverse momentum based on the exponential function. And the unfolded asymmetries here are shown by these red crosses. The boxes are RMS ranges, and the shaded region shows chi-square below 10 units. We then got a combined result with total systematic uncertainties for all 3 parameterizations here, that is polynomial 3, power law, and exponential. These are unfolded asymmetries as a function of the transverse momentum. So the black data points show the unfolded asymmetries obtained from the average of all parameterizations. And the boxes now depict the total systematic uncertainties arising from the unfolding procedure, MC generator, and parameterizations. So as we can see here, so far, the trend of these asymmetries are such that they tend to slowly increase at low transverse momentum. And then at high transverse momentum, they kind of level off up to about 0.2 GeV per C. So just to summarize my talk, the Phoenix experiment has measured the first explicitly unfolded transverse momentum dependent single spin asymmetries of forward neutrons in inclusive triggered transversely polarized proton-proton collisions at the center of mass energy of 200 GeV. The first reliable test of mechanisms that produce these asymmetries can be performed using this measurement. I think for theories, I think that would be good. So trend-wise, the unfolded asymmetries appear to slowly increase at low transverse momentum and leveling off at high transverse momentum. This kind of trend seems not to follow a simple linear transverse momentum theoretical prediction, which is given in this paper here by Kopeliovich and others. I showed this on slide number 4. And just to wrap up my talk, the preliminary results are currently being finalized and the paper being prepared for publication, I think within this year or early next year. So that said, I would like to end my presentation here. Thank you very much.
Thank you, Bernard. So we can now have questions. I am not seeing any raised hand. Okay, it seems there are no questions.
Sure.
Thank you again. Thank you.
Thank you very much.
So we proceed directly. We have some delay already accumulated. We proceed directly to the talk with Marco Radici.
Okay, let me. Can you hear me first of all?
Yes.
Yeah.
Yes.
Let me share the screen. Okay, can you see that?
We see, yeah.
Okay. And let me start the presentation. Okay. So good morning, good afternoon, good evening to wherever you are. So I'm going to talk about the latest news on transversity and Sieverts functions about the extraction of these objects. Actually, when I was preparing this talk, I realized that I gave a talk with a similar title early this year in the beginning of February in the workshop organized by Bakur at CERN. And I realized that that was my last trip to a workshop before the strict lockdown that Italy entered, as you all know, in February. And since then, many new developments appeared in the literature, so research have progressed despite the COVID. Some of these results are driven by the preparation of the yellow report document of the EAC, and I take the opportunity to just advertise that in a few days, and on Thursday, we will have the fourth and last workshop of the series. And here I put the Indico address for your convenience. Okay, so transversity and Sieverts. These objects sit in the bottom corners of the famous TMD table at lead and twist. I think they can be considered as a sort of prototype of the exotic parton densities, in the sense that prototypes of the class of Carolod structures on one side and of naive time reversal of the structures on the other side. And if you go back to the white paper, EAC white paper, almost 10 years ago, basically, and these functions were nominated the gold and the silver channel of the EAC. And I think this message is still valid nowadays. And according to this ranking, let me start saying something about an update of the situation about the Sieverts. So there are two very good reasons why we want to run after the Sieverts. The first one is related to his naive time reversal of the nature, and it's predicted non-universality. So you know that if you in other words, if we extract the Sieverts from a semi-inclusive DIS process, and we do the same in a Drellian process with transversely polarized protons, we are going to get results that we are one the opposite of the other, just because the color flow in the color interactions is opposite if you consider the final state interactions in semi-inclusive DIS or the initial state interactions in the Drellian. We just heard from Oleg that the new data will come out. And also this is a very promising field for to understand and confirm these very important predictions, and that should confirm our understanding of the QCD structure. Okay, so the second good reason is the relation between the Sieverts function and the quark angular momentum. We all know that through the G-sum rule, the total angular momentum of a quark is given by the second Mellin moment of the forward limit of the GPD H and E. We know that this forward limit of the GPD E is unreachable, and in models you can relate it to the KT moment of the Sieverts function, for example, through the Lansing function model put forward by Burkhardt many years ago. And therefore, if, by fitting data from the Sieverts, one can guess numbers for the total angular momentum of quarks and do the exercise and compare with extractions using GPDs or lattice calculations. Okay, so there is a long record of extractions for the first KT moment of the Sieverts function as a function of X using semi-inclusive VIS data. Now, in this year, we have seen a sort of turning point. Alessandro already mentioned that this morning. Work by the GEM collaboration was published where they basically construct a global fit of all data for semi-inclusive single spin asymmetries coming from the Sievers or the Collins effect by including in their fit data from semi-inclusive DIS, Drell-Yan, W and Z production, and E plus E minus. So this is a very tremendous effort, very important. Now, the theoretical framework, however, is a bit outdated, I would say, because the KT distribution of the TMDs is still factorized and described by a Gaussian function, which is unaffected by evolution. And even if we know that this approximation works reasonably well in semi-inclusive DIS process because of the range covered by the in Q squared is not very large, it's certainly questionable if you compare with data from Hadron colliders, I mean Drell-Yan or WZ production data, because the scales there are very different. Anyway, in this work, basically they managed to fit a lot of data, so more than 800 data for the unpolarized multiplicities entering the denominator of the spin asymmetries, and more than 500 data for the polarized part in the numerator after applying the usual cuts induced from semi-inclusive DIS considerations. In particular, for the Sievers effect, we have 126 data plus this set of data from the Drell-Yan measurements and the WZ production. And actually, maybe one should be careful in dealing with this data, because this is the total data published, which are projections of the same data set in, using these different variables. So for example, XF or QT or X of the beam or X of the target. And therefore, not all of these data are independent. So one should reconsider the estimation of the chi-squares per degrees of freedom in this analysis. And also another weak point of this analysis is that the completely unconstrained TMD of the pions in the Drell-Yan process is just taken fixed equal to the TMD of a proton, which is quite questionable assumption. Anyway, apart from this, this is the result that you can take. I took from their paper. You see the first KT moment of the Sievers function multiplied by X as a function of X for the up quark and the down quark, compared with two other previous parametrization. I will come back to this plot later. Let me first come to the next result that appeared in the literature early this spring. This work done from our group in Pavia. And this is an attempt of extracting Sievers function from semi-inclusive DIS data, but in a full TMD framework in a sort of consistent way. Consistent means basically that we are using the same framework for describing the denominator, the unpolarized cross-section, and the numerator for the polarized part of the cross-section. And actually, we are using even the same ingredients, in the sense that we started from our extracted unpolarized TMD parton distribution and fragmentation functions from our global fit of 3 years ago. And we built our starting parametric function for the Sievers, just building on top of the parametric function using the unpolarized analysis, and with the same expression, and just introducing some further parameters, and then evolving our parametric function at the next to leading log level up to the scale of the data, the higher scale of the data, and checking that positivity bounds at each step of the evolution. As I said, we consider only semi-inclusive DIS data, but we took only the set of single spin asymmetries as function of X, since we are looking at the KT moments as a function of X. So we didn't include all the projections, which are not all independent. And after applying the usual semi-inclusive DIS cuts, we got something like a little less than 120 data that we fit with 14 parameters, reaching a very good chi-square per degrees of freedom on average. Okay, let me show directly the results. Here you see again the KT moments for the up and the down quark as a function of X. Our result is this green band for the up quark, and here for the down. And it's compared with some recent extractions. For example, the yellowish bands that you see here are coming from the work of the Torino group. And if you look at the red band here and here, this is the result of Miguel Echevarria, Idil, Bikang, and Bitev. And the blue band is our old attempt almost 10 years ago using the lensing function that I was mentioning before. Now, you see here below, again, the results from the GEM collaboration. And just to guide the eye in the comparison, just look at this green dashed line here. Is the same as the red band here above. Is the result of Echevarria, Idil, Bikang, and Bitev. You see that for a half quark, we basically have an overlapping result with them. So our band basically would lie here in this plot. And therefore, we have a peak in the up Sivers function, which is larger than the one obtained by the GEM collaboration. While on the down, you see the dashed line here lies here, and we are much higher than that, almost twice higher in the peak, and therefore we are definitely higher than the extraction of the GEM collaboration. Okay, but this is okay. Like you can download the slides and have a closer look to them. Okay, this is the money plot that already Alessandro showed out of our extraction of the Sivers function. This is the distribution of the probability density of up and down quark, up on the left, down on the right, inside the proton, which is traveling towards you out of the screen. So if the proton is not polarized, you basically see a perfectly cylindrically symmetric distribution around the direction of motion. But if the proton is polarized along the vertical direction, the y direction, then you see the distortion induced by the Sivers effect. And this effect is completely induced by data without any model assumption. Okay, so very recently, 2 months ago, another parameterization was released of the Sivers function. This is, again, a global fit of semi-inclusive DIS, Drell-Yan, and WZ production data. And it is performed in a full TMD framework now, and the analysis is quite sophisticated. They have corrections. The hard part is described up to the next leading order, and the evolution is treated, the summation of the radiation is treated the next to next leading log level. I don't want to run a spoiler of the next speaker. I think that John Terry, the talk after mine, will describe in detail his work. Let me just remind and stress again what already Alessandro said. The most curious result of this analysis is that if they just included the Drell-Yan data on top of the semi-inclusive DIS one, they get Sivers KT moments of the Sivers function, which are very similar to the ones that we get in other extractions. But if they include the W and Z production from STAR, then they run into troubles. As you see that all the replicas of their fit go crazy. The average is squeezed for the valence down and up quark, and the C quark is enhanced. So there is something to be understood here. Actually, let me anticipate some questions to John that on top of this, and I'm wondering what happens to positivity for the Sivers function here in this plot, in these conditions. And also in their analysis, they are also using the whole set of data for the Drell-Yan and the WZ production. And this data set is not all independent, of course. The same problem is the GEM collaboration. And also it's not clear from the paper what do they do with to describe the TMD or the pion and for the semi-inclusive single spin asymmetry in the Drell-Yan case. Okay, let me move quickly to a new method. You know, with the advent, with the future EIC, there is an advent of new techniques. And basically, the idea is to use jets to study the TMD structure. And for example, you can study the Sivers effect just looking at azimuthal correlation between the electron and the direction of the jet. And I think that Ignazio Cimei will talk about this on Wednesday. So I do not spend much more time. Just let me show this simulation of the Sivers effect using the parameterization of the Echevarria, Idil, Bikang, and Bitev, the EIC kinematics. And you see here the projection of the uncertainties of the EIC, which is will dramatically reduce and select theoretical results, and also will allow to explore the Sivers effect at very low values of X, also in the C quark regime. Okay, so I think Alessandro spent some time also explaining how many data are upcoming, basically. So from COMPASS, of course, but also from JLab 12 about the Sieverts effect. We have simulations of very promising results coming both from class and from OLE through the solid spectrometer. I think that Patrizia and Hayan will describe these things tomorrow. And there is also the whole world of the gluon Sieverts problem, extraction of the gluon Sievert, and select which are the best candidate channels for doing this. And I think that Daniel tomorrow will illustrate this problem. I move quickly to the transversity now. This is the transversity sits in the bottom right corner of our map. It is, you all know that in a proton, so in speeds 1/2 object, the transversity is a non-singlet, typically non-singlet object because there is no contribution from the gluon due to the mismatch in the helicities. But in a higher spin object, hadron, like the deuteron, there is a gluon transversity, but there is also much more. And I think Shinzo Komano will describe these things in his talk on Wednesday. And sitting in this corner, transversity sits also on the diagonal where all the collinear PDFs lie. So transversity as a double nature is a TMD, but it's also a PDF, survives after integrating on the transverse momenta. And I will come back on this. The transversity is important also outside our field. For example, because its first Mealy moment, the tensor charge, enters in many effective field theory that try to describe potential new physics beyond the standard model. For example, the tensor charge enters in the expression of the neutron electric dipole moment. Therefore, it's crucial to estimate the contribution coming from the quark chroma electric dipole moment in order to estimate the amount of CP violation of these terms. The tensor charge in its isovector component enters also in effective field theory and try to estimate the nuclear beta decay effect contribution coming from new operators not in the standard model Lagrangian, like the tensor operator. And therefore, it's crucial to know with a high precision GT, the isovector tensor charge, in order to estimate the coupling of these unknown operators. Okay, so I mentioned that transversity has a double nature, collinear PDF and a TMD. In Pavia, we developed machinery to extract transversity as a collinear PDF using the inclusive dihedron channel. And we released a fit that I call PB18, where we addressed the data from semi-inclusive DIS, PP collision, and also with the fragmentation part fixed to E+ E- production of dihedrons. And the main important feature of our fit is the fact that the functional form is built by construction, fulfills the Sofer bound at any value of x and q squared. And also we have a constraint at low x such that when we calculate the first Mealy moment, the tensor charge, we get a finite result. Now, the theoretical framework is still not very accurate, it's at the leading order level, but we made an effort to estimate the theoretical errors coming from the fact that in the fragmentation side, we don't know anything about the gluon channel of the dihedron fragmentation, unpolarized dihedron fragmentation function. And also we try to describe it as describe the statistical errors using a powerful method with a replica method inspired by the neural network analysis. Okay, so this is the published result. You see here the transversity for the valence up quark and for the valence down quark multiplied by x at 2.4 GeV squared. The light blue bands contain 90% of our replicas, so they cover basically the maximum uncertainty due to our poor knowledge or lack of knowledge of the gluon channel of the unpolarized dihedron fragmentation function. You see the vertical dashed lines cover the range, X range covered by the data, and the blue lines describe the Sofer bound. Now, at low X, our object diverges by less than 1/x, such that the first Melly moment is finite. Our results compare very well with the transversity extracted using the Collins effect. You see here an example of the results in the TMD framework by Kang and collaborators, and a similar comparison holds also with looking at the results of the Torino group. This is all published. What is new? Basically, the new thing is that I took our unpolarized Hadron fragmentation function that in that fit was fitted not to Bell data, but to the output of Pythia in the Bell kinematics. I built the unpolarized cross-section as a function of the total invariant fractional energy of the pair and invariant mass. And I compared with the data, published Bell data, and this is the outcome. So my results are the red lines, and the black points are the Bell data. So each box is a specific bin in a fractional energy Z, and the plots are functions of the invariant mass of the pair. So you see that apart from the very first two bins in Z, so between 0.2 and 0.3, in all other cases, our object fitting output of Pythia compares very well with real data. So our extraction is somewhat reliable in this range. And these results I showed you are obtained in next leading order and are quite stable from the point of view of evolution. Here you see a comparison between the leading order, next leading order, and next to next leading order. And you see that the result is quite stable. Okay, let me go to some real new extraction of transversity. Since GEM made a global fit of all single spin asymmetries coming from Sievers and Collins effect, it's not surprising that they have also results on the transversity that Alessandro already commented this morning. You see that here their results are described by the red band compared with a bunch of other extractions in different colors. Among them, there are two of the results. The one from Kang and collaborators for the Collins effect in the TMD framework, and in the blue dotted line is our results, and these are the two extractions that I was just showing you before in the comparison. And you see that the problem basically happens in the outside of the X range covered by data. You see that the down quark result of the GEM collaboration has very deep minimum where around 0.5, where all other parametrization go to 0. And basically the trend of the other parametrization is dictated by the trend of the software bound. So basically this suggests that the GEM parametrization is violating the software bound. You can see this also in the up channel. You see the scale here for the maximum of the up quark distribution with respect to the software bound line here. Now, we'll come back to this, I will comment again, but let me just show the results for the tensor charges. Here on the left, you see the result for the down versus the up tensor charges. The global fit of GEM is this pink blob here. And our result is this black lines here. While we agree for the down result, we disagree in the up badly. And we disagree also with the lattice, while the GEM collaboration is close to the lattice result. Here you see the same information at the level of the isovector tensor charge. This is the GEM result final in red compared with lattice up above here in purple, and this is our results, which is outside their error band. Now the question is this discrepancy between our parametrization and GEM1 due to the software bound? There is an interesting result coming from the work of Umberto D'Alessio and collaborators in Cagliari, where they have basically refitted the Compass and Hermes data for the Collins effect, but releasing the constraints on the software bound. Here you see the results on the tensor charges with the software bound in blue and without the software bound in this brownish color. And you see, while nothing happens at the up quark level, you see that the down tensor charge just spreads to much lower values. And therefore, since the isovector component is just the difference of the two, the isovector component also spreads towards larger values, and tend to become in agreement with lattice results. So according to them, indeed, the agreement between the GEM collaboration and the lattice on the tensor charges is probably due to the releasing, violating of the software bound. Nevertheless, since in the up quark there is not much effect, so the discrepancies we can see in the up tensor charges are still there, and so there are still a puzzle, a question mark.
Marco, 2 minutes.
Yes. Yeah, the last part, future perspective. Just because of lack of time, I'll just tell you what I've done by using pseudo data in my case, so using the dihedron channel for the extraction of transversity, divided into classes, short-term and long-term pseudo data. Of course, first of all, compass. I studied the impact of the compass pseudo data for deuteron on our global fit in Pavia for the extraction of transversity. And since these are data for the deuteron target, it's not surprising that most of the effect comes in the down transversity. Here you see the uncertainty band of our published fit in pink, and you see how it is shrinked by including the compass pseudo data, whose range is represented here by these vertical dashed lines, while nothing happens to the proton. I've done the exercise also for pseudo data coming from class 12. This is the proposal. These data extend, these are for proton target and extend to very large X. And you see that again, since this is for proton target, again, not surprisingly, the increase in precision of the uncertainty band of transversity happens mostly for the up quark here, and the increase is quite remarkable in the range of the pseudo data. Okay. And there are also data I'm working on from STAR. There are published data at the 500 GeV squared that are still trying to analyze and have some troubles. But I know there are more data coming for 200 GeV squared from STAR and Sphenix. And finally, I show you the picture that I prepared for the yellow report document. This is the impact of EIC pseudo data in this energy configuration and you see here what happens when you go from our published plot in pink to when including EIC data with proton target, light blue, and including data also from the helium-3 beam in dark blue. And here below you see how the width of the uncertainties shrink with respect to our published uncertainties. So for the up quark, basically we get a factor of 2 better, narrower uncertainties. And for the down quark, we get, in the case of when include helium-3 data, we get even 1 order of magnitude shrink in the uncertainty at very low X that can be reached the EIC, so beyond the reach of the current data. Here on the right, you see the same situation about the tensor charges, the up versus the down, how the EIC impacts these results in comparison with the lattice calculations. And here the same for the isovector tensor charge, and you see the dramatic increase in precision that can become comparable or even better than the lattice. The GEM collaboration did also the same exercise, and this figure will enter also the yellow report document, and they confirmed our finding, even with a much larger statistics, because they used all the energy configuration, so they have more than twice the data points that I could analyze. And therefore, if there is any discrepancy between the tensor charge coming from phenomenology and coming from lattice will be there, then it will be a many sigma discrepancy, and we'll have to think about it. It will be a problem with such kind of precision. Okay, so finally, of course, jets are useful also for the Collins effect. The only thing is that instead of looking at the mutual correlation between electron and jets, you look at correlation between electron and hadron in jet measurements. Here you see a simulation using the Kang transversity and Collins functions, and you see the impact, the potential impact of the AC, which is dramatic. And okay, I think Ignacio will say something more about this on Wednesday. Okay, so basically I have no conclusions. My conclusion is that you have to stay tuned and have fun with upcoming data and more interesting results. Thank you very much.
Thank you, Marco. Okay, so we have questions. Franco first.
Good talk, Marco.
Thank you.
Listen, Of course, you're correct when you do not treat the measured asymmetries, for instance, the Sieverts asymmetries, as projected on X, Y, Z, PT as independent input to your fits. My question is, you have used only X projections. Have you compared the output you have to the measured projections?
We have done an exercise using the PT projections for the Sieverts, I mean, and the result is stable. We have not done a full systematic comparison with all three different projections. This is still missing.
Thanks.
Okay, so Bakur next.
Okay.
Hello?
Am I unmuted now?
No.
Unmuted, yeah.
Thank you, Marco. Nice presentation and nice progress indeed, starting from between February and November.
Yes.
I have a question about GEM results, actually. I was a bit puzzled. I don't really feel how Drellian results on Sieverts would influence the fit. I mean, would have any big impact, because the results are not precise enough to have any impact. Whether, I mean, and it doesn't really matter, I think, whether you use 12 points or 3 points. I mean, whether you focus on X dependence or all the dependencies. The correlations, I mean, they may impact, but the uncertainties are so large that they should not really constrain. I had an impression that GEM fit is more constrained by the fragmentation function they use, because they use their own extraction for the FFs.
Mm-hmm. Yeah, that's true. That's true. In fact, I mean, I didn't have time to show. They have results of parameterization also for the Collins function, which at the low Z is quite different from the one extracted using only semi-inclusive DIS, any plus and minus data. That's true. Well, probably this is also the reason why in their analysis they used the whole data set. Because I mean, if they had to take only the independent ones, they would be really statistically insignificant. Just 3 data compared with hundreds of data coming from semi-inclusive DIS. But I don't. Well, probably there is also another thing to say, that this data for Drellian, and I don't know about W and Z, but certainly for Drellian, the average X is quite large. It's a little larger than the maximum reached in the semi-inclusive DIS. Is around 0.3, 0.35, if I'm not wrong. So this, from this point of view, these data are helpful because they constrain an area which is not yet covered from the semi-inclusive DIS data. But certainly statistically, they are really not very important. I agree.
But then for the, I mean, comparing with what Miguel, Jean-Bo, and John has obtained, I guess here the difference is that they use the evolution. That's why probably they see a tension between compass data and star data. Because if evolution is strong, then you expect something for star compatible with 0, which is not really the case, and probably this creates the tension. Anyway, I guess we will see in the next talk something more. Thank you.
Well, yeah, keep in mind that the analysis of JAM is basically has no evolution at all in the KT part.
Yeah, that's
it's quite different with respect to the Miguel and Kang and Vitev analysis.
They would indeed not see any tensions. Then, yeah.
Okay, let's proceed. There is several questions. So, Ahut.
Yeah, can you hear me?
Yes.
Marco, you were showing this very significant difference between this software bound and non-software bound. So the transversity is the difference of 2 probabilities, while the sum is F1. So the software bound, I understand, is supposed to take care of that. So what is the meaning at all of any kind of fit violating it?
Yeah, you should ask directly people that violate this constraint in their feet, and not to me. I fully agree. Basically, it's the Sofer-Band is what a little bit stronger constraint than positivity, but still is based on very elementary grounds. I mean, violating that is, well, I don't know what it means.
Well, maybe it should be banned once and forever, and the same thing for G1 fits. I mean, that's just nonsense to some extent, right?
Yeah, okay, but it's certainly interesting that if there is a connection between the disagreement or slash agreement with lattice related to this thing, something we should think about, also from the lattice point of view.
I can understand that if you use some kind of polynomials, whatever, you can describe the data. But what is the value of that? I mean, that there should be probably, I don't know. To me, it makes no sense.
Well, let me add another piece of information. I didn't have time to mention, but it is written on the slides. Aurora and the collaborators made also an attempt to release the Sofer-Bound and see what happens to the parametric functions. So basically, they are using the Bayesian inference. They built the uncertainty on the different types of parametrization of transversity when you are not constrained by the Sofer-Bound, and actually estimated the error coming from that. And indeed, the uncertainty band enlarges with respect to area extraction. Not very much, I would say, but it is larger. So in a sense, one could see that could criticize the Sofer-Bound in the sense that it imposes a sort of rigidity in the functional form, which is our main concern in a sense, because it, I mean, is a prejudice that we insert in our analysis, and from the very beginning, and produces an error, theoretical error, that we are not really very able to estimate in a full glory.
Okay.
I think we have to be a little bit faster. So I think one more question, then we have to go on.
Okay, so maybe, well, there is Oleg and there is Zongbo Kang. So Oleg, if you would not mind to ask the question afterwards during the coffee break, maybe.
Well, there are no coffee breaks, so but this is important. Marco, please, your slide number 3.
Number 3.
About the sign change.
This
even slide number 2. Yeah, the question is very, very simple. Imagine none of us know Rick will at 2 sigma confirm the sign change. Would you feel still yourself quite comfortable with TMD approach, or you would rather push us to do the anti-proton transversely polarized target experiment in AMBA as we planned it?
Wow. Well, I think that, I mean, I would tend to push you to do the measurement, because I mean, this issue is so important that the more data there are to constrain the.
Thanks a lot. So that was the end of the.
Yes.
Okay. Anna, can we still have the question by Zongpo?
I was fast enough.
By Kang, I think, yes.
Yeah, it's just a comment. And let me make quick comment as response for this TMD pion thing. So in the GM collaboration for the TMD pion, it's only the KT part is treated, the Gaussian way is treated as the same as a proton, while the collinear part is exactly the pion PDFs. Same thing for our recent received fit, even the Gaussian part is treated, it's actually extracted from a fit from the pion proton Young data. So everything's good, I think. So
you mean in your last fit, you mean again the collinear part of the pion, or the whole transverse momentum part also?
Yeah, only that. So in the most recent, where John is going to present, both part are fitted from a pion proton Julian data.
Okay.
So everything overlays good.
You mean the E605 data, for example?
Right, yes, yeah.
Okay, good.
Okay, so we thank Marco again for
Thank
this
you.
very interesting
Stop
talk.
sharing.
And we will proceed with the John Terry talk.
Hello. Let's see. Can you guys hear me?
Yes, it's still black for the moment. Okay, now we see it.
Okay, great. Let's see. So first, I'd like to thank the organizers for the opportunity to present here. I'd also like to thank Marco Radici and Alessandro Baghetta for some nice discussions on our recent fit. So my name is John Terry. I'm a fifth-year PhD student at UCLA. This work was done in collaboration with Miguel Echeverria and Zhongbo Kang. And for this talk, I'll be discussing our recent global analysis of the Sivers function and next deleting order and next to next deleting log of QCD. Okay, we already saw some discussion about motivation for TMDs, but I wanted to provide some context for my talk. So collinear parton distribution functions, they provide information about the distribution of momentum of partons in the direction which is collinear to the direction of this parent hadron. As a result of this, they allow us to examine the one-dimensional substructure of hadrons. We created this one-dimensional picture over here. TMDs, on the other hand, are much more complicated. So they probe not only the distribution of the parton momentum in this collinear direction, but also in this direction, which is transverse to the direction of the propagation of the parent hadron. Because of this, they allow us to form a full three-dimensional picture for the substructure. And the goal in the TMD community is to increase the precision at which we understand the substructure, to understand the evolution of these TMDs as a function of Q, the hard
Sorry,
scale.
John, maybe can you speak closer to the microphone? It's feeling a bit difficult to hear you.
Is that better? Can you hear me?
We can hear you. I'm not sure if it is better. Maybe it's better.
Let me try changing my microphone. Okay. Is it better now?
Maybe, yes.
Okay.
Much better, yes.
Okay, and then finally, and most relevant to my talk is we want to understand correlations between the spin and the transverse momentum of the partons. So within the TMD community, the answer to the third question is very well understood. So the two standard TMDs are the TMD parton distribution function and the TMD fragmentation function. And these TMDs can be organized into these famous tables according to, for instance, for the TMD PDF, you organize them in terms of the parent hadron spin and the quark spin. And similarly for the TMD fragmentation function, you organize them in terms of the fragmenting quark spin and the spin of the produced hadron. In each of these functions, they provide different non-perturbative information about interactions that occur between these hadrons and these quarks. For instance, the TMD PDF provides information about interactions between an unpolarized hadron and the unpolarized quark constituent. The Sivers function, on the other hand, which is here, provides information about non-perturbative interactions between a transversely polarized hadron and its unpolarized quark constituent. And we see interesting behavior here. For instance, in momentum space, the unpolarized TMD PDF has this monopole type behavior. So it's completely azimuthally symmetric in the transverse momentum plane. Whereas the Sivers function, because of the correlation between the spin and the transverse momentum, it generates this famous dipole type behavior. Okay, so a majorly important piece of what we try to do as theorists is try to describe experimental data over a wide kinematic range. So we see that, so in this plot, I've highlighted the experimental data in which we're sensitive to the Sivers function. We see that this experimental data covers a wide kinematic range, and this kinematic range will be even more pronounced at the Future Electron Ion Collider. In particular, what's interesting is that we actually have experimental data that lives in two regions. So we have a large bit of experimental data that lives at small values of Q squared. We have an additional set of data, which comes from STAR, that lives at large values of Q squared. And in order to be able to simultaneously describe the set of data which lives here and the set of data which lives here, you have to be able to understand at very high precision how these functions evolved as a function of the hard scale. So in order to really illustrate these evolution effects, I wanted to provide this example over here. So you can imagine if you perform some experiment, if that experiment is at small values of Q, and your experiment is completely blind to any short distance physics that happens in this vertex here. However, as you begin to evolve to larger and larger values of Q squared, you begin resolving additional radiation that happens in this vertex. For instance, you can consider that this quark, before interacting with this photon, it emits this gluon. So as a result, it's lost a portion of its collinear momentum. And so the X that enters in here in this cartoon is smaller than the X that enters in here. And this type of evolution is governed exactly by D-Glap evolution. So that's one of the effects. The other effect is TMD evolution. And TMD evolution is actually very much analogous with D-Glap evolution. So you could consider that rather than losing only collinear momentum in this picture, that you also, when this quark splits, it generates some transverse momentum between these two. So as a result, the transverse momentum that enters into this vertex is larger than the transverse momentum that enters into this vertex. So as you evolve to larger scales, your distribution in transverse momentum becomes more broad. Okay. Now, in order to perform an extraction of the Sivers function, there are really three types of processes that are, at least in the standard picture, are sensitive to this function. So the first two are Drell-Yan and W and Z vector boson. So for these two processes, you have some initial unpolarized hadron, you collide it with a transversely polarized initial state hadron, and you produce a vector boson in the final state. The second process is semi-inclusive DIS, in which case you have some unpolarized initial state lepton, you collide it with a transversely polarized initial state hadron, and you produce an unpolarized hadron in the final state. So for this process, since we have a transversely polarized initial state hadron, the spin-dependent parton distribution function has two contributions. So this first piece is completely blind to the transverse spin, while the second piece contains the spin corrections to this distribution over here. Now, in order to separate these two contributions, what experimentalists do is they measure these transverse spin asymmetries, which are given here. And these transverse spin asymmetries can be written as a ratio of the spin-independent structure function and the spin-dependent structure function. You can use hand-waving arguments to show that this transverse spin asymmetry is very sensitive to the ratio of these two functions. Okay, so in order to perform an extraction of the Sivers function, the first thing that we need to do is parameterize the unpolarized structure function. So for theorists, we tend to not work in transverse momentum space. We work in E space, which is the Fourier transform space of transverse momentum. And then at the very end, we perform a Fourier transform. So in B space, typically, in B space, the structure function has the following form. So we have one contribution, which comes from the hard contribution, which depends only on the hard scale. We have one piece which is related to the collinear parton distribution function. We have another piece which is related to the collinear fragmentation function. And then the effects from TMD evolution perturbatively and non-perturbatively are in this exponent here. So the typical scheme for performing this evolution, so these distribution functions are at some initial scale. And in order to extract the structure function, you need to evolve them up to this hard scale here. So the typical scheme that people do is they take their distribution, since these distributions are collinear, you have to perform D-Glap evolution from some initial scale, which is proportional to 1 over, so say from some initial scale, and you evolve them to this natural scale, which is proportional to 1 over B. And the reason you do this is to kill large logs that enter into this operator product expansion. And then in the TMD evolution, this perturbative evolution here, you resum those large logs. And then on top of this perturbative evolution, you also have to perform non-perturbative evolution, which enters into this non-perturbative pseudokov term. And this non-perturbative pseudokov term can only be obtained by fitting experimental data. Okay. So in terms of the scheme for our fit, so we take the Wilson coefficients that enter here. It's not working anymore. So we take the Wilson coefficients, the C functions at next deleting order.
There is some noise.
I think it's frozen. You have to restart your iPad.
Sorry, 1 second. Let me stop sharing. Technical difficulties. Pen doesn't work now. Okay, I have to continue without the pen. Okay, so these C functions, right? We take them at next to leading order. We perform these operator product expansions, and then for the perturbative piece, so next to leading order, right? That's order alpha S correction, and then for the perturbative piece, so we resum these large logs at next to leading log. So that's it for the perturbative evolution. For the non-perturbative evolution, we take the following parameterization. Sorry. Now the non-perturbative evolution, we take the following form. So this parameterization was used by these guys on the left, so Sun, Isaacson, Yuan, and Yuan in 2014. And they perform their fit with 3 parameters. So the first one is this G1F, and this G1F is the width of the TMD fragment, the TMD PDF in momentum space. They also have this parameter G1D. This is the width of the TMD fragmentation function in momentum space. And then finally, they have this G2 parameter, which is the universal evolution piece. So this G2 piece is universal to all TMDs. So this also enters into our discussion of the Sivers function. So the numerical values are given in this slide. And Marco had also mentioned that it was unclear in our paper how we treated the evolution of the pion. So the width in momentum space for the pion was extracted in 2017 by these guys, Wong, Liu, and Schmidt, and the numerical value for the width is given here. Okay, so using this parameterization, we wanted to check if we can describe unpolarized data. So what we did here is we generated, using this parameterization, this numerical recipe, we generated our theory, and we compared it against this COMPASS 2017 multiplicity data. So in order to describe this data, what we had to do is we had to fix the normalization. So we set our theory is equal to our data at the first point in each bin. So these are these normalization issues, and people who do these fits to unpolarized data know about these normalization issues. While it affects the fit of these unpolarized data, it doesn't affect this asymmetry data. You'd expect that any normalization issue that you have for the unpolarized case cancels in your ratio for the transverse spin asymmetry. In any case, so we can describe the shape of this unpolarized data extremely well using this parameterization. So on the top, this is the COMPASS CITUS data. And then just to do a comparison also with the Drelian data, we also look at this E288 data. And we see that more or less we can describe this Drelian data very well. Okay. So the unpolarized structure function, or sorry, the polarized structure function is very analogous to the polarized structure function. So once again, it can be written as a Fourier transform of V-space function. The functions are very similar. So you have a hard part, you have a fragmentation part, you have the same perturbative evolution, but a key difference between the unpolarized case and the polarized case is that whereas in the unpolarized case, you matched onto the collinear PDF, for the polarized case, you match onto this Chu-Sturman function. So the Chu-Sturman function is represented diagrammatically in that picture there. And we can see that it depends not only on one value of X, but actually 2 values of X. So it's a quark-1 quark correlator. So the Sivers function is related to the Chu-Sturman function via soft poles, which just means that x1 is equal to x2 is equal to xb. So while the Chu-Sturman function depends on 2 kinematic variables, x1 and x2, the Sivers function depends only on 1. Nevertheless, despite the fact that it's related through soft poles, this gluon actually introduces additional complications into the evolution. So the evolution of the Chu-Sturman function is not well understood. Because of this issue, people usually just use phenomenological schemes to treat this evolution. So there are 2 schemes that people use in the literature. The first was shown by Kong and Chu in 2009, and they showed that at large values of X, the evolution can be treated as this diagonal type evolution. So this evolution is called diagonal in the sense that you have only quark to quark splitting, whereas in full declap, you typically have quark and gluon mixing. Nevertheless, in 2009, they showed that this is a valid approximation at large values of X. Here, this quark to quark splitting kernel is given In the second equation here, we see that the D-glop evolution kernel of the Chu-Sturman function can be written in terms of the unpolarized splitting kernel plus this additional piece. So this is a minus eta delta 1 minus x, where a is equal to nc. So I think that this equation is actually very interesting. So what it's saying is that the Chu-Sturman function actually loses more radiation to collinear gluons than the parton distribution function. It's very interesting. The second scheme that people use is that they treat the D-glop evolution of the Chu-Sturman function to be the same as the D-glop evolution of the PDF. We can model this type of behavior, for instance, by taking eta to go to 0, and then once again doing this diagonal type evolution. In this case, the splitting kernel of the Chu-Sturman function is the same as the collinear PDF. Okay, so I discussed the D-glop evolution. Now I wanted to give the parameterization. So our parameterization is given here. So these NQ parameters give the size of the Chu-Sturman function. We also have this x to the alpha q, 1 minus x to the beta q, this polynomial dependent. So the data, which is at small x, is very sensitive to these alpha parameters, while this data at large x is sensitive to these beta parameters. And then actually for positivity reasons, people normally include this prefactor, this complicated prefactor in the front. And this is used so that the size of this polynomial times this prefactor, the maximum of it is just 1. So that the only parameter that controls the size of the Chu-Sturman function is this NQ parameter. And then since we saw that the asymmetry is closely related to the ratio of the TMD PDF and the Sivers function, it's very natural to choose that the Chu-Sturman function is related to the collinear PDF. Okay, so we fit these parameters NQ, alpha Q, and beta Q. And then for the TMD case, we choose a parameterization which is very similar. So we take, so we fit this parameter G1S, which is the width of the Sivers function in momentum space. Okay. And using this parameterization, so the first thing that we wanted to do, so we saw that we essentially had 2 sets of data. So we had a set of data which exists at small values of Q, and then we have another set of data which exists at large values of Q. So the first thing that we wanted to do was remove this outlier data set and say, can we describe this experimental data? So we see that the majority of the data comes from COMPASS, followed by Hermes and Jefferson Lab. In this table, I've highlighted experimental data, which comes from PP collisions. For instance, this COMPASS trillion data. Okay, and I'm sure most of the people in this audience know that there's this sign change between the Sivers function in Drell-Yan and then in semi-inclusive DIS. So theorists typically say that this sign change occurs because the difference in the Wilson lines between these 2 processes, and as Marco had said, another way of looking at it is just by considering the color of this anti-quark in Drell-Yan and this quark in semi-inclusive DIS. So you have a repulsive interaction that occurs in Drell-Yan, and you have an attractive interaction that happens in semi-inclusive DIS. So this sign change was first verified in 2015 by this COMPASS data, which is given here. Okay. So using this experimental data and using this parameterization, so we achieve a chi-squared per degree of freedom of 1.032. This is with 12 parameters, and we have 226 data points in total. We see that the Sivers function for the D and the U quark are essentially equal and opposite of one another. And then we see that the size of the Sivers function for the C quarks is much smaller than for the valence quarks. So in this plot, I used this replica method. So here I've plotted all of the 200 replicas in this gray band that you see. So we keep the middle 68th percentile at each point in order to generate this uncertainty band. Okay, and then so just because I think it's pretty remarkable that we can look at the substructure at this level of precision, I wanted to include these plots. So this is similar to what we saw in Alessandro's talk and then also in Marco's talk. What I'm doing is I'm plotting the distribution and transverse momentum. It's the TMD PDF at XP is equal to 0.2, and I'm actually evolving my distribution from Q squared is equal to 1.9 to 100 GeV squared. So I'm plotting my distribution as a function of Kx and Ky. And then exactly as you would expect, the TMD PDF is completely azimuthally symmetric. Oh, sorry, and you can see as we evolve, the distribution and transverse momentum becomes more broad, as I've mentioned before. So we can also look at the Sivers function. So if we look at the Sivers function, we see very clearly the effect of the sign difference between the U and the D quark. So we see that the unpolarized quarks, they favor having a kx value which is positive, where red means positive, whereas the D quark favors having values of kx which are negative. And here, the blue is a negative value of the distribution. So once we add these two contributions, we can look at the full spin-dependent TMD PDF as a function of transverse momentum and also Q squared. And you can see clearly the effect of this distortion from the Sivers function. Okay. You'll have to forgive these slides. There's some technical issues that are occurring. Basically, those lines are too thin and it's having trouble displaying them. But we see clearly that so this blue curve is our theoretical prediction, and we're comparing the theoretical prediction against the experimental data at COMPASS. So on the top, it's for the Drell-Yan data, and on the bottom left is for the H+ data at COMPASS. So we see clearly that we described this low energy data extremely well. And using this fit, what we wanted to do is give a prediction for the RIC data. So we can see clearly in this plot that our prediction for the RIC data is much smaller than the experimental data at RIC. So we see that there's some level of inconsistency that's occurring between these two data sets. So the natural question to ask is our treatment of the evolution to blame? So really the difference between these two data sets is that one lives at large values of Q squared, whereas one lives at small values of Q squared. And as I mentioned previously, the DGLAP evolution of the Chu-Sterman function is not well understood. We had to choose some scheme in order to perform the evolution. And so that could potentially be causing the issue. So one of the tests that we ran is we changed our fitting scheme for the DGLAP evolution. So originally in the fit I just presented, we chose eta is equal to NC, but we wanted to see how the theory changed for each of these data sets as we went from one scheme to the next. And so we defined this quantity delta T here. And what delta T, it gives the average change in the theoretical prediction simply by changing this eta parameter. So we looked at two data sets. So we looked at the low energy data set and we looked at the high energy data set. What we found is that this delta T for the low energy data set, it changes only by 1%. However, exactly as you'd expect, high energy data is much more sensitive to this radiation. So as a result, this RIC data is much more sensitive to how you treat the DGLAP evolution. So what we did here is to see which scheme was providing a better prediction for the RIC data, or which scheme provided a better agreement with the RIC data. What we did is we plotted the chi-squared in orange as a function of this eta parameter. So we keep all of our parameters fixed, we vary only eta. And what we find is that the eta equals 0 scheme clearly gives a better description of the RIC data than the eta is equal to NC scheme. Okay. So using this knowledge, we wanted to perform a fit to all of the experimental data. Now, as we saw, the majority of our data lives at low values of Q squared, whereas we have very few data points at large values of Q squared. So in order to have some level of compromise between these two data sets, what we wanted to do was treat the two data sets to be equally weighted. Namely, we wanted the RIC data to be as important as the rest of the experimental data that's at low values of Q squared. So in order to do this, we took this value of omega to be 226 divided by 17. So we have 226 data points at low Q, and we have 17 at large Q. And so by doing this, we treat them to be the same.
John, 2 minutes.
And after doing this, we achieved a chi-squared per degree of freedom of 1.482. This is again with 12 parameters, and here we have 243 data points. So you can see the effect of the RIC data is pretty drastic. So we see that while qualitatively we still have the exact same behavior, the size of our uncertainties is very large. So this is a result of using the weighted definition of the chi-squared, and then also the large experimental uncertainties at RIC, as well as the large values of their asymmetry for the central value. Okay. Despite these large uncertainties, we still see that we can describe this low energy data reasonably well. At the same time, the description of the RIC data is much better than the previous extraction. Okay, so this is my last slide. So I just wanted to quickly summarize everything that I've said. So we can describe the low Q data very well. However, describing the data, which is at large values of q squared, appears to be very difficult. We found that the treatment of the DGLAP evolution has a very large impact on how well you can describe the experimental data. However, we don't really know if this effect is because of the measurement at RIC, or if this is actually something which is very physical. So what we're doing is, we're really looking forward to additional data in this black region. So in this black region, we have no experimental data, which we can use to really understand what's going on in this intermediate region. So personally, I'm looking forward to the experimental data that will be coming out at q squared is equal to 100 GeV squared from Amber, as well as this future, the reanalysis at RIC that should be coming out in the next couple of months. Thank you.
Thank you, John. So we have questions. So Alexei first. Alexei Veladimirov.
Yep. Hi. So thank you for very nice work. So I actually have more like a comment. So recently, me and my collaborators, we made also extraction of Sievert's function, and actually we do not see any problem with RIC data. So even if we fit only see this data, we can describe then afterwards RIC data with reasonable high square. And okay, there are some small differences, of course, in our work and your work, but I think the main problem in why you have such a big high square there is that what you call the DGLAP evolution for Church-Terman function is completely broken. So it is known that with Church-Terman function, the kind of diagonal part of evolution is numerically suppressed. So the main part of evolution comes from off-diagonal terms. And this off-diagonal terms is something like 2 orders of magnitude higher than diagonal one. So that's why in our analysis, when we just use data prescription, we don't need to use this DGLAP evolution, so we do not have any problems.
You don't use, sorry, what do you mean you don't use DGLAP evolution?
Sorry?
Sorry, what do you mean you don't use DGLAP evolution?
You described somewhere in the middle on some slide that you use this DGLAP type-like evolution for Church-Terman function.
Mm-hmm.
So kind of we use data prescription, and that's why we just have a Sievert's function at some fixed scale on zeta scale. So we don't need to evolve it from point to point in different p's.
In your operator product expansion, you don't have to evolve it to the scale mu b.
Sorry?
And in your operator product expansion, you don't evolve to scale mu b.
So yeah. Because it's not okay. That's a technical point. So, but okay, in our approach we don't need to do it, and when we do not see discrepancy. So that's why actually I think that this most part of that problem comes from incorrect treatment of Church-Terman evolution.
Yeah, I mean that's one of the interesting points of this discussion is that the treatment of the DGLAP evolution is a very important piece in being able to describe this large energy data, right? Yeah.
So it was a comment. So.
Okay. Okay. Thank you. And we have a question by Marco.
Yes, I would like to go back to the plots where you show your comparison with the unpolarized data. It was, yeah, the beginning of your analysis. Here, yeah. I would like to check if I understood correctly. You are not fitting the unpolarized data, correct? You're just comparing your results with the experimental data. Is that correct?
That's correct, yes.
Okay. Because, yeah, I was just going back in my mind to the remark by Jean-Beau at the end of my talk that I understand that the pion part is linked to the Fermilab data, but it's not a fit actually. It's just a comparison, which is good, at least looking by eye, but it's not actually a fit.
So there was this extraction that was performed. Let me see. It was performed in 2017, this extraction of the pion width by Wong, Liu, and Schmidt in 2017. And I believe that what you had said was right, that it was this E605 data that they performed this extraction from. Does that answer your question?
Yeah. Okay.
Okay, it seems there are no more questions.
No, I still have questions. So.
Sorry.
Sorry, concerning Pi0 and K0 production, where did you take the TMDs for them? Because to my best knowledge, there is no kind of on market any TMD distribution for Pi0 and K0.
I mean, the compass trillion data is only for pi minus, correct?
No. So if you go to the table of all included experiments,
sure.
Here, yeah. So I see that you have K0 and Pi0.
Mm-hmm.
Yeah. So where did you take the fragmentation function for them?
Yeah, we use DSS14 for the pion, DSS17 for the kaon. So what we do is we perform an average over the pi plus and the pi minus to get the Pi0, and similarly for the K0.
Okay, thank you.
Okay, so we thank John again and all the speakers of this session.
And we will be back in 10 minutes.
Voila. So I would like to check for the next session that we do have speakers and their mic is working.
Yeah, I believe I'm the first speaker.
Yeah. Please, Maxwell, go on. Let's try.
Yeah, you can.
I can see you.
Okay, you can see me. Hopefully you can hear me.
Yeah, I can hear you.
I can also do the screen share.
Let's see. That's the case. Okay.
Do the slides look okay?
Yes, I see your sharing and it looks okay. Yes. Good.
Great. Thanks.
Ready to go.
Ready to go.
Yeah. Go with the next, which is
should be me. Hi.
Stefan.
Can you hear me?
Yes, I can. Now
okay. Let me try to share my. Yep. No, this is not.
The source of the light that you are using is not the best. It seems to be, but I think we can. That's not the big problem.
Okay.
I see a shadow of light behind you.
Oh yeah, that's just one spot at the.
Yes.
Okay.
Okay.
But I hope with this, can you see my slides?
Yes, I can see the slides and everything works fine. Okay. Thank you.
And the volume of the mic is okay?
The volume of the mic is perfect.
Okay, thank you.
Thanks to you. Igor.
Okay.
I think that now is you.
Let me share my screen. Can you see it?
We can see your monitor, not yet your slides.
Okay, let me make a full screen. Can you see it now?
Nope, not yet. You have more than one screen, most probably. You have two screens.
We see the desktop.
We only see your desktop now, or one of your monitor.
Okay, I understand.
If you have more than one display, you need to choose the one which you are using, either the display number 1 or the display number 2.
Okay.
Or screen number 1 or screen number 2, what is normally presented.
Okay. How's about now?
Now is about better. I see on your screen part of your presentation. If you go full screen now, we can be sure.
Let me make a full screen.
Yeah, that's perfect. Yes.
Oh, great.
Yeah.
Thank you.
You're set. Thanks to you.
Let me stop sharing and give a Volker time.
Yes, Volker. And check with you now. If you are there. We are a bit late with respect to the schedule. That's for that reason we try to be fast, and also we will restart in a few minutes. Volker, are you there? Oh, let me check if he is connected. Volker is there, okay, but probably it just took the break. Okay, in any case, we are set and let's wait for the convener. Anna, you are talking
The person is there, so everything is fine.
Yes, it's connected, even if it's probably taking a small break before the start of the section.
Yes.
Okay, good, thank you. Wolfgang, are you the chair now, no? I see you.
Yes, I'm prepared.
Okay.
We actually should start now, right?
Whenever you want, you can start.
Well, the 10 minutes have passed, so we start now, right?
Ready.
Okay, so welcome back from the very short coffee break, and welcome to session 4. We'll have 4 talks on Hadron spectroscopy. The first talk will be given by Maxwell Hansen from Edinburgh about spectroscopy on the lattice. So please go ahead.
Great. I'll go ahead and jump in. Let me first say thanks very much for the opportunity to speak here. I'm excited to tell you a little bit about progress looking at QCD spectroscopy from the lattice. And I want to also give you an idea of the methods that we use and both their strengths and their limitations. So with that, I'll jump to my first slide here. I just want to sort of give a lightning introduction that, of course, my focus will be on the strong force, which is a part of the standard model. The standard model is an overwhelmingly successful description of nature, and it's built, as most all of you know, from this gauge group, and I will focus here on the SU3 part, which of course is the mathematical theory of QCD, quantum chromodynamics. And I would like to emphasize the point that we now know QCD is the correct description of quarks and gluons, also in the strongly interacting regime. So I'd like to say we know it's the theory of the strong force. And it's interesting to glance at some of the evidence we have for this. So of course, going back many decades, we also have some non-numerical evidence. We can make some predictions of low energy QCD. And for example, the patterns that hadrons form when you arrange them according to quantum numbers is already strong evidence for QCD. For example, Gelman's 8-fold way. There are other interesting low energy examples. But as a latticist, I want to comment also on the numerical example. And I want to highlight recent progress in really seeing the full dynamics of QCD in numerical lattice calculations. So one very fine example from last year is looking at the inner quark potential as you pull 2 very heavy quarks apart. And this beautiful plot from Bulava et al. Last year shows that as you pull those heavy quarks apart, you see a string breaking where a light quark-antiquark pair pops out of the vacuum. And this can really be seen numerically. And in fact, this calculation was done with both light and strange quarks. So you see a second breaking associated with the strange quark production. So we can see this kind of phenomenology in deep numerical detail. Finally, we can extract low energy parameters from the QCD calculations. And this plot illustrates an extraction of the strong coupling. Effectively, the inputs here are the meson masses, the pion and the kaon mass, as well as the decay constants. And then using the numerical calculation, you can run the QCD parameter up into the deep UV regime and see that it's consistent with other extractions. And I point you to this FLAG effort, which is a lattice averaging group, to sort of see the state of the art in these calculations. But I want to highlight my topic here, which of course is spectroscopy. And I would emphasize that the observables I just showed are all based on single particle states, but many interesting phenomena are governed by multi-hadron observables because some short-lived excitation decays into hadrons. And this of course is the story with various exotic candidates, the XYZ states, as well as tetra and pentaquark candidates. An example here is the X3872. From the mass of this particle, it might seem like it could be some molecular state, some combination of DD star. But we also know it exhibits a very prompt production, and so the nature still is not fully understood. So it's interesting to try to understand these states from first principles QCD, as well as electroweak decays that include resonant states. For example, the B can go to pi and leptons through a rho resonant, or can go through a K star. And extracting these from QCD is also interesting. But the key message for all of these states is because they're resonances, they're not part of the QCD Fock space. They're not eigenstates of the QCD Hamiltonian. So what do we mean by such excitations? Now, what we do know is that we have the low-lying stable states like the pion and the kaon, and we can also form asymptotic multi-hadron states, and from this we can form the S matrix. And this is the language in which we want to think about resonances. So here I'm showing this cartoon example in the pion case. You can look at the overlap between a 2-pion in state and a 2-pion out state, and that defines for us this scattering matrix. We know, of course, that this will depend on the center of mass energy, or on this Mandelstam S, And it also depends on angular coordinates, but if we project to definite angular momentum, it becomes just this simple diagonal matrix. And because of unitarity, we just have a simple phase on the diagonal. And I just want to emphasize that our goal here is really to extract this S matrix from QCD, and that this is an enormous space of information because we can look at the overlap of 2 pion states, 4 pion states, KK bar, etc. Just a massive space of information. And this leads to our definition of a resonance. A resonance is a complex pole in the analytic continuation of these S matrix elements. Now, roughly speaking, we know that we can form the scattering rate. We take the magnitude squared of our amplitude, and this is the scattering rate. And if we see a peak feature, that's already a hint of a resonance. So here's an extraction from experimental pi-pi data. And you see here this characteristic peak of the rho resonance in pi-pi scattering. But if we now take this data and think of it as a curve in the complex energy plane, when we continue out to non-zero imaginary parts, we see something much more crisp than just a peak, an actual honest singularity, a pole in the complex plane. And this gives us a very clean definition because the real part of the pole position can define the mass for us and the imaginary part the width. And it also conceptually bridges the gap between a bound state, a pole on the real axis, and a resonance in the complex plane. And the other beautiful aspect of the pole is that it's universal. So we can see a rho, for example, produced in many different contexts, in a B to J psi decay or in a J psi decaying into photons. And if we imagine taking all of these different curves, although they have different shapes, their analytic continuation to the complex plane must yield exactly the same pole position. And that's the sense in which it is honestly the same resonance driving all these processes. The reason they look different is the couplings to the in and out states differ. But although the couplings differ, the poles are indeed the same. And so we want to attack this using lattice QCD. And to achieve that, we first need to understand a bit more about the mathematical structures here. In particular, I did something a little non-standard in the last slides. I imagined analytically continuing the rate, the magnitude of m squared. It's more instructive to analytically continue the amplitude m itself. And to do that, we need to understand its analytic structure. Does it have poles? Does it have branch cuts? What does it look like in the complex plane? In fact, we can understand this from the basic rules of quantum field theory by representing the scattering amplitude as this series of diagrams. This can be made precise. It's a beta Salpeter expansion. And we know that m is represented by this short distance kernel together with these ladders where this represents, for example, 2 pion states propagating in the vacuum. And to understand the analytic structure, we look inside these 2 pion loops and we define a cutting rule. Of course, this picture just represents an integral, and one can prove that this integral is equal to a real part, which is a principal value, and that's pure analytic, together with imaginary part, which is proportional to a square root function. And it's exactly this square root that I want to emphasize. If I substitute this cutting rule into all of these pictures, I can rearrange things and I reach this very simple conclusion. If I group together all of the real parts, that identifies sort of the maximally analytic part of the scattering amplitude. This is what we call the K matrix. And at the next order here, I see 2 K matrices with this square root function in between them. In fact, this geometric series continues to all orders, and I reach this very nice punchline. So what have we learned at this stage? We've learned that each 2-particle channel introduces a square root branch cut, which doubles the number of Riemann sheets. And therefore, we really think of scattering in this 2-sheet context. On the so-called physical sheet, you can form the bound state poles. And on the second unphysical sheet, you discover the resonances. And so this tells us that the details of analyticity are important for a quantitative understanding of resonances, and that this idea of a cutting analysis separates the long-distance kinematic singularities from the short-distance microscopic physics. And this is really how I would like to think of lattice QCD, as a tool for getting out the K matrix, for getting out that short-distance microscopic physics that depends on the details of the channel. Now, as most of you will know, lattice QCD is a numerical tool for evaluating the QCD path integral. But to make things numerically tractable, we have to cheat a little bit. We have to make 3 key compromises, and those are listed here. First, we have to replace our continuous spacetime with a discrete lattice. Second, we have to put the entire system in a finite spacetime volume. And third, we have to work with Euclidean signature in order to have a sharply peaked integrand that allows for Monte Carlo importance sampling. And that's why on the left-hand side here, I really write observable with a question mark. We have to check on a case-by-case basis, how severe are these modifications? Is it still possible to get out the observable that we want? And I should also mention that Many calculations are done at heavier than physical pion masses, but the physical mass is becoming increasingly common. Now, I think somewhat surprisingly, if I'm interested in multi-hadron states and scattering, the biggest limitation turns out to be the finite volume. And that's because the finite volume completely destroys the story I just told you. In a finite volume system, we have a discrete spectrum of states, and therefore we have no branch cuts and no extra sheets. And this is really illustrated by this comparison. On the left, you see the finite volume analytic structure, the analytic structure inside the lattice calculation, if you will. And it's very simple, just isolated discrete poles, no branch cut, only one sheet, no extra poles off in the complex plane. So that looks totally different from the right panel where we have two sheets and the second sheet contains the resonant poles. So what we do at this point is we really step back and say, if we've changed the analytic structure so much, what can we hope to get out? And we take the finite volume head on and we say, what we can actually get from a lattice calculation. The only thing we can get from a lattice calculation are finite volume energy levels in QCD and finite volume matrix elements. And our task then is to relate these finite volume energies and matrix elements to experimental observables. And so let me tell you how that works. And I really want to emphasize that we start to think of the finite volume as a useful tool, a useful mechanism for probing these resonance physics. To be concrete, we always think in terms of a cubic periodic spatial volume. And the effect of that periodicity is that only discrete momentum modes are allowed, only these integer multiples of 2 pi over the box length L. We also take the box large enough to neglect certain exponentially suppressed effects. And we also typically work with the temporal extent much larger. So this is all about a finite cubic spatial volume. And the reason we can make progress with scattering is because scattering leaves an imprint on the finite volume quantities. And remarkably, this was already understood in the late 50s in this simple context. In the left panel here, I'm imagining I scatter 2 pions very close to threshold. And the scattering amplitude at threshold just defines the 2 pion scattering length. And in 1958, Huang and Yang showed that exactly the same scattering length appears in the 1/L expansion of the 2 pion ground state in a box. So whether you scatter pions at low energies or whether you put them in a box and study the L dependence, you get out the exact same piece of physical information, the scattering length. And that's the philosophy of this program that I'm now going to describe. Now, we can actually do this not just for the ground state, but for excited states. And it turns out to be very closely related to the story I told you about analyticity and the idea of the square root branch cut. So let's consider for a second this new object. This is a finite volume version of the scattering amplitude. And the question that we want to answer is, what is the L dependence of this field theoretic quantity? The answer is that we can define yet another cutting rule that relates this finite volume loop, the effect of the pions in the box, to the infinite volume principal value loop, this infinite volume analytic bit, and a new cut. And the latter is given by a matrix of known L-dependent geometric functions. And by mimicking this analyticity argument, we reach the following form. We recover exactly the same infinite volume K matrix, but then the series contains these F cuts, and when you sum them up, you get this result. This object has a set of discrete poles, and those are exactly the finite volume energies. And so this is the result that we're going to use for the rest of this talk. The result is that this known function of the scattering K matrix and these geometric Fs, whenever it vanishes, that's one of the finite volume energies in the system. And if we measure the finite volume energies in the lattice calculation, that gives us a constraint on the K matrix. So here's a flowchart of how we will work. We put in some finite volume information. We map that to the infinite volume K matrix. And then by enforcing unitarity, we recover the 2-to-2 scattering amplitude. And I just want to stress this is a very general program, but only for 2 particle states. That's one limitation. It works for multiple channels and for spinning particles, but again, only 2. Here's an example of this approach in action. So what you see here in the left panel is an actual lattice calculation performed by the Hadspec collaboration. And they find these finite volume energies in a box that's 16 cubed, 20 cubed, and 24 cubed. So this is a piece of low energy, non-perturbative information about 2 pions, in this case, 2 pions with row quantum numbers. And when you plug it into the master formula, you get the scattering amplitude, or in this case, the phase shift at that given energy. And then you repeat this for the different volumes. here you see that the information is all in a very similar energy regime. But if I boost the two-particle system in the box, that changes the geometry completely, and then I get very different constraints. And by using 3 different volumes and 5 different boosts, I can really populate this curve and see the shape of the rho resonance as a sharp rise in the pi-pi scattering phase. So we're not just getting a single state, we're really getting the shape of the scattering phase. And I want to stress that many collaborations are doing this. So this is 3 others that have also done very nice rho analyses. You'll see some of them use 3 quark flavors, others only 2, but they all are able to reproduce this very nice scattering structure of the rho resonance, thereby getting both the mass and the width. And here's a summary plot of the rho to pi-pi coupling. This just gives you an idea of how many lattice collaborations are working on this. So it's really reached this era of being a standard quantity that people can extract. And we see overall good agreement across collaborations. And now there's no possible way that I can really do justice to the huge amount of scattering that's been done. So I want to just stress the over a dozen rho to pi-pi calculations. These are all hyperlinked, so I encourage you to click on the slides if you want to look at any of these in more detail. Both the j = 1 and the j = 0 scalar multiplets have been completely mapped out in this scattering framework. And I do want to highlight on one other feature here that is interesting and challenging, which is that the cubic volume has its limitations, and in particular, it mixes together information that we would like to separate out. For example, if you think about k-pi scattering, there both the S wave and the P wave are resonant. And in the finite volume, those 2 resonant channels mix together. So a given finite volume energy depends on both. And similarly, if you think about scattering of, say, pi-pi to kk bar, this whole 2x2 scattering matrix all mixes together in the finite volume. And that leads to this sort of workflow. We use many, many different operators to really reliably extract many finite volume states. And these dots represent the finite volume states that you'll extract, not just the ground state, but many excited. And then you want to identify some reliable description of the K matrix. And this is where contact is made to other communities. We can use polynomial and pole descriptions, but it's better to use some EFT motivated description of the K matrix, or even something based in dispersion theory. And by fitting these K matrix parameterizations to these many energy levels, we can extract the infinite volume scattering also in a coupled channel system. And so here's an example of that, looking at the sigma and the excitation, the F0. So each of these curves here represents an example of the K matrix that is commensurate with the finite volume data. So the lattice can't say which of these curves is the preferred value, and the spread gives you an idea of the systematic uncertainty. So the finite volume information is constraining the curves, but it's not completely pinning down the result. But if you take the spread as your systematics, then you do have an extraction of the scattering information. And in this case, if you continue these curves into the complex plane, then you see here a very reliable pole. It moves around a bit, but it appears in every single description. And that tells you that there really is a resonant pole here. And this, of course, is the F0 resonance by the kk bar threshold. I also want to mention that these calculations are working at different pion masses. And that can be seen not just as a limitation, but in fact as a feature. So this is now looking at the kappa and the k star resonance. Let me focus on the k star 892, which is this bottom plot. You see this beautiful sharp rise corresponding to the resonance. And this gray curve is from an experimental determination at the pion mass of 140. This lattice calculation at 240 already shows you how the resonance narrows up. And as you ramp up to higher and higher pion masses, the curve becomes steeper and steeper as the phase space closes and the resonance becomes closer to stable. And indeed, you can track the pole position of the K star in the complex plane. So here you see the experimental value. And as you ramp up the pion, that pole drifts upwards toward the real axis. And in fact, at 390 MeV, it becomes a stable particle on the real axis. And this way of probing resonance structure by varying the quark mass can really give us some insight about the meaning of these resonances and their underlying nature. So I really want to highlight this beautiful study. And then I also wanted to mention that this isn't just being done with light quarks. There's also a scattering analysis in the charm sector. In fact, many of them. And this is an example that finds a bound D star 2317. I'm happy to answer questions about this later, but I just wanted to highlight that also charm studies are being done. And similarly, something that came out just last week is a DD bar scattering by Prelovshek et al. And they also see a bound state pole, or at least some evidence for a bound state pole at this heavier than physical pions. I will skip the rest of these studies, and I want to use my last few minutes to comment on the idea that something has limited all of these calculations, and that's that they were all looking at 2-to-2 scattering. 2-to-2 is certainly the simplest system, but we know it has some limitations. 2-to-2 scattering can only sample certain quantum numbers, certain JP values, and more importantly, we know that many interesting resonances also have a significant 3-body branching fraction. So for example, the X famously goes into 3 particle states. And so one of my research focuses has been the question, can we do the same thing that we've done in the 2-body sector also for 3 hadron states and beyond? And more precisely, our goal is to come up with a finite volume, unitarity-based formalism for any coupled 2- and 3-particle systems. And the applications range from exotic resonances and form factors to also nuclear 3-body forces. So I just want to give one slide on the status of this effort. This is something that I started in my PhD and has now sort of been pushed to completion over the last 10 years. And what we now have, just as in the 2-particle sector, is a relation that takes you from finite volume 3-particle energies into this combination of a 2- and a 3-body K matrix. And then we know how to solve integral equations that enforce unitarity and get out the physical 3-particle scattering amplitude. And I'll point you to this recent review article if you want some more detail about this 3-particle in a box scattering formalism. But let me close with one final result. This is something that I've done also with the HadSpec collaboration, and it's just been accepted to appear in PRL, and it's the first entire workflow for looking at 3 pi plus goes to 3 pi plus scattering. So this is a boring channel. It's a non-resonant channel, but it's just kind of setting the benchmark that we know how to do 3 hadron scattering on the way toward 3 hadron resonances. And I just want to highlight that in these left panels, all of these black points represent finite volume 3 pion energies. And these orange curves represent our best fit to that data. So you extract the infinite volume K matrices from all of these finite volume inputs. And then when you feed that through the framework, what comes out at the end is the 3-to-3 scattering amplitude. And even for this boring system, you see these very nice analytic structures in 3-to-3 scattering. And those are due to the inherent singularities in these. Ultimately, these come from triangle diagrams that exist in any 3 hadron amplitude. So it's possible to also see these structures coming out of the formalism naturally. And finally, it's not only enough to get the resonance positions and the couplings to hadron states. It's also very nice to probe these with external electromagnetic currents. So I just wanted to give 1 second to these kinds of calculations. This is looking at a pion colliding with a photon to produce a rho. And it's also understood how to probe the rho resonance with such a photon current in the lattice calculation. And in fact, now we're considering 2-to-2 scattering, in which you again probe with an external current. These again face a new set of complications, because if you have 2-to-2 with an external current, you can form these triangle diagram topologies, and those induce a new set of singularities that you have to understand, both in the infinite volume world and in the finite volume world. And with that, I would like to conclude. The main message I hope I was able to deliver is that lattice QCD is in the era of rigorous resonance spectroscopy, where we really see the resonance in analog to how it's seen in experiment, and that's achieved by using the finite volume as a tool. I won't read the challenges and the progress here, but I will say that many challenges have been overcome, but many still remain. And to my mind, the most important are pushing this to an n particle formalism, so we can really treat resonances that decay to 3 or more states, and also pushing more channels into the physical mass precision regime. And with that, I'll flash my big picture, just summarizing a number of the plots I already showed. And I just want to say, I think this is a thriving field with more to come. And I'll say thanks for listening.
Yeah, thank you for this very elegant talk, I think, which is open now for questions. Yes, Bertone.
Yes. Yeah, it was actually very fascinating. So I'm definitely not an expert in this field. I just have a curiosity. So in the beginning of your talk, you mentioned that the fact that you work in a finite volume essentially breaks down the analytic structure of the amplitudes. Is that only due to finite volume effects, or is that also due to the fact that you are on a lattice, that you have a finite lattice spacing?
Good. So in this case, it's only due to the finite volume effect, so only an infrared effect, if you will. It's true that the lattice spacing also has modifications, but those are more relevant in the ultraviolet. So if you look at this structure here, as you go to higher energies, then you'll also see lattice distortions. But these low-lying states, they're mainly distorted by the infrared.
Okay. Concerning, I mean, along the same line, I guess that because of time constraints, you didn't mention renormalization in your talk.
Right.
What's the role of renormalization in this framework? I mean, for determining
very good. Yeah. So I mean, of course, it's very important. So it depends in detail what current you have, but the basic strategy is there's the so-called regulator independent schemes that allow you to numerically flow up to a high scale and then match, say, to MS bar. So this is understood, but it's technical, but it's understood, I would say.
Okay. Okay. Thank you.
So I see no more raised hands. So thank you again. And we proceed with the next talk, which is by Stefan Wallner. The talk is about the strange meson spectrum.
Hi, so good afternoon. I hope you can see my slides. Okay, first of all, thanks a lot for the kind invitation to speak today about strange meson spectroscopy at Compass, but also at other facilities. If you want to know what is known about strange mesons, of course, the first thing to do is to look into the PDG, which lists at the moment 25 strange mesons, shown here by their spin parity quantum number. 30 of them are marked as established states, shown here as blue points and blue boxes, and another 12 still need further confirmation, shown here as orange points and boxes. And the black bars show a quark model prediction for strange mesons from Ebert and collaborators. And you see with respect to the quark model, there are still many states experimentally missing. I think this picture nicely summarizes that there's still much work to do for us. We can group the strange mesons into two families. One are the KJ star states, where 8 of the 11 listed KJ star states are marked as established states. They decay to K-pi, but also to other final states, and most of our knowledge about them comes either from K-pi scattering or from heavy meson decays or tau decays. The second family are the KJ states, where only 5 of the listed 14 KJ states are marked as established states. They cannot decay to K-pi, so we usually observe them in the decay to other final state particles, usually multiply the final states, like K-pi pi or K-phi, K-omega, and lambda antiproton, and then the phi omega and lambda antiproton further decay. Most of our knowledge about the KJ states come from measurements either again of heavy meson or tau decays or from various production experiments. With production experiments, it means scattering of high energy beams, either charged kaon beams as it is used at SLAC or CERN, for example, or a photon beam as it used at Jefferson Lab, for example, at the GLUX experiment. You will hear more about that later in the session. Or there's also a recent proposal, actually it was approved, I think, for a K-long beam at Jefferson Lab at the GLUX experiment. And you will also hear more about that in the next talk in this session. And then this strange mesons appears intermediate state X here, and as they're very short-lived, they decay in some quasi-stable final state particles. At Compass, we use our high-energy K- beam in diffractive scattering, where we produce the strange mesons, and then our flagship channel is the decay to the K-pi pi final state. If you want to know what is known about or what resonances appear in this K-pi pi final state, of course, the first thing to do is to look into the invariant mass spectrum, which you can see here on the right-hand side, which already shows a few interesting structures here from the 2K1s, for example. But there's also some broad spectrum where this signals sit on top, and this broad spectrum arises from many overlapping interfering states, and as they are overlapping and interfering, we cannot directly extract them from the K-pi pi mass spectrum alone. Compass has actually collected this world's largest data set of diffractively produced K-pi pi with a dataset size of around 700,000 exclusive events. And as a comparison here, I show again the K-pi pi mass spectrum from a measurement of the K-pi final state of the WA03 experiment at CERN, and which was analyzed by the ACMO collaboration, and they collected 200,000 events. Then, of course, this K-pi mass spectrum is not the only information we have available. We can look into the mass spectrum of a two-body subsystem. So, for example, here of the pi-pi subsystem, we can see here on the right-hand side, now this is clearly dominated by well-known two pion resonances like the Rho 770, for example. And this indicates that this X here not directly decay to K-pi-pi, but dominantly successively decays via two-body resonance we call isobar. And then we also observe rich structures in the angular distribution here of the two-body decay angles of the isobar decay, or of the two-body decay angles of the X decay into the isobar and the bachelor kaon. And these decay distributions are actually characteristic for the spin structure, for the spin and the parity of the decaying state. Okay, knowing this, we can define what we call a partial wave, which means a certain intermediate state X with a certain spin parity and spin projection M epsilon, in combination with a certain decay mode, which means a certain isobar L, bachelor particle here the kaon, and angular momentum L between the bachelor particle and the isobar. And now, as we know the footprint, the characteristic footprint of each partial wave in our final state distribution, we can extract the partial wave amplitudes in an ambient maximum likelihood fit from our data. And on the next few slides, I want to show you now results from selected partial waves in certain JPC sectors. And I want to start with actually our most beautiful signal, which is a 2+ state decaying into K star pi, where both are in a D wave. And you see this nice clear peak here in the mass region of the K2 star 1430, in combination with a rise in the phase. So here the relative phase of this 2+ wave with respect to a 1+ wave. And again, this nice rise in the relative phase in the mass region of the K2 star 1430. And this rise in the relative phase and a peak in intensity, those are characteristics for narrow isolated resonance. So those are the kind of signals which we are after. Then, of course, we were not the first to look into this partial wave. You see here now the intensity distribution again of the 2+1+ K star pi D partial wave from this analysis of the ACMO collaboration. And see also they observe, if you compare with COMPASS, a similar peak in their intensity distribution. There's a recent high precision measurement from BES3 in the case of shape psi to the KK pi final state, where the K-pi system appears as a subsystem and allows us to study strange mesons. And you see here the corresponding invariant mass distribution, which of course shows a prominent peak here from the K star 892. But you see also here a smaller peak in the mass region of the K2 star 1430. And they performed a partial wave analysis and actually extracted one of the most precise determinations of the K2 star 1430 parameters. Then, of course, the K2 star was measured in various K-pi scattering experiments. For example, you see here a result of the D wave from the last experiment, which again shows a clear peak here in the mass region of the K2 star 1320. And nonetheless, the K2 star is such a nice and clear signal. Still, there are some question marks concerning its parameters. And the PDG actually lists two different sets of parameters, one for the charged K2 star and one for the neutral K2 star. And if you look here on the right-hand side, now is the ideogram of the width of only the neutral K2 star. And already there you see some discrepancies. So there's one cluster with a width of 100 MeV and another cluster with a width above 110 MeV. So this shows that even for such nice and clear and in principle well-known signals, there's still some question marks remaining. The next JPC sector I want to discuss are the 2- states. And you see here our strongest partial wave in the K2 star pi S decay, which develops this clear peak here at about 1.8 GeV with a bump in its high mass shoulder. Where in the peak, the PDG lists the two established states, the K2 1770 and the K2 1820. And in this bump, we potentially see a signal from the K2 2250, one of the states that need further confirmation. We observe similar signals also in other decay modes, for example, here the Rho K decay or the K star pi decay. Then this K2 1770 was studied also by the last experiment in the K omega final state, where you see here the intensity distribution of the 2- waves, which again shows a clear peak slightly below 1.8 GeV. There's a recent measurement from LHCb in B2 shape psi phi K decays, and then the phi K subsystem, again, we can study strange mesons. And you see on the right-hand side the corresponding invariant mass distribution from the analysis. Okay, and one of these many contributions to the spectrum actually comes from 2- states. Actually, it's only those two measurements that determine the PDG averages for the mass and the width of the K2 1770. There are further observations of the state from decays to the K2 pi, K phi, K omega final state from production experiments at SLAC and CERN. And you see here again an example of the ACMA analysis of the 2 minus 0 plus K2 star pi S partial wave for the solid curve here. This is a fit with 1 K2 resonance in the model, and the dashed curve, this is a fit with 2 K2 resonances, the K270 and the K21820. And actually ACMA states that with their data, they are in favor of the 2K2 solutions, but they cannot finally state whether there's 1 or 2K2 states. The other experiment that also studied the K2020 was LAS in this K omega final state. And actually, they made a similar statement than ACMA. Only LHCb and their analysis of the shape phi K final state, they say they observed the K2020 with a significance of 3 sigma. And those are the only 3 observations of the states. And nevertheless, this is an established state. Still, there are only 3 experiments that observed or potentially observed it, and 2 of them claim that they cannot finally decide whether they're 1 or 2 K2 states in this 1.8 GeV mass region. And finally, there's the K22250, which was observed mainly in the lambda antiproton final state. And you see here again a measurement from the CERN omega spectrometer, so the D wave intensity distribution, which shows this peak here slightly below 2.3 GeV. The last JPC sector I want to discuss today are 1 plus states. You see here the partial wave in the decay into rho K. They're both on an S wave, which shows this nice narrow peak here in the mass region of the K11270 with some bump again in Seymour's shoulder, which potentially arises from the K11650, so one of the states that need further confirmation. The K11270 and its part in the K11400 was, of course, also studied in recent measurements, for example, in D2 K3 pi decays, where then again the K pi pi system appears as a subsystem and allows us to study strange mesons. And you see here on the right-hand side the corresponding invariant mass squared distribution from this LHCb measurement. And you see here clearly this kink in the mass region of the 2 K1s. And then there's a recent measurement from Bell in B2 shape psi K pi pi decays, where we again can study strange mesons in the K pi pi subsystem. And you see here again the corresponding invariant mass distribution, which shows this clear peak here with some shoulder in the mass region of the K11270 and K11400. And finally, of course, in principle, the perfect laboratory to study K1 states are in tau decays. We see here the results from a measurement from CLIO 2 in tau to K pi pi new tau decays. And they model the intensity distributions and perform partial wave analysis with a large contribution here from the K11270 and a smaller but also large contribution from the K11400. However, they get a much larger width compared to other observations for the K11270. Actually, it's even worse if we look again into the PDG listings for the K11270. And there's some potential bimodality again in the width of the state, where there are some measurements that observe a width of more around 90 MeV, and other observations measure width of above 110 MeV. And those are just the 3 measurements that enter the PDG average. There are more measurements in the different regions. And this might not even be experimental discrepancies, but there are also proposals that this K11270 is a 2-pole structure similar to a lambda 1405, and the different poles have a different width. Then there is also the K11650, so this possible further state. And as it is at a higher mass, it cannot be accessed in DO tau decay. So actually the situation is even worse, because in principle, the low mass tail of the K11650 still might contribute to the data of DO tau decays. So it's more that they actually would need a precise input of this state to include it in their model, because if they see only the low mass tails, this might be too less information to extract the parameters themselves. The K11650 was observed in this LHCb measurement of B2 chip psi K phi decays, or in the K phi and K pi pi final state from production experiments at CERN. And you see here on the right-hand side again a result from this ACMA analysis in the 1 plus 0 plus K star pi D partial wave, which has 1 peak in the slow mass region of the 2 K1s. And then there's in principle another peak at about 1.8 GeV. It's actually just one measurement that determines the mass of the state, or the PDG average for the mass of the state, to be at around 1650. Actually, most of the other observations here state more in the 1.8 GeV mass region. So this, I think, again, clearly shows that the state clearly demands further clarification. So coming back to our compass data, we were quite surprised seeing this signal here slightly below 1.5 GeV in the 3 plus 1 plus K star pi D partial wave. And we are surprised because there's no known or predicted 3 plus state in this mass region. In addition, this signal was very sensitive to systematic effects. So you see here in different colors the result of this partial wave in different systematic studies. And okay, the shape of this signal changes drastically. So we performed actually many systematic studies, many Monte Carlo studies, and tried to figure out where the signal comes from. And finally, it turned out that the reason for it is that our final state particle identification, which we need to separate the negative kaon from the negative pion in the final state, does not cover the full kinematic range. I mean, this we know, of course, but this unfortunately leads to holes in our acceptance. And these holes lead to a reduced distinguishability of partial waves and then lead to the systematic effect, which we call leakage. The good news are that this seemed to affect only a small subset of partial waves and that we have various methods to identify them. So this leakage effect happens only in certain partial waves and only in certain mass regions. But for them, of course, we see very large systematic effects and it will be very hard for us to extract physics from there. So this brings me to my summary. In the strange meson sector, there are many states still missing or need further clarification. Many of the measurements are more than 30 years ago, and most of the recent measurements are from tau or heavy meson decays, and they also do have their caveats. COMPASS has collected the so-called world largest dataset in the fractal reproduced K-pi, where we are able to observe well-known states like the K2 star here. We see also potential signals from excited states, like here in this high mass tail of the 2- partial waves. However, we know that a few of our signals are affected by large systematic effects, and then we cannot, well, it will be very challenging to draw physics conclusions from them. And this actually brings me to a new proposal for a new QCD facility at the M2 beamline at CERN's SPS accelerator called COMPASS plus Amber, and Stefan Paul talked about it already today morning. Where one aspect of this very broad physics project is a spectroscopy of strange mesons using a radio frequency separated high energy and high intensity kaon beam, which would allow us to select and to measure a data set which is at least 10 times larger than the data set collected by COMPASS, which I showed today. And with such a large data set, we could map out the strange meson sector with a similar precision as we did it already for the unflavored light meson sector, for example, with our 3-pi analysis. And the proposal for the phase 1 of this experiment was recommended by the SPSC recently. And with this, I want to thank you for your attention.
Yeah, Stefan, thank you very much for this very nice talk on very recent data. It's now open for questions, comments. I could ask about the two-body isobars in your three-body analysis, for instance, K-pi. Did you just use the states, the Breit-Wigner resonances in the PDG, or can one really free the fit and determine the K-pi states, for instance, the kappa, K star 0, and so on, or quite enigmatic states?
That's a very good point. I mean, okay, actually what we do in the analysis I showed you today was still use the classical isobars parameterized by Breit-Wigner resonances. We did first tests, and Stefan Paul showed one example of the P-wave, K-pi, P-wave today morning, that we tried to free individual waves. So then we replaced this Breit-Wigner isobar parameterization by stepwise constant functions, and this way we can then extract actually the pi per amplitude also in our fit, so the amplitude of the pi per subsystem in this K-pi free-body final state. But unfortunately, okay, with 700,000 events, we will not be able to do this almost complete analysis, I would say, as we did it in the 3-pi analysis with where we free a large fraction of our data, but in this analysis, most probably we'll be able to free just individual waves. Of course, we plan to look also into other waves. For example, the pi per S wave is, of course, a very interesting candidate. But I think this is, again, one argument why even if we have already nice data in this COMPASS analysis, I think we still need more and better data to, for example, use this free isobar analysis at its full power to free many waves simultaneously and try to be really as bias-free from this isobar model as possible.
There are more questions. I think the next was Misha, question by Misha.
Yeah, so it depends on how much time we have. I mean, I would mail Stefan also. His nice presentation triggered a few questions I had. So can you clarify the maybe do you remember for Cleo presentations, the pictures you showed had some kink at some threshold they put in. So I'm wondering what is that, and do we also do this? Yeah, for the K1, you see that there is some kink in the parameterization.
Yeah.
Which threshold did they put? Do you know? Is it KK?
No.
I mean, it's pretty spectacular shape, right? I mean, they must have done something interesting there. And then I think I will pass to Bernard. As in mail you some other interesting thing.
Sure. Was very welcome.
Yeah, Bernard, please go ahead.
Thanks, Stefan, for this nice overview. Maybe just you want to say something how it is planned in the future facility to avoid this hole in the PID for the kaons that we have at the moment. I think it would be interesting to hear that.
Okay, actually from the instrument point of view, depending on the beam energy, it might clarify itself. I mean, if we go down to beam energy of 50 GeV or something like this, in principle, then we can cover a full kinematic range, because at the moment we have a PAD up to 40, 50 GeV at the higher end. And then for the lower threshold, so for low momentum tracks, there are ideas to use to perhaps add another ridge detector, so another ring imaging Cherenkov detector to cover then this low momentum range. But this depends more on the beam energy, and this, to best of my knowledge, is still an open question. What will be the best choice there?
I have a short follow-up. Actually, Bernard asked a similar thing, what I wanted. Do we have a way to a priori say this type of cut will lead to such a leakage between waves? So without running complicated partial wave analysis, do we have a way to say how much we're gonna suffer from acceptance holes?
Perhaps let me go to my backup slide. Okay, this is actually, okay, what you can see here, this is the distribution. So it's the main task of the ridge is to separate the negative kaon from the pion. And what you can see here is the momentum of negative kaon versus the momentum of negative pion. And this hole here, this gap in between, this is what this ridge acceptance does to us, because as I said, we can only identify particles in this band from around 10 GeV up to around 50 GeV. So if the beam momentum would be 50 GeV, then in principle, okay, this whole triangular would shrink and we would be just in this region here below, where at least from the high momentum point of view, then we could cover everything. And if we don't have a hole there, we don't have a hole there.
Why 3 plus then?
Sorry?
Why 3 plus? So
this I don't know. This, I mean, we can, with Monte Carlo studies, we clearly could figure out which waves are affected, and there are also other methods with looking at the overlaps of different partial waves. We can see which you have kind of something similar in the zero motion with pi analysis, so directions in your amplitude space in which you can go without changing actually the model, because you're missing information from this hole in your acceptance. And from there, we also see that these waves are contributing just from their shape in the phase space distribution.
Thanks, Stefan. That clarifies. Yeah, thanks.
Yeah, thank you, Stefan. Thank you again. And we now have the last two talks of this evening, and both are about GluX. First, Igor Strakowski.
Okay. Let me hope that you can see my full screen, right?
Yeah.
Can you see it?
It's good, yes.
Okay. Let me go. And good evening, good day, and good morning, depending on where you are. And let me say I appreciate organizers who invited me to give a talk and about a plan of our new Kelong facility, which will work at Jefferson Lab, specifically that recent JLab pack. Give us a blessing, as Stefan told you at the end of his talk. And actually my outline is here, and then I will follow archive version of our proposal. First of all, what kind of IAMs we are considering for our Kelong project. And one and very important step is to establish secondary neutral Keon beam at Jefferson Lab, which flux should be of 3 orders of magnitude higher than SLAC had a while ago. Then, and there are 2 more steps. One, to focus on Hyperon spectroscopy and to measure differential cross-section and self-polarization, which allow to make high-quality phase shift analysis and to look for as much as possible resonances. And then, today was a lot of talks about the strange meson spectroscopy. Our goal is to focus on pion-kaon interaction and to establish a pole position in either spin half and 3/2. And there is a link of our activity to the ion energy facilities and to allow to understand formation of our worlds through in several microseconds after Big Bang. But that is some sort of the byproduct. So, and to support our project, we had 4 international workshops and posters are here. And then let me start to talk about Hyperon spectroscopy. And there are 2 famous and baryon multiplets, octet and decuplet. And then we can compare, one can compare and reports of PDG and how many states PDG reported, and then how many states quark models and latest calculations proposed overall. And we know only as a quarter what was proposed. And that is means for us that missing states problem is still valid, and it's good to solve this problem. And then the history of hyperons started back to 1947 when Manchester group reported and first hyperon observation, which was lambda 1116. It took about 60 years when our group reported and first pole position for hyperon, for not for this state, for particular lambda 1520. We did analysis of the Keon electroproduction data came from JLab Hall 8. So, and there are many reactions which one can possible to study using neutral Keon beam, which I tried to show you, and using proton and neutron target, hypothetical neutron target, because definitely it should be neutron target. And to search for missing hyperons, one can possible to select the following reactions. And as illustration, what one can possible to get, if you will, thinking about this specific reaction for the sigma hyperon production. So, and Bond-Gachina group and using own phase shift analysis technologies generated angular distribution for differential cross-section for 2 different solutions. You can see how big, how huge difference between 2 different solutions. And the roadmap to study hyperon spectroscopy is quite well known. And facility, experiment, and data which important to collect, and then phase shift analysis which allows to get amplitudes, model dependent, model independent. It's a tricky business, but then we have to look for the pole position on complex plane, which will allows us to get a solid evidence to support resonances, and then PDG will report it. So, and the key issue is data. So, and this, my page shown and what kind of data available and using K-long probe. It's not so big, and 2,500 differential cross-section, very little a number of polarized measurements. Of course, and most of data which community collected during this 20 years activity came from bubble chamber measurements. Of course, there were no crazy people who put polarized target inside of the bubble chamber. So for that reason, we have no chance to get a double polarized measurements. And we know about very high activity of many facilities which I label on the left side of this slide. So, and the technology of phase shift analysis formalism and associated with the Gerhard Höller recipe, and which is quite simple in the case of the two-body reactions like elastic or charge exchange reactions. So that is illustration which I took from Mark Manley, more or less recent papers, and possible to see quite reasonable fit of differential cross-section, but possible to make some sort of the complaint, but nevertheless, and we can accept somehow this result. But, and if you're looking on this polarized measurements plot, and what can possible to say that modern polarized measurements are tolerable for any phase shift analysis solution because they cover, they have a spread between -1 to 1. So, and then we generated pseudo data using GlueX as a detector properties and give this pseudo data to the Bongachina group. Then they made evaluation and projection and what we can expect in the case of the 100-day statistics and 20-day statistics. And that was important for us to satisfy PAC. And then the top two plots shown differential cross-section and polarized measurements, and green band shown what we can get in the case of 20 days and yellow 100 days. For two specific resonances which we selected to illustrate, one can possible to see that 100 days definitely reliable. And the bottom table shown and the difference in the mass and width distribution, and unfortunately no information about this sigma 1920 which PDG is ready to report, and then JLab latest group reported up to 4 different kind of results for each of these resonances. But that is one more test addressed to sigma 1920. And I shown you this plot and then what kind of trick we made. And if you will remove this resonance from the analysis, then immediately chi-square in the case of the 100 days will jump by huge amount. In the case of 20 days, the jump is much smaller, but it's not really acceptable in terms of the statistics. So, and then, nobody made any measurements using neutron target. So it's absolutely terra incognita. And Maxime May selected 6 different models and focus on the pole positions for lambda 1405, which is a very attractive task. So that is a different distribution between different results of the pole position. To illustrate how it will work in terms of the absorbers, cross-section and polarized measurements for different reactions for very small particular momentum of the neutral kaon, which is about 300 MeV per C. So, and then that is my summary, and which I hope can illustrate what we can expect in the case of the 100-day statistics and how many hyperons we promised. I do not like to use the term discovery, but at least we will have a chance to do observation. Actually, it will follow to the long-range plan for nuclear science, which is 5-year-old. So then let me say a few words about the plans for strange meson spectroscopy. And today it was several really great talks about it. And so, and we selected at least 3 different reactions to study it and to measure K plus, K minus, and K long in the final state. That is the SLAC results. And one can possible to see that the area sensitive to the kappa is really almost empty in the SLAC measurements. And Bell shown some results, but uncertainties are really huge. And if you will project what we can expect using K-long facility, you can see this cartoon, which definitely improve our knowledge about kappas. So, and scalar meson nonet, which has 4 kappas, and we have a chance to get information about all of them. And specifically that PDG asked future confirmation. And let me show you some nice cartoon which came from Bob Jaffe recent talks, and to compare ordinary meson states. And this is a kappa's states, which is really attractive. And definitely it's good to file this distribution. So, and that is my short summary of the study of pion spectroscopy which you proposed. And unfortunately, Stefan had a chance to show these 2 slides, 2 plots at the end of his talk. And so that is a projection what we can expect to get. Actually, Jose and his former students archives using our pseudo data generated a pole position. So it means that we will have a chance to reduce uncertainties of mass in kappa by a factor of 2 and uncertainties in width by a factor of 5. And then it will allow us to accomplish this establishment of the scalar meson nonet. Of course, that is not a final goal of our study. I hope we will make a deal with the heavy, strange mesons as well. So, a bit of history. And the first paper addressed to the possibility to have a neutral kaon beam associated with the famous Fizrev paper, which Drell and Jacob wrote back to 1964. At that time, and CP evaluation was a very hot topic, and this definitely was a theoretical request to SLAC experimentalists to do it. So, and probably fortunately, Cambridge Electron Accelerator in 2 years reported and neutral kaon photo production and using different nuclei. And then Daresbury Nina facility using Manchester group reported this. And recently, Mike Albrow, who was a student at the time, told me that his advisor, who was a leader of this collaboration, Paul Murphy, who passed away about the same time when JLab PAC gave us approval. And he told me that Paul was very impressive about the possibility that his dream will make some realization across 50 years. About the same time, and SLAC reported a similar neutral kaon photo. In this case, it was the electric production at SLAC. So, and then what we can expect at Jefferson Lab. And Jefferson Lab facility is probably right now well known these days. I will focus on the fourth hole D. So, and which has to have a 12 GeV beam, which will produce a photon beam, and finally, and neutral kaons will hit cryogenic target. That is some sort of the beam line. So initial 12 GeV 5 microamps electrons with broad bunch spacing will hit copper radiator inside of the compact photon source, and then photon beam will interact with the beryllium kaon production target, and we'll use a sweep magnet to clean up a beam from the charged particles, and then kaon flux will be measured by the flux monitor system, and then kaons will interact with the cryogenic target in the center of the GluX detector. So, and as I mentioned before, and our flux should have a factor of 1,000 larger than SLAC had before, and we compare our Monte Carlo simulation versus at 12 GeV what SLAC had experimentally at 16 GeV, which are really similar. So that is a photo of the experimental hole and with the GluX detector. And then, and let me point out the important fact that mean lifetime for neutral kaons is much smaller than mean lifetime for neutral kaons. It means that we'll have a chance to do some measurements between neutral kaons and proton or neutron target at much smaller momenta. And momentum measurements with time of flight, we'll do it and to measure, yes, time of flight between start counter and ref of CBUF system. So, and the delta P over P are shown here, and that is a resolution in terms of the W depending on the resolution of the start counter. But right now, our resolution is about 250 picoseconds, which is almost acceptable for our purposes. So, and there are several illustrations of the particle identification, which came from our Monte Carlo, which knows and full capacity of the GluX detector. So, and this slide shown comparison between results of the bubble chamber measurements with some phase shift analysis results, which came from Mark Manley paper. That is a projection using a giant simulation, which we are expecting during the 100 days of the run period. And then, that is our time request table. So, and for several important reactions, I was trying to summarize what kind of statistic, how many events we will get, and that is for differential cross-section, and that is for self-polarization in the case of this sigma naught in the final states. So that is a current map of our long collaboration, which has 110 experimentalists and almost 40 theoreticians who are supporting our project. And that is almost my summary. So, and threefold our goals is it's to establish this facility, to make it real, and because right now our proposal is accepted, and then to find enough evidence about many hyperons, and then to do something for strange meson spectroscopy. And the important and side effect is to help to understand as a process of the formation of baryons from quark and gluons. So, and then collaboration is starting now, and welcome for new members. So, and then if I have 2 more minutes, do I have 2 more minutes? Oh, I cannot hear you, sorry.
Hello, yeah, just 2 more minutes, yes, of course.
Okay, so it's only 2 quick pages about how history of an universe developed. So I'm talking about the range of few microseconds after Big Bang, and where one can possible to expect an Kelong contribution and simultaneously G-Park contribution using neutral negative Keon beam. And then recent Houston group evaluation of the this task and using chemical potential, one can possible to see that if they will use only observed resonance, it means that what resonances PDG reported, and then it does not work if possible to add and much more predicted resonances which quark models or lattice proposed, then possible to get reasonably consistent. The priority in this case is hyperons, non-strange baryons, and mesons and nuclei. I cannot clarify what is the exact percentage because I was talking to lattice people, and generally that is a quantitative issue. And then, thank you very much, and I'm almost done.
Yeah, thank you for this very impressive presentation of the new facility. Other questions or comments? Yeah, Oleg, please.
Yeah, you have mentioned a lot of possible things you have to do. And what is the general goal of it?
Okay.
What is the fundamental understanding of QCD would it bring to?
Let me show you this summary for hyperon spectroscopy. So, and definitely, and PDG reported only quarter of the resonances predicted by quark models, different kind of quark models, or
I'm not talking about the resonance predicted by the quark models or whatever. What kind of general knowledge to the QCD it will bring us?
of course, and information about resonances, both, and hyperons and strange mesons will prove or improve our knowledge about QCD and move theory ahead, because we will have a much more experimental data.
In which particular sector, what would help us to understand better in the QCD sector the knowledge of the of these resonances and whatever? Because, you know, it is now important to somehow to concentrate on a very few topics where we have no clue why QCD doesn't work or doesn't provide us with the answers. And this is not enough to say that I'm studying now the Hadron spectroscopy, I'm studying the light Hadron spectroscopy, I'm studying heavy resonances spectroscopy. What for?
Okay, let me give you one example. Maybe 10 years ago, and a sigma meson, or right now it's called F0 500, was not really established. I do remember when first information about pole positions came up, I asked many experts, what do you think? It's a real resonance or it's a general description of the data through summary parameterization? And no, almost single expert said that they believe that that is a real resonance. Right now, and sigma or F0 500, it's a real resonance. No questions, no objections. It's a well-established resonance. In this case, a situation with kappa, because we have some prehistory, and it's much more simple, but nevertheless, we have to establish this resonance and to be sure that this strange resonance is available. And also open questions regarding and heavy strange resonances. They are real, or that is again, some sort of the imitation of the resonances or reparameterization, because, and you know, and pole position or associated and Breit-Wigner, it's a good parameterization. If you will replace Breit-Wigner by Padé-Proximant, but you can get a similar behavior. But Padé-Proximant usually is good to describe background, not a real resonance. For that reason, and it's a good to have a solid information about resonances. And then the next step, it's a job for theoreticians to understand the nature of these resonances. It's molecular states, exotics, or some different kind of states. So we have to have a solid information about resonances. That will allow to move and QCD ahead. That is my naive vision.
Thanks a lot.
I think there are no more questions. So thank you again, Igor. And we proceed to the last talk of this evening, which is also on GluX. It is given by Volker Krede from Florida.
All right, can you see my screen?
Yes.
We go to full screen mode. All right, can you still see it?
Yes, very nice.
All right, good. I recently had some trouble when I went to full screen mode with Acrobat Reader on Zoom. So just making sure. Okay, so a very late good morning from Florida here. I'm aware that I'm the last talk before the next meal, whether that may be lunch or dinner. So It's a great honor to participate in this meeting, and I'm happy to report on recent results from the GLUAX collaboration at Jefferson Lab. I don't think I have to really motivate why we're doing hadron spectroscopy, so I want to introduce the GLUAX experiment and then show you some recent results, mostly on beam asymmetry, maybe following up a little bit on what Igor presented. I'll show you some ideas for the study of doubly strange cascade baryons, and also briefly discuss J-psi photoproduction at threshold. So what we've done at GLUAX, we've observed the first germanium state at Jefferson Lab. Okay, very briefly motivating hadron spectroscopy that resides in the confinement regime where we're studying strong coupling QCD. That's where the world of hadrons is. So what we want to understand is how does QCD give rise to excited hadrons? So in particular for the meson sector, we want to understand what role does glue play, or do gluonic excitations play in the spectroscopy of light mesons. So GLUAX set out to map out the spectrum of hybrid mesons, whereas in baryons, we're still also interested in mapping out the spectrum still, and we're more interested what are the fundamental degrees of freedom. But there are also now ideas and proposals at Jefferson Lab to study hybrid baryons, which in principle should also exist. They're just a little bit harder to study experimentally.
Sorry, I don't think it is correct that we are still on first transparency.
Oh, you can't see my slides?
We see the first transparency.
The title page?
The title.
Oh. I have moved on. So does this work?
Yeah.
May you put on the full screen, please? Thank you.
Well, can you see it now when I move on? So I'm changing slides.
Not full screen.
This is not full screen, by the way.
It is still the strong coupling quantum chromodynamics.
And this is the next one.
Slide. No.
Well, this is full screen for me.
You have to share the full screen part, but then you have to click such that you advance the other.
Okay, let me try something else here.
You share the full screen and then click on it. Then your control is also the full screen.
Okay, and now. Okay, does this work?
Yes.
Yes.
All right. Okay. My apologies for that. I I had some trouble before. I do not fully understand why this is. It was full screen on my laptop here, and it was actually working. Okay. So GLUAX does hadron spectroscopy and we're doing photoproduction. This is complementary to pion nuclear scattering in COMPASS, for example, and positron electron annihilation or PP bar annihilation. So the GLUAX detector is a design for hadron spectroscopy, a 4-pi detector that consists of 2 drift chambers, a central forward drift chamber, and a barrel like inside of a solenoid magnet, and a barrel calorimeter, central calorimeter, and a forward calorimeter, which will provide us, or which provides us with almost 4-pi solid angle. The GLUAX collaboration, I think, is a little smaller than the COMPASS collaboration. We're about 135 members at the moment from 29 institutions located in 9 different countries. GluX has just completed its first phase of data taking, what we call the first phase, which was approved by the JLab PAC, 120 days. So most of the early publications now are based on what we call this GluX phase 1. So GluX started about 4 years ago with the commissioning of the apparatus, and we have published the first physics now a little bit more than 3 years ago. This is a photograph which goes back a few years, but it still shows nicely the solenoid detector here. So Hall D was a new component to the experimental program at Jefferson Lab that came with the energy upgrade at JLab to 12 GeV. This was achieved in 2014. And then, as I said, 2015, 16, that is when GluX started commissioning, with the first physics run in 2016. You can see that here on this picture. So Hall D is the new addition to the JLab experimental program on the other side of the previous experimental halls. Okay, this is another picture of the GluX detector, including the tagger magnet, which resides in a different experimental hall, essentially, which is 75 meters away from Hall D, where the GluX detector is housed. GluX uses linearly polarized photons with a coherent edge at 9 GeV. Our design goal is actually 10 to the 8th photons per second in the coherent peak, which is what we call high intensity. That's the goal. All data have been taken more with like 5 times half of that rate, 5 times 10 to the 7th photons per second. We're going to use, as we've heard before from Compass speakers, we're going to use sophisticated analysis tools, partial wave analysis, in close collaboration with our theory friends at Jefferson Lab and elsewhere around the world. Some brief words about the photon beam facility. So we have the photon tagger here, which I said is about 75 meters away from the liquid hydrogen target. We have an energy resolution of roughly 25 MeV and a linear photon polarization of about 40% in the coherent peak, as can be seen here in the picture on the right. From our first publication. And I mentioned earlier, the design goal is to go with 10 to the 8th photon per second, but we haven't really reached that goal yet. What is a little bit unique to GluX in comparison to earlier low energy experiments at Jefferson Lab, in particular in Hall B with a class detector, is that we have a triplet polarimeter that allows us to actually measure the degree of polarization for the linear photon beam, whereas before this was mostly based on calculations describing the enhancement in the photon spectrum. And that has proved very, very useful. Okay, I'll skip over the slide. So we're interested in gluonic excitations here. And of course, the goal is to identify exotic quantum numbers that are not accessible with a regular quark-antiquark system by establishing the firm existence of such exotic quantum numbers. We know that we have like found or observed something fairly new. It still then remains to be seen whether we really have established gluonic excitations. The Hadron Spectrum Group at JLab has produced first spectra of such exotic mesons. So in addition to negative parity and positive parity mesons, they have clearly identified also the exotic states on the lattice, with the idea that the constituent glue contributes with 1 ± quantum numbers. And if we combine that with the lightest non-net of vector mesons, the 1 −−, this will produce, among other quantum numbers, the non-net of the 1 −+, which is predicted as the lowest mass hybrid mesons. What is interesting, if we look at these lattice calculations and we use in the meson sector the rho as the reference mass and the nucleon mass in the baryon sector, then there appears to be a common scale of about 1.3 GeV for gluonic excitations. So as I said earlier, it is more challenging to identify hybrid baryons experimentally, but certainly the search for hybrid mesons will also guide our searches for hybrid baryons. And there are some ideas in Hall B with a class detector to search for gluonic excitations in baryons in electroproduction, but certainly that program is more challenging than to identify and search for exotic quantum numbers in the meson sector. So where are we at the moment with GluX? We're not there at the point where we've done intensive amplitude analysis and could present results. At the moment, we're still at the point where we're studying the polarization transfer. We're looking for, so this essentially means we're looking for beam symmetry in a large variety of reactions. We have started to study spin density matrix elements, where in addition to the polarization, we have to add the detector acceptance and fully understand our detector system. And then we also started, or we are currently finalizing first cross-section measurements, where really we have to fully understand everything about our detector. So this is where we are at the moment. And then, of course, we're also setting up the framework for amplitude analysis. We've started to look into first partial wave analysis, but we're certainly not yet at the point where we could report any results. So polarization transfer, beam symmetry, spin density matrix elements for vector mesons and cross-section measurements, that's what we're concentrating on in GluX phase 1. So to highlight the reactions, so I mentioned beam symmetries. Those have been measured now and published for single meson reactions, single pi, single eta, eta prime, but also for hyperon production, and also for the negatively charged pion of the delta plus plus in a charge exchange reaction. And then, as I said, we're looking also at spin density matrix element and cross sections for these single meson reactions, with first hybrid searches in these reactions on the right. So we're concentrating, or many groups are concentrating on the eta pi, eta prime pi system, both of the proton and in the charge exchange reactions of the delta plus plus. And certainly 3 meson final states are a little bit more complicated for us at the moment. In addition to that, some groups study J-psi production at threshold, also baryon, anti-baryon final states are interesting. And along those lines, what Igor mentioned earlier, we also have a program on baryon spectroscopy, in particular in the search for new excited cascades states, and I will mention briefly where we are with this. So beam symmetries in single pion production. The linear polarization allows us to distinguish between natural and unnatural parity exchange in this reaction here. So these experiments are closely accompanied by calculations by the JPAC group at Jefferson Lab, and they're even essentially participating in our meetings regularly. So we're working hand in hand. So experimentally, we're looking at the angular distribution between the reaction plane in these reactions and the photon beam polarization plane. So which is conceptually a fairly easy measurement, but of course the devil's in the detail, and it's always difficult to make these measurements. Okay, first results that GluX has published in 2017. So for single pion production, we observe that the beam symmetry is fairly fairly flat and at unity. Overall, we observe significantly improved data quality. And for the eta reactions, actually the first measurement of this kind in the GluX energy range between 8.5 and roughly 9 GeV. For both reactions, the beam symmetries are close to unity, and that tells us that vector meson exchange is dominant here. Also noticeable is that we do not observe the dip that was previously observed in SLAC data at about 10 GeV. So all of this is sort of to lay the groundworks for understanding hybrid mesons. It contributes to our understanding of the production mechanisms in photo production. So we need to understand established mesons, the production of established mesons before we can claim to have observed any kind of new exotic matter. So there was a follow-up measurement of the Ada beam symmetry. So you see that here in the top picture, where with the second measurement, we have actually even significantly improved our statistical uncertainties, and also measured the Ada prime beam symmetry, which is also close to 1, but a little bit lower overall than what we observe in pion and in Ada photo production. Again, we observe the dominance of vector meson exchange, in particular for the Ada reaction. What the JPEG group has done is that they have not only studied the exchange of established mesons, the vector mesons and axial vector mesons, but they've also tried to include like unobserved mesons. So for example, the 2-, exchange. And based on our current data situation, there's no indication for such an exchange. It would substantially lower the beam symmetry. However, we observe something that is consistent with unity. So as a first physics result, we can rule out such a new exchange of an yet unobserved meson. Okay, we also looked at the pi delta plus beam symmetry in the charge exchange reaction, which surprisingly looks entirely different from the reaction of the proton. So we observe negative beam symmetries at low T values, which is dominated by pion exchange. And then the beam symmetry rises towards 1 again, above about 1 values of 1 in T. For another reaction, so for K plus sigma 0, again, we observe something that is consistent with like flat contributions around 1, at least for the T range below 1 GeV. And that tells us that natural parity exchange dominates this reaction in this energy range. Okay, moving on to the cascades, a little bit what Igor mentioned earlier. What is our primary motivation here? So this is again like a result from the Hadron Spectrum group at Jefferson Lab that was published a few years ago. And what we see here for negative parity is the first excitation bands that was supposed to observe 7 states here. And what's known, if we look it up in the particle data group in the booklet, there are only 5 states even known at the moment, and one of them is a poorly established state. So first of all, the cascades, they appear in the octet and in the decouplet. So I call this the ground states. So we're looking essentially for new cascade states with negative parity in the first excitation band, still with masses around like 1600 and 2 GeV. And very little is known about these resonances. The spin parities have never really been measured for these cascades. And even for the ground state, these are merely class model, quark model assignments. So we're trying to make some measurements of spin and parities for these cascades and also search for some of these missing states, even at the very low masses. What's particularly interesting is that situation between 1600 and 1700, where I said there's a poorly established state here that has attracted some interest in recent years. Let me just move on to this next slide here. So there were some indications in class data, which at the time was merely discussed as a fluctuation, but is sitting at the right mass and could be a contribution from the 1620 state. There's certainly some advantage in what Igor said when we come in with some strangeness to make doubly strange baryons. So in photo production, of course, we have to pay a certain price. Since our initial state is non-strange, we have to create two strange quarks. So we have to create two kaons that accompany the doubly strange baryon. So we pay a high price in photo production for studying these states. These programs are in competition with JParc and with the future program in Hall D, but also with programs at LHCb, the Future Panda collaboration, and most importantly, there are active people. There's an active group in the Bell collaboration in electron-positron annihilation. And I mentioned the 1620 state here. This is something that the Bell collaboration has recently published and established. So they observe clearly two peaks here at 1620 and 1690. So this is interesting for us as well to establish those states in photo production and understand better what the nature of these states may be, whether these are just regular missing states or whether we have a similar situation, for example, like a two-pole structure here, like the lambda 1405, or just something else. So this is part of our motivation and interest to do this. But for that, in order to understand any of this, we need to establish these states clearly experimentally. Okay, we have observed the cascade ground state in early GLOAX data. We're in the process of measuring cross sections, the beam symmetry, and also the mass splitting between the isospin related states here. This was part of a dissertation, but as I said, cross-section measurements are difficult, so it's still going to take some time in order to finalize this cross-section measurement. At the same time, we're also looking for excited states. They proceed in a very similar way. So in photo production, we produce an intermediate excited hyperon first, and that will decay into an excited cascade plus another kaon. So it's these excited cascades that we're after in the decay of lambda k. So there are many states that are predicted to decouple from the pion decay and would make these states narrower. So they would be easier to observe in the spectrum directly, and we could avoid the situation of complicated broad and overlapping states that we face in N-star physics. So some preliminary results from GLOAX here. So we have observed the cascade 1820 in its decay to lambda k with a significance of more than 10 sigma. So this is not a fluctuation, this is a real peak. We also have enough statistics if we use the entire GLOAX phase 1 to actually make some measurements in terms of a beam symmetry and a cross section. Interesting. This is really the only state in lambda k that appears to be abundantly produced. You see other structures in the spectrum here, and for those that are familiar with the cascade spectrum, all these structures and fluctuations, they sit at the right place where we would expect cascades, but clearly we wouldn't make any claims other than the 1820 here for any other cascade state. But this is exciting. So GLOAX, that establishes really that GLOAX will be able to contribute to this field. Okay, last not least, J-psi photo production, something that GLOAX has studied and also published already. So at the threshold, there's a large momentum transfer to the J-psi, and there are models that predict that this is proceeding via 3-gluon exchange, a model by Brodsky here. He calls that threshold production would be sensitive to multi-quark correlations, whereas towards higher energies, the production of J-psi proceeds dominantly or predominantly via a single or a double gluon exchange. So this is part of the motivation, and the previous data from Cornell and from Slack in the 70s, and the yellow highlighted area here is where GLOAX can contribute. So right at the threshold, in the threshold area. Also, of course, interesting is the possibility of observing a pentaquark as like reported by LHCb. And we would expect the 4450 state roughly here where the arrow indicates. So now, what have we measured at GLOAX? First of all, we've seen the J-psi in its decay to electron-positron, and that was the first ever observation of charmonium at Jefferson Lab, and we're all so excited about it that the collaboration was awarded a plaque. It may be hard to see, but we see that peak here of the J-psi. So that was like fairly exciting. However, results are that we measured the T-slope, the differential cross-section here. We measured the slope parameter and published that in just last year. And we've substantially improved the data situation here for J-psi production at threshold. We certainly or clearly do not observe any pentaquark in this cross-section measurement. What you see here is calculations by the JPAC group, where the pentaquark would appear as this peak here in the cross-section, but our data are inconsistent with that. So no observation of a pentaquark, and all we've done at the moment is put some limits on such pentaquark production, but it still remains an intriguing idea. Okay, briefly summarizing what are the aspects of the GLOAX physics program. So we're primarily interested in mapping the spectrum of light quark mesons and looking for gluonic excitations. And this in particular is interesting also if we include strange final states. And that has that's going to work much better now by adding a Dirac detector, reusing some components of the Babar Dirac detector. So we've commissioned the detector and we've started data taking. So first data are available to study strange final states. In addition to the regular spectroscopy of mesons and baryons, we're also looking at the Primakov effect, so precision measurements of the ADA in radiative decays. We have plans to study the charge pion and pi0 polarizability at GLOAX, and we have a whole program on summary tests and symmetry tests of rare ADA decays to all neutral final states. And for the longer term, there's also a nuclear program at GLOAX. So in a summary and an outlook, early GLOAX data show rich prospects for hadron spectroscopy. We have reached the goal of high luminosity running, plus using the Babar Dirac detectors, which will extend the current program to strange quark states. We've observed first charmonium. So a brief outlook on partial wave analysis. So we are, of course, primarily interested at the moment in looking into the 1- states, the only state, the only quantum numbers where some candidates exist. This is all inspired by results from the COMPASS collaboration in the Ada prime, Ada pi system. Not going into details here. So this is part of the motivation for GLOAX. So we are looking into Ada pi of the proton and also in the charge exchange reactions of reaction of the delta plus plus. So this is a priority at the moment because this can be easily compared with results from, for example, the COMPASS collaboration. Current data sets indicate that we have sufficient data to explore these systems with even competitive statistics using GLOAX phase 1 data. We have multiple charge combinations available, and GLOAX allows to look at all the possible decay modes. And as I mentioned earlier, we're doing this in close collaboration with JPAC, who have started to produce amplitudes for these reactions in the same way that JPAC is also closely working with the COMPASS collaboration. So about 70% of the photo production cross-section in the energy region 7 to 12 GeV has multiple neutral states, and for that reason is completely underexplored. And that will allow GLOAX to make key experimental advances in this field in the years to come. And my summary sentence, advances here in both theory and experiment, will eventually allow us to finally understand QCD and confinement. Thank you very much.
Yeah, we thank you, Volker, for this very comprehensive talk and congratulations for all these nice data. So this is open for discussion. Oleg, please.
What do you mean under the competitive statistics compared to COMPAS?
Well, just in terms of
what is your data sample, the exclusive data sample compared to ours?
Well, I mean, the production mechanism is of course, like complementary and different, but we're hoping for the exotic peaks to have as much statistics that is observed by the COMPAS collaboration. So that's what I mean by competitive. Competitive in terms of statistics and statistical uncertainties for many of these exotic final states.
Thank you.
Yeah, are there more questions? Last questions for this evening?
Late morning.
Doesn't seem to be the case. So thank you all for this nice session with very nice talks and good discussions. I don't know whether the organizers still want to say something. I think we convene tomorrow at
1:30. No, thanks to everybody. Thank you very much. And see you tomorrow at 1:30 p.m. in Italy.
Buona serata.
7:30.
Bye.
US. Ciao Anna.
Ciao.
Bye bye.
Bye then.
Ciao.
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 Ciao ciao.
Ciao, buonasera.